Uh, Good morning, good afternoon to everybody. Welcome all the participants for the 20th Lomonosov conference at the plenary session. It is an honor and pleasure for me to give a floor to Professor Antonella Castellina, who will chair the morning session. Professor Castellina, please.
Thank you very much for your kind words, and welcome to everybody also from my side. So this morning we have five interesting talks. We have only 2 hours, as you know from the program. So please, I ask all the speakers to stay in time. We give 20 minutes for the talks and 5 minutes for discussion. So I can warn you if you want about your time, the end of your time. So let's start immediately, not to waste any time. I give room to Francesco Palma, who is going to talk about the status of the Access Limadu experiment, the space mission. Please, Francesco.
Good morning. Can you hear me?
Yes, very well.
Okay, thank you.
You can share your screen.
Yes.
Perfect.
Can you see my... Okay.
Yes.
Okay. Okay, good morning, everyone. My name is Francesco Palma, and I work for the Italian National Institute for Nuclear Physics in the division of Roma Tor Vergata. Thanks very much for this opportunity to illustrate to you the status of the CSES Limadu space mission after 3 years in flight. CSES stands for China Seismo-Electromagnetic Satellite. This mission has been designed to achieve 2 main scientific objectives. First, to improve our knowledge of the near-Earth electromagnetic environment, in particular to investigate possible correlations between perturbations in the ionosphere and the occurrence of seismic events. And the second, to better understand some phenomena of solar-terrestrial interactions and cosmic rays in the space weather context. The satellite was launched on the 2nd of February 2018 and was put into a sun-synchronous orbit at about 500-kilometer altitude with a 97-degree inclination and a 5-day revisit time. The satellite has got 8 instruments on board, among which the high-energy particle detector, HEPD-01, that was developed by the Italian collaboration of the CSES mission. The Italian collaboration is named after the Italian missionary in China, Matteo Ricci, whose Mandarin name was Limadu. As I have already mentioned, the Italian team was in charge of the design and the construction of the high-energy particle detector. On this slide, you can see a Gen4 schematic of HEPD-01 on the left and a computer-aided design of the detector on the right. From top to bottom, the instrument is equipped with 2 double-sided silicon microstrip planes, a trigger system, which is a plastic scintillator plane segmented into 6 paddles, and a range calorimeter. The range calorimeter is composed of an upper section made up of 16 plastic scintillator planes and a matrix of 9 LISO crystals on the bottom. Finally, HEPD-01 is equipped with an anti-coincidence system comprising 5 plastic scintillator planes, 4 lateral surrounding the scintillator tower, and 1 plane on the bottom. Thanks to this set of subdetectors, the instrument is optimized to detect electrons in the energy range between 3 and 100 MeV, and protons between 30 and 250 MeV. The detector has been designed for a rich physics program: the low-energy cosmic ray physics, the physics of the radiation belts, and last but not least, the solar and magnetosphere physics. Regarding the first item, 1 year ago, we published the galactic cosmic ray proton spectra in the 40-250 MeV energy range, while at the moment we are very busy trying to finalize our ongoing analysis on cosmic and reentrant lepton spectra. For what concerns the study of the Van Allen radiation belts, we are about to publish proton fluxes inside the South Atlantic anomaly in the same energy range as galactic protons. Finally, in the solar in the solar physics, in the field of solar physics, due to the minimum solar phase, up to now we have studied only some geomagnetic storms. In particular, some months ago, we published the response of our instrument to the August 2018 geomagnetic storm. So I have mentioned both electrons and protons, but how do we perform electron to proton separation with the HEPD-01? This slide shows a possible strategy we use to separate electrons from protons. The ADC signal released in the top calorimeter plane is plotted on an event-by-event basis as a function of the energy deposition in the whole range calorimeter. And these are the two curves we used to select the hydrogen band in our analysis of galactic protons. In this work, we published 3 semi-annual galactic hydrogen spectra in 3 different consecutive periods between the very end of solar cycle 24 and the beginning of solar cycle 25, from August 2018 to January 2020. And for each time interval, we selected galactic particles in the geomagnetic region above 0.26 gigavolt, corresponding to about 35 MeV. This is the galactic proton energy spectrum we measured for the first period from August 2018 to January 2019. We compared our results with the theoretical prediction from the heliospheric modulation model, the solid blue curve in this plot, and with the SOHO spacecraft, the red square. SOHO is the only mission providing data at such low energies. We found a good agreement in all the 3 periods under study, considering both statistical and systematic uncertainties. From a comparison between this first spectrum and the last one, from June 2019 to January 2020, we observed an overall increase of about 9% in a very good agreement with the variation observed in SOHO. This behavior is not surprising, is expected because as the solar activity continued to wind down from 2018 to 2020, the effect of the sun magnetic field was less and less strong, resulting in higher proton fluxes. Unfortunately, the overall errors in the first and last energy beams do not allow the observation of a clear energy dependence in the demodulation over time. As you can see from this plot, we appreciate a modulation effect only after the end of 2019, when the effect is larger than our systematic uncertainties. As expected, we observed a larger effect at lower energies, and for this particularly quiet period, we observed no modulation effect at energies higher than 59 MeV. Regarding cosmic electrons and positrons, our analysis is still preliminary, so I will not go into details now. But as you can see from the blue full circles in this plot, we have already found quite a good agreement with the past and current experiments, for example, ISOP, which operated in similar periods of solar activity. Another ongoing analysis is about the reentrant lepton spectrum. These secondary particles are generated with upward going directions and are then bent by the geomagnetic field back to the Earth. This is why they are called reentrant. They are a byproduct of cosmic rays near the equatorial region. In our analysis, we have selected the L shell values between 1.1 and 1.2 Earth radii. The agreement of our preliminary flux with the Pamela data in the overlapping region looks already reasonable, but we are trying to extend the analyzed time period to inspect other L shell regions, and let's hope to include the measurement below 10 MeV. In addition to cosmic rays of galactic origin, we also studied protons trapped in the South Atlantic anomaly. These protons are produced by the beta decay of free neutrons that are in turn generated by the interaction of galactic cosmic rays with the Earth's atmosphere. Many efforts have been made up to now in order to model the near-Earth radiation environment, which, as you know, is dangerous for both human space flights and a satellite system. The state-of-the-art is provided by the NASA AE9 AP9 set of models for high-energy electrons and protons, even though their predictions are not based on a statistically sufficient sample of direct measurements. And these are our results on trapped protons in the South Atlantic anomaly during the minimum activity phase between solar cycles 24 and 25 at energies ranging from 40 to 250 MeV. In the top panels, you can see South Atlantic anomaly proton spectra for 3 different local pitch angle intervals, while in the middle and bottom panels, trapped proton fluxes are presented as a function of 3 local pitch angle and L shell intervals, respectively. We found a general good agreement with the AP9 model, that is the red line in these plots, except for the higher energies, where fewer experiments provided valid data to construct reliable estimates of the fluxes. Moreover, we observed a general time stability of the trapped proton intensity for 3 different energy beams, which again is due to the minimal solar activity over the period between mid-2018 and late 2020. Finally, we produced geographical maps of omnidirectional proton fluxes as a function of latitude and longitude for 2 energy beams. A low energy one, 45 MeV in the left panel, and one higher, between 200 and 230 MeV in the right panel. As already observed by Pamela, low energy protons are present in almost the whole region of the South Atlantic anomaly, peaking in its central part, in the bulk, while on the contrary, high energy protons are more concentrated in the bulk, while they are practically absent in the peripheral sectors. In the framework of the CSES mission, our detector can also be used as a space weather monitor. Actually, the past minimum was particularly quiet, and after 2017, no extreme solar energetic particle events occurred. However, we have been able to assess the capability of our instrument during some transient phenomena, in particular during the strong G3 class geomagnetic storm, which occurred on the 25th of August 2018. The consequent magnetospheric disturbance was strong enough to trigger a response in our detector. As you can see from this comparison between the HEPD 01 count rate maps, some days before in the left panel and after in some days before in the left panel and after in the right panel, the impact of the storm. As a consequence of the arrival of the storm, we observed an increase in the particle rate at both northern and southern latitudes. Both maps are related to a trigger configuration which allows the detection of the lowest energetic electrons at energies higher than 3 MeV. As for protons, their contribution to the trigger rate increase is negligible due to the absence of direct injection from solar energetic particles during this specific storm event. The increased particle rate during the storm time is also visible as a function of L shell and time, as you can see from the top two panels on this slide. The top three panels show the HEPD 01 trigger rates for 3 different trigger configurations corresponding to as many increasing energy thresholds for electron detection. Higher than 3 MeV, higher than 4.5 MeV, and higher than 8 MeV, respectively. In the top two panels, we observed a clear enhancement of trigger rates starting on the 25th of August, exactly in coincidence with a strong decrease in the disturbance storm time index down to about minus 190 nanotesla, as you can see from the bottom panel on this slide. We detected this increase during all the storm recovery phase at L shells immediately above 3, and that is due to a phenomenon of magnetospheric electron acceleration, which lasted several days. Finally, we shifted the focus of our analysis to the observation of possible Furbush decreases, which are rapid and temporary decreases in the observed galactic cosmic ray intensity as a consequence of the arrival of a coronal mass ejection. For the August 2018 geomagnetic storm, we detected a Furbush decrease of about 8%, as you can see from this plot. And this Furbush decrease was registered by 3 neutron monitors as well. To conclude, the CSES Limadu space mission can be really considered as an extension of PAMELA and AMS-02 in the study of low energy cosmic rays. And after 3 years in flight, our results are quite satisfying. We published new results on the galactic hydrogen energy spectrum between 40 and 250 MeV To our knowledge, they are the first results on galactic protons obtained in such a low energy range since a series of balloon flights in the 60s and the 70s. Then we obtained the first results on trapped protons in the South Atlantic anomaly at energies below 250 MeV. So our low energy data can provide an excellent cross calibration for radiation environment models, a task that is no longer performed by the Van Allen probe missions. We still need some time to finalize the measurements of the cosmic and the reentrant lepton spectra. In particular, for what concerns reentrant leptons, our goal is to provide data, reliable data below 100 MeV, where there is a substantial lack of recent data, thus contributing to the development of secondary particle production models. And finally, for what concerns space weather, our results are promising, especially in view of the approaching of the solar maximum and of the already planned constellation of CSES satellites in the next few years. In particular, a second satellite is currently under construction in China, and the Italian team is building a second high-energy particle detector, which is expected to offer a further insight into both low-energy cosmic ray physics and space weather studies throughout solar cycle 25. Thank you for your attention.
Thank you very much, Francesco, for this very nice talk. So now the floor is open for questions. Please raise your hands. You can use the reaction button in your Zoom window. Maybe I can start. I have a curiosity. At the beginning, you talked about the proton flux. I'm wondering what is the contamination that you get from light nuclei on your proton flux, and also what is the main contributor to the systematic uncertainty on this flux?
Yes. Okay, the most important source of contamination for galactic protons is given by high energy electrons. In order to avoid contamination from high energy electrons, inducing electromagnetic showers in our calorimeter, we apply a certain number of selection cuts, however, this contamination is about 10% at energies higher than 50 MeV. And we estimated this contamination from Monte Carlo simulations. For what concerns systematic uncertainties, we took into account two possible contributions. One from the accuracy of the deconvolution procedure we applied to take into account the particle slowdown and the energy losses in the detector. And the second contribution is given by the discrepancy between Monte Carlo and flight data, even after the digitization procedure. And these systematic uncertainties amount to an interval ranging from 4% to 13%, depending on the energy. The highest contribution is given in the lowest part of the spectrum, so at lower energies. As you can see, the discrepancy with the model, with the Helmut model, is larger at the lower energies. So the uncertainty is higher in the lowest part of the spectrum.
Thank you. So, more questions for Francesco? I don't see any hands, so let's thank again our speaker. Thank you very much. And we go on with the program. The next talk is by Francesca Alemanno. She will talk about the DAMPE space mission, the status and main results. So please, Francesca.
Hello, can you hear me?
Yes.
Okay. Okay, I cannot share.
Francesca, so you have to take out your screen. Okay.
Thanks. I will share.
Perfect. Please.
Okay. Okay. Hello to everyone. I'm Francesca Alemanno from Gran Sasso Science Institute and INFN LNGS. And I will give you this talk about the DAMPE space mission status and main results. First of all, DAMPE stands for the Dark Matter Particle Explorer, and it is a satellite-based experiment, which was launched in December 2015 from China, and it is currently orbiting in a sun-synchronous orbit and at an altitude of 500 kilometers. The DAMPE collaboration is an international collaboration, and it involves institutes in China and Europe. What are the scientific objectives of DAMPE? Here in this first row, you can see some performance that we were expecting, and these plots are obtained with some simulations. Starting from the first one, here you see the electrons and protons spectrum that we were expecting. So we wanted to reach higher energy with respect to previous results and with good precision. Then we also want to study galactic cosmic rays, and here you see some expected performance for proton and helium, but we also want to study heavier nuclei, so carbon, oxygen, up to iron. And also in this case, we want to extend the spectrum to high energy with very low uncertainties. After this, we want to do also gamma ray astronomy. Here you see a preliminary result from DAMPE, and you will see more later. And then, okay, the name of this experiment is Dark Matter Particle Explorer. So of course, we want to study dark matter. And there are also some secondary objectives that are study of exotic particles and multi-messenger astronomy. Some more details about the DAMPE experiment. We want to explore the energy range from 5 GeV till 10 TeV for electrons and gamma, and from 50 GeV till 200 TeV for protons and nuclei. The lifetime of the experiment was estimated to be more than 3 years, but the experiment is now taking data for 5.5 years very well, so it will continue to take data. In this table, you can see some comparison between DAMPE and AMS and Fermilat, and from here you can see these numbers in which you can appreciate the difference in, for example, energy resolution that for DAMPE is very low, around 1.2% at 100 GeV. and also the thickness of the calorimeter, that is 32 radiation length. Now, how is the detector made? Starting from the top, we have the PSD, the plastic scintillator detector. And with this detector, we measure the charge of the incoming particle, and also we are able to identify electrons and gamma rays. Then the next detector is the silicon tungsten tracker, so-called STK, made by silicon strips used for precise tracking of the particle, and a tungsten converter for pair production. The next detector is the BGO calorimeter, in which we measure the energy of the incoming particle, and we are also able to separate electromagnetic showers from hadronic shower. At the very bottom, then there is the neutron detector used to make an additional hadrons rejection. Okay, here there are some event displays just to show you better how do we separate these particles. From the top, again, we have the plastic scintillator detector, then the STK, BGO, and NUD. In case of protons and the electrons, you can see that we have a signal in the PSD, in the scintillator, while for gammas, there is no signal in the PSD. And this is a good way to discriminate electrons from gammas. Then in the STK, we track the particle. And then in the BGO calorimeter, you can see the difference in showers for an electromagnetic one induced by protons that is broad and deep, and an electromagnetic one induced by electrons and gammas that is more well contained. And finally, there is the last detector, the neutron detector, in which there is a signal in the case of protons and no signal for electrons. Okay, so we said the dark matter particle explorer, so we look for dark matter. There are, as you know, many dark matter candidates. If the dark matter is a particle, there is the so-called WIMP hypothesis, in which we expect that two WIMPs could annihilate into a photon and another particle. And this, if this is happening, we should be able to see a monochromatic structure at a specific energy of the photon that will then give us information on the mass of this dark matter particle. Just as a reminder, the dump energy resolution for photons is around 1%. Here you see preliminary results with 5 years of data collected by DAMP in the energy range from 5 till 450 GeV. This plot is the average spectral energy distribution, so-called SED, and in this case, there is no obvious line-like structure. For this reason, we decided to perform another test, searching for signals in different region of interests that you see here, considering different dark matter profiles. And the last one is the galactic plane. And after that, we do test statistics, looking for a value of these test statistics larger than 9. But we didn't find any of these, so there is no line signals with these 5 years of DAMP data. What we could do anyway is to put some constraints on the annihilation cross-section and the decay lifetime for dark matter. The first plot is the annihilation cross-section. In red, you see the results of DAMP with included statistical and systematics uncertainties, and the dotted line is only statistical, compared with the Fermilat in blue. And you can see in this case that the DAMP 5-year results are comparable with the 5.8-year results of Fermilat. The second plot is the low limit for the decay in dark matter for the decay lifetime. And in this case, the DAMP lower limits are stronger for dark matter with mass lower than 100 GeV. We also look at the gamma ray sources. So we collected more than 220,000 photons above 2 GeV in 5 years of data that allowed us to build this map. and also to identify some sources that you can see here. So with these 5 years, we identified a total of 222 sources, in which the majority of these sources is AGN. Okay, now we go to electrons. You saw how to distinguish electrons from gammas and from protons. And here I show you some additional details on how to separate electrons and protons, looking at their shower in the calorimeter. Here in this plot, you see this variable F last, that is the ratio of energy deposited in the last VGO layer, so the last layer of the calorimeter, to the total energy deposited in the calorimeter, while on the x-axis there is the shower spread. And you can see that these two families of particles are very well separated, so protons and electrons. Then combining these two variables, we use these other variables, zeta, to obtain this peak of electrons that you see in this shaded area. And it is very well separated from the protons that are here in this other region. Here in this plot, there are both Monte Carlo data and flight data, and you can appreciate the good agreement between these two. Okay, after identifying electrons, we published this spectrum on Nature in 2017. The spectrum is in the energy range from 25 GeV till 4.6 TeV, with 530 days of dumped data. The proton contamination estimated was lower than 3%. And the importance of this publication is that we found an evidence of a break at around 1 TeV in the proton spectrum that you can see here, well fitted with smoothly broken power law. Okay, now we go to nuclei. We saw again how to identify protons, but there are of course heavier nuclei that we want to measure, and we separate these different nuclei in the plastic scintillator detector in the PSD using the Bede-Bloch formula. You know that using this formula, the energy released per unit of path length is proportional to the charge squared of the particle. And in this way, we can build this charge spectrum that you see here, in which there are hydrogen, helium, lithium, and all the nuclei peaks well separated. The charge resolution was estimated to be very low, from 0.12 for helium up to 0.32 for iron. And an additional charge measurement can be also done using the STK and with the lower precision by BGO bars. Here, just to show you this discrimination that we can do between different nuclei, you can see a preliminary boron over carbon flux ratio, in which the red points are the damper results, and that is in good agreement with our other experiments. Okay, the most abundant nucleus is hydrogen. So the first result for this nuclei was the proton spectrum. In the first row, you see the peak of energy released in the PSD. This is actually the charge. And this is taken for different energy deposited in the BGO. And you can, as you can see, there is a different behavior when the energy is increasing. So we study this charge. We study also the contamination from other nuclei like helium, and the contamination from electrons. This contamination is very low at low energy, and it increases at higher energy only for helium. Then, in order to go from the number of events to the final energy spectrum, we also calculate the effective acceptance that you see here. And of course, we estimate all the systematic uncertainties, in which you see here all the contributions. And the most important one is the one on the hadronic model. Finally, we published this proton spectrum on Science Advances in 2019, in which we confirmed the hardening structure at around 500 GeV, and we also detect a softening structure at around 14 TeV with very high significance. Going to the next abundant nucleus, we have helium. These are the same plots that you saw before, but in this case for helium. So the contamination is here only from protons. And we published also recently this spectrum on physical review letters. In this case, we again see the hardening, but the important point is that we detect the softening in the helium spectrum for the first time at around 34 TeV. And if we compare this with the proton result, this is suggesting a charge-dependent feature, even though mass dependence cannot be ruled out for the moment. What we are doing now is also to measure a combined proton plus helium spectrum. In this case, we found a good agreement between the combined analysis that suffers very less from contamination and the two independent proton and helium analysis. And also in the proton plus helium spectrum, we saw this hardening and softening. What we want to do with the spectrum is to extend it to higher energy, because in this way we could connect indirect measurements and direct measurements. And in this plot here, you see in blue the damper result, and the other results are from indirect measurements. So here are the conclusions. The dark matter particle explorer was launched in December 2015 and is now taking data very smoothly. We searched for gamma ray lines, and we obtained some constraints on dark matter annihilation cross-section and lower limits on dark matter decay lifetime. We also found around 220 gamma ray sources with 5 years of damper data. And we published this 3D spectrum on electron and positron spectrum, in which we find a break at around 1 TeV, the proton spectrum with the detection of a softening at around 14 TeV, and the helium spectrum with, again, a detection of a softening around 34 TeV. What is going on now is the proton plus helium analysis in order to reach higher energy with respect to previous results and build a bridge between direct and indirect measurements. And also many other analyses are ongoing, including primary and secondary nuclei, and also their ratio, like boron over carbon, boron over oxygen, and so on. Thank you very much.
Thank you, Francesca. This was a very fast talk. You finished even before the time. It's now full of time for questions, almost 9 minutes of questions. So please raise your hands. So maybe I can start asking you one question. Are you going to look for the softening of the spectra that you saw in proton and helium spectra also for heavier nuclei to see if a possible charge-dependent or mass-dependent break is visible, is detectable?
Okay, let's say that that will be the optimal way to understand better if it is charge or mass dependent, but we should be able to reach such a high energy, and with heavier nuclei it's a bit more difficult. So I'm not sure at the moment. I hope so, but I'm not sure at the moment.
And just to continue, is the energy resolution different for different nuclei? when you put together proton and helium, for example, you must have differences maybe in the energy resolution or in the efficiency that you have?
Okay, actually for proton and helium, it's not so different. So what we usually do is to use Monte Carlo. We rely on Monte Carlo data, and at the beginning we try to use 50% proton and 50% helium, and we see what is the result that we get. So we get a smearing matrix that we use for the unfolding, so to go from the number of counts to the final spectrum in this case. Then we try to change this percentage of proton and helium based on other results from other experiments, and we do all the procedure again, and we compute the spectrum again, and what we found is that this difference is negligible in the end. So there is not much difference. If we go then to heavier nuclei, the situation is a bit more different. So for example, we cannot put all the nuclei together to have I mean, probably it will be difficult to have an all particle spectrum, for example.
Thank you. So our audience is quite shy. No questions? Let's wait some time more, but I don't see any. Okay, thank you very much then again.
Thank you.
And we go on with our program. It's now the time for Valerio Formato. He will talk about EMS2, observation of 5' structures in the primary cosmic ray light nuclei fluxes.
Yes. Good morning. Can you hear me?
Yep.
Okay. So you should be able to see my slides now.
Perfect.
Okay. So I will start. So good morning to everybody. My name is Valerio Formato, and I'm speaking on behalf of the AMS02 collaboration about the observation of fine time structures in the primary cosmic ray light nuclei fluxes. So just to recap, if any of you wasn't present by the time that Javier did his overview AMS02 talk a few days ago, AMS is a large acceptance high energy spectrometer for measuring cosmic rays in the GeV to TeV energy range. It's been operating since May of 2011 on board the International Space Station, and quite recently we just had the 10 years birthday of the experiment a few months ago, some small celebration which were sized down due to COVID, unfortunately, but we plan on having something a little bit more entertaining later on in the year. And so far, the experiment has recorded more than 180 billion cosmic ray triggers in these last 10 years of operation. And we expect to be able to continue data taking for as long as the International Space Station is alive. So at the moment, this is foreseen for at least 2028. So we're talking mainly about primary cosmic rays, and so to make clear what we're talking about, these are all cosmic rays that are able to reach the solar system for detection without ever interacting with the interstellar medium, which is a low density, mainly hydrogen and helium gas that permeates the whole galaxy. So if this kind of possible interaction that cosmic rays can have with this interstellar medium when traveling through the galaxy and following the galactic magnetic field never happen, we dub them as a primary cosmic rays as opposed to secondaries, which are the ones that are then produced in these kind of interactions and re-injected in the galaxy for further propagation. So some examples of primaries are, of course, proton, helium, and carbon, oxygen, and iron nuclei, as well as the main part of electrons in the galaxy. And we are mainly in this case studying the time evolution of this population in cosmic rays, because this is tied very closely to what happens in our solar system. We expect, because of the solar wind and the emanation of the interplanetary magnetic field throughout the solar system, that we will be able to see large time scale effects due to the change of intensity of these effects. So this will affect in turn the intensity of cosmic rays in a time-dependent fashion. And it will affect also differently whether we are in a maximum of the solar cycle, which is a periodic phase change of the intensity of the solar magnetic field and polarity of the magnetic field every 11 to 22 years. So basically every 11 years, the polarity of the magnetic field flips over and the intensity will go from a minimum to maximum. And so every 22 years, you get back to the same exact configuration you had before. And we also expect to see small time effects on a matter of a few days, which are related to perturbation in the heliosphere due to eruptive events on the sun due to explosions of coronal mass ejection and solar energetic particle events and all the effects that are related to this kind of happenings. So briefly, how do we measure cosmic rays? So AMS is a kind of a slice of your average particle detector at the colliders. So you have a tracking system here in the center made of silicon microstrip detectors, which are embedded in a magnetic field provided by a permanent magnet. So we're able to see particles bend the trajectory within the magnetic field, and by measuring this trajectory, we can measure their momentum. And also via measuring the ionization, we can also measure the charge. Then on top and below of this inner tracker part, we have a time-of-flight system made of plastic scintillators to give the trigger to the apparatus and to measure the velocity of particles and also knowing if they're coming from below or above. And this is complemented for what we are mostly concerned in this talk by other two silicon microstrip detector layers, one at the very top of the detector and one at the very bottom, which are used to further extend the energy range. Then for other kind of measurements, which are not covered in this talk, we also have a transition radiation detector and an electromagnetic calorimeter to study leptons, and a ring imaging Cherenkov detector to further measure with higher precision the velocity of particles. What is very important is that we have a very high redundancy of measurements both in terms of the momentum measurement or energy measurement and of the charge of the particles. And we use all this redundancy to measure what is called the flux of cosmic rays, which is basically the number of events normalized by the acceptance of the detector, so basically the size and angular exposure, the data taking efficiency, and per unit time, and rigidity in this case, which is the momentum per unit charge. So this redundancy allows us to have very clean sample in the hadronic part of the cosmic ray let's say populations, and be able to separate all the nuclei in the periodic table from hydrogen up to nickel. In this case, you can see the very last peak we have, and it's still very clean and uncontaminated. So this is especially helpful when you're doing this kind of study, because contamination from neighboring charge can be sometimes very hard to estimate if you don't have some other detector besides the one you're mainly using for measuring charge to tell you if you were wrong or not. So the kind of data we are dealing with once we go through the analysis and measure the flux is summarized in this kind of three-dimensional representation, where you have the flux on one axis, the energy or rigidity in this case on some other axis, and then you see the evolution as a function of time. And you can see that there are very complex structures and a long general term which is anti-correlated with the solar activity, as we were imagining a few minutes ago. And basically the trend is very similar between all species, because the underlying transport phenomena is the same. And just to expand and understand a little bit better what will be the conclusions of these studies, I would like to take a little step back and consider how cosmic rays are traveling through the heliosphere. And the way they do this is very similar to the way they travel through the galaxy, with the exception of a few small changes where we have generally a diffusive process as in the galaxy. So we have a diffusion tensor, and then cosmic rays are diffusing against the turbulence and the irregularities of the magnetic field in the galaxy, or in this case, through the heliosphere. And on top of that, we have also convection, because there is this solar wind, this stream of low energy particles coming from the sun and expanding radially outwards toward the termination shock and bow shock. And then, since this wind is constantly pushing against cosmic rays coming through from the galaxy, we also have what are called adiabatic energy losses, because again, this is expanding wind pushing against the, let's say, cosmic ray wind that our solar system encounters while it's traveling through the galaxy. And what we can learn by seeing how different nuclear species are affected by by this process is mainly all inside this K-term, which is the diffusion tensor, which can be separated into a spatial dependent part and a energy dependent part. And since also the velocity of particles takes a role into modulating how the flux changes in time, we can basically use nuclear species with the same charge to mass ratio, since the underlying phenomena are still magnetically driven, to highlight this velocity dependence and study better how this process is happening inside the heliosphere. But also we are able to pinpoint if there is any difference in the spectrum of particles outside the heliosphere, the so-called local interstellar spectrum. So we are also sensitive to the energy distribution of particles outside the solar system, which is actually quite interesting and fascinating. So we can use combination of all these different particles to probe different aspects of the same phenomena. And also keep in mind that the only measurements of cosmic ray fluxes outside the solar system are provided right now only by the Voyager spacecrafts. So they are limited to very low energy, and let's say that above a couple of GeV, there are no direct measurements. And basically, we have several combinations we can leverage in the primary cosmic ray group, let's say. And so if you start with carbon over oxygen, since these have the same charge over mass ratio, they will also have the same velocity at a given rigidity. So we don't expect any time dependence for this, but if there is any, it can only come from the spectral shape difference outside the heliosphere. And the same is kind of true also for helium over carbon or helium over oxygen. And while if we take a look at proton over carbon and proton over oxygen, here we have both effects playing a role. So we only have numerical models we have to leverage numerical models to make a little bit more sense of this phenomena. So that being said, let's take a look at the results. So this is basically a slice of the three-dimensional plot I was showing before, where we have proton, helium, carbon, oxygen fluxes superimposed to basically give an impression that the main impression that the long-term trend is more or less the same. And also you can see that there are some time structures that are present in all the fluxes, and we are able to measure this time dependence up to very high rigidity. Basically, we see these trends up to 25 gigavolts for carbon and oxygen, 50 for helium. And for protons, we are able to see an effect all the way up to 100 GeV, even if the analysis actually is only confined in the 1 to 60 GeV ranges for ease of displaying, let's say. But once we start taking a look at all these ratios, where we actually are a little bit more sensitive to see any time dependence, we start with the carbon over oxygen, and we, for statistics reasons, we have to basically make the measurement every 4 so-called Barter rotations, which are periods of 27 days, which are the kind of the main unit. 27 days is the time it takes to the sun to make a full rotation, even if it doesn't rotate with the same velocity at all latitudes. But basically, this is the first time this is measured with such a precision in such a long time scale, and on a time-dependent fashion. And in this case, we don't see any dependence in the carbon over oxygen flux ratio in the whole energy range from 2 to 60 GeV, which is, again, we will come to the conclusion later, but this is, you can remember what we said a few slides ago about this. We then leverage the fact that carbon over oxygen have the same time dependence and gain a little bit more statistics power by summing the two fluxes and then comparing the sum of the carbon and oxygen flux to the helium. It's a little trick to gain, let's say, 40% more statistical accuracy and a bit more sensitivity to time changes. And in fact, we do see a time dependence, a low rigidity of the helium over carbon plus oxygen ratios. And again, since all these particles have a very similar charge over mass ratio, this means that this is not due to any to the presence of the velocity in the diffusion tensor, but rather due to a difference in the spectrum of helium, carbon, and oxygen outside the heliosphere, above the 2 GeV threshold, where there is no direct measurement, but still we are able to tell that there is a difference due to this time-dependent, the presence of this effect. Whether for a proton over carbon plus oxygen, this flux ratio is also exhibiting time dependence up to 4 GeV, but here you have both effects playing a role in this time dependence. So you need to be able to disentangle them. You need numerical models of the propagation through the heliosphere. But we don't stop at 27 days time bins. Let's say we are able, at least for proton and helium, to go even deeper and measure the fluxes in a shortened time period. And this is helpful because we actually are able to see effects due to the presence of irregularities on the sun surface while it's rotating on itself. I'm mainly talking about the presence of one or more coronal holes on the surface of the sun that can create sub-Barton rotation variations in the flux. And we expect that if there are coronal holes, this perturbation in the solar wind will propagate through the heliosphere and cause a variation in the cosmic ray fluxes with the period which is, let's say, with the harmonics of the base period of the sun rotation, which is 27 days. So we expect something along the lines of 27, 13 and a half, and 9 days periodicities in the proton fluxes. So using the whole data set we have available right now, which is corresponds of 5.5 billion protons, this was also shown by Javier a few days ago, we are able to measure the flux on every day, the proton flux every day along, in this case, nine and a half years, almost 10, which corresponds on roughly 3,000 days, and at different rigidities. And you can see that there are, again, there is a long term, but there are also some fine time structures that that seem to be recurrent on top of this long-term trend. And if you zoom a little bit closer, as an example here in 2016, these repeating structures appear in the proton flux at different rigidities, and they're all very similar. So to study periodic phenomenon, this periodic phenomenon, we perform a wavelet analysis on the proton flux, and we start looking at the power at different frequencies as a function of time. So this is a way of doing, think of it as a fast Fourier transform of the data, but a little bit more complex, and which is able to handle also non-sinusoidal periodicities in your signal. And we indeed see that there is a big spike of power at 27 days, but also we are able to see the two harmonics at half the time period and 1/3 of the time period in here. So and we are also able to study the rigidity evolution of these periodicities and present this data basically to the community, because you can imagine this is a very complex subject to study, and you can easily get outside the scope of a publication. So right now we're working on a publication also with this data, which should be out pretty soon. And we are actually looking forward to get this data on the hands of really expert people in the interaction between the solar wind and the cosmic ray fluxes, because this is a very, very, very complex subject. So we do see that this the strength of this periodicity changes with rigidity, and this is what makes it very, very complicated to study. But indeed, we do see them in the whole rigidity range, at least up to 20 or 30 GeV for the proton flux. So with this, I can now just come to my conclusion, saying that we lately have been studying the time variation in the light nuclei flux in the primary component of cosmic rays. At first, starting with the most abundant species, so proton, helium, and carbon, and studying the long-term variations by looking at the fluxes every Barthes rotation, which I remind you is 27 days. And this kind of study on the long-term time evolution of these fluxes can provide unique information on how the local interstellar spectra and the velocity dependence of the diffusion tensor in the heliosphere play a role into the propagation of cosmic rays in our solar system. We provide the first and only measurement of the time dependence of carbon and oxygen fluxes as a function of rigidity, and as well as well, it's not the first measurement of proton and helium, it's more kind of an update because we had a previous publication a few years ago about this, and we extend this to a few more years of data, and we enhanced the statistics by a factor 5 with respect to the previous publication. But indeed, we see that carbon over oxygen having identical time behavior, indicating a very similar rigidity dependence of their local interstellar spectra above 2 GeV, where again, there's no direct measurements because Voyager is confined to very low energies. We have measured the helium over carbon plus oxygen flux ratio, and we saw a time dependence, which indicates vice versa, that the helium local interstellar spectrum is quite different from the carbon and oxygen one. And the same can be said about the proton over carbon plus oxygen, but here we also have the different velocity at the same rigidity effect playing a role. Then we also present the precision measurement of the proton flux on a daily basis, and we start seeing this recurrent flux variation with periods of 27 days and its harmonics of 30.5 and 9 days, which are very, very, very evident, especially in 2016, whereas in other periods they're still apparent, but not so evident that they can be seen by the naked eye. And we study the strength of these periodicities as they change with both time and rigidity. And that's all.
Thank you very much for this talk. It's a really tricky analysis I have seen.
Yeah, it's quite complex.
Quite complex, yes. So we have time, since our speakers today are very fast and the audience is quiet. So please, questions to Valeria. There is a question from Alexander Zakharov, please.
Okay, thank you very much. I have a question about one of your first pictures. You showed propagation of cosmic rays over our galaxy, but as foreground you used Andromeda galaxy images, seems to me. Yes.
Yes, we don't have.
But in this case, you have to mention that is because otherwise people could think that you took a real image of our galaxy from space. You know.
Oh, I understand. I took it for granted that it is a fact. We don't have images.
It's Andromeda. It's Andromeda.
Should be. Yes, I don't remember.
Okay, good.
I made this slide a long time ago. I don't remember.
Otherwise, it's misleading, you know.
No, you're right. I agree.
So, more comments or questions to Valerio? So let me ask, I'm always curious about the systematic uncertainties. I didn't get it, it was too fast. The strength of the fluctuations that you see. So are they significant with respect to the systematic uncertainties that you have, and which are these systematics and how big they are?
Okay, that's a good question. So the short and immediate answer is yes, they are. Because I didn't have time to go into the details of how we do these measurements. But basically, wherever you see an error bars, this is depicting both the statistical uncertainties and the systematic ones. And we are mainly, at least for proton and helium, still statistically dominant. Systematic dominant, while for carbon and oxygen it will kind of play the same role. And here there is an additional component of systematic uncertainty that you have to take care of with respect to when you do, let's say, the average flux in 10 years. So you just have one flux measurement and you do all your systematics, which are related to your acceptance, your nuclear cross-section corrections, your unfolding procedure to get rid of the resolution effects of your instrument. Here you also need to monitor all the efficiencies of your detector on a time-dependent basis, because rarely detectors are stable in time. Even the best detector is aging, first of all. And for the case of AMS, there's also the environment of the space station, which is always rapidly changing, because the exposure to the sun, let's say, changes quite rapidly along the orbit, which is only 90 minutes. So you can imagine that the temperature at which the detector is operating changes a lot during several orbits. And this can affect the performance of the detector in a time-dependent fashion. So we also have to keep track of all this. Of course, we do our best to get rid of all these temporal dependencies in the reconstruction, in the performance of the detector, but some trends are still visible that we need to track them and appropriately correct them. Otherwise, you will see time trends which are not real, are due to the detector and not to the physics. So this introduces an additional term of systematic uncertainty with respect to the major publication we had so far, but it's still at the level of 3 to 4%. So the overall systematic uncertainty of on this measurement. So we keep our target of a few percent systematic uncertainty goal in all the measurements.
I see. Thanks. Thank you very much. So more questions. We have still a couple of minutes. Alexander, you have another question, or you just forgot your hand up?
Sorry, I forgot.
Okay.
Sorry, thank you. Sorry, I apologize.
So just to finish, out of curiosity, do you are there other experiments to which you can compare in which they see the same time variation?
Unfortunately not, because Pamela stopped taking data a few years ago, and they only published proton and helium time dependence. So in a sense, yes, there's only basically Pamela data in the and it covers the first, let's say, half of our time span. But speaking about these nuclei flux ratios, the only other experiment that is, as far as I'm aware, currently taking this kind of data is ACRIS, but the energy range unfortunately doesn't overlap with us. So they barely touch. Let's say we start from 2 GeV and they are a few hundred MeVs lower than our lower threshold. So unfortunately, there's no way of directly comparing this data.
I see. Thanks a lot. Okay, so if there are no more questions, let's thank Valerio again. And we go to the second to the last talk, which is Dr. Shin from Tokyo, recent results from the telescope array. Please.
Hello, do you hear me?
Yes.
Okay, then I'll share my screen. Okay, now can you see my slides?
Yes, perfect. Yes, you can.
Okay, then now I begin. Hello, this is Hung-Soo Shin from ICRL, University of Tokyo. I'm going to make a presentation with the title of Recent Results from the Telescope Array Experiment. The outline of this presentation is like this. First off, the telescope array experiment and its expansion. The name is TA times 4 will be introduced briefly first, and then I will introduce about the recent results from the spectrum measurements. And next, the composition study results will be introduced, and then the anisotropy results will follow. And recently, TA has been working on several interdisciplinary studies, so I will introduce about them, then I will summarize. The telescope array experiment is joint efforts of 160 members affiliated with 35 institutes across the 7 countries in the world, USA, Japan, South Korea, Russia, Belgium, Czech, and Slovakia. The telescope array experiment holds the largest ultra-high energy cosmic ray observatory in the Northern Hemisphere. It is located in the Millard County, the Utah State in USA. The figure here shows the map of USA and satellite photo of the TA observatory. And the science goals of the telescope array experiment is to shed light on the origin and properties of ultra-high energy cosmic rays, and also studying on high energy hadron interactions and the multi-messenger studies with photons, neutrino, and dark matter to study high energy astronomic phenomena, and also interdisciplinary studies with earth science is now becoming interesting topics in the experiment with thunderstorm, TGF, and meteoroids. The telescope array experiment consists of 2 types of detectors, which is surface detectors and fluorescence detectors. Surface detector array has 507 scintillation detectors with 1.2 kilometer spacing, covering around 700 square kilometers. The fluorescence detectors are built to surround the surface detector array. There are 3 detector stations for fluorescence telescopes, each station consists of 12 to 14 telescopes. And from north to clockwise, the station is named the Middle Drum and Black Log Mesa and Long Ridge. And also to monitor the atmospheric condition, the vertical UV laser instrument is installed in the middle of the surface detector array, which is called central laser facility. The tail is a lower energy extension part of TA experiment, with fluorescence telescopes seeing high elevation angle of 30 degree to 57 degree and more densely deployed SD array. Tail aims to observe the lower energy air shower than the conventional TA instrument can see. So they also consist of both FD and SD. Tail FD is built near to the middle drum station of TA FD, as can be shown in this photo. The upper figure shows the field of view of TA FD and tail FD, and you can see the tail is seeing the way higher elevation angles. And the tail SD array consists of 80 scintillation detectors, and which is the instrument is exactly the same to the TASD. And the spacing is different from TASD, that the spacing is 400 meter to 600 meters, which can be compared to the 1.2 kilometers of conventional TASD. So with these 2 types of detectors, they also can conduct a hybrid observation of air shower with these settings. And TA times 4 is the most recent upgrade of TA experiment. The final target of this upgrade is to increase the coverage of TASD array by 4 times which is roughly equivalent to the 3,000 square kilometers of area. 2 additional FT stations for hybrid observation will be they are already constructed, and the observation of TA 4 times instruments started from 2019. So now I want to introduce about the spectrum measurement results by the TA experiment. The figure shows the spectrum measurement by TASD with 11 years of observation data from 10 to the 80th electron volt and the 10 to the 20.5 electron volt energy range. The spectrum could be fed with broken power law fit that shows the anchor and the cutoff features. The cutoff features. So anchors around the 10 to the 18.69 and the cutoffs around 10 to the 19.81. So TA combined spectrum is shown in this slide. The black sphere shows the spectrum result from TASD 11 years data plus tail monocular observation data of 22 months. With the tail and TA combined, the experiment can measure the energy spectrum that accrues to 5 decades of cosmic ray energy from 10 to the 15.5 electron volt to the 10 to the 20.5 electron volt. The recent spectrum measurement result from Pierosa Observatory, which is another UHCR experiment located in the southern hemisphere, reported a new feature in the UHCR spectrum between anchor and cutoff. The new feature is the spectrum hardening in the 10 to the 19 electron volt and 10 to the 9.5 electron volt, and they are called instep with analogy with the shape of human foot, like this. TA and with TA telescope array experiment with combining TASD, TAFT, and high-res data also observed the instep feature at the 10 to the 19.25 electron volt with 5.3 sigma of significance. The upper left figure shows instep feature reported by Pierosa Observatory. You can see the hardening around here. And the lower figure shows the TA spectrum measurement results. The first one is the TASD, and then the TAFT and the high-res. With these data, spectral index and the position of spectral features are estimated. The result between TA and Pierosa is compared in the upper right figure here. TA experiment and Pierosa Observatory has long been working with the joint spectrum because there is difference in instruments and seeing different skies and different analysis method. So with a common observable declination band, the working group's result is that the working group's result is showing that the absolute energy scale difference between TA and OJER is about 9%, with a plus minus 10% of energy dependent shift. So this is the first result from the TA times 4 SD, which is the spectrum measurement data with 1 year observation data. The preliminary result shows that the TASD spectrum indicated in green markers, and the new the TA times 4 spectrum indicated in black triangles. So they show these two results between TASD and TA times 4 SD are inconsistency. The next result from TA experiment is about composition study. The left figure shows the mean Xmax measured by tail FT's monocular observation mode, indicated in black squares, and TA hybrid Xmax result is in red squares. You can see the tail Xmax and TA hybrid Xmax result is smoothly connected around the 10 to the 80.3 around here. And the tail monocular Xmax result can be fit with a broken light fit, and that indicates the breakpoint around the 10 to the 70.2 electron volt. In the light figure, the primary particle fraction and log A of the primary particles have been estimated with tail data. So X-max measurement with the hybrid mode is also done for tail and TA detectors. The alpha figure shows tail hybrid X-max measurement results, also shows a breakpoint with a broken light fit. Here, the 10 to the 17.07 around here. And for the lower figure shows the TA hybrid trigger measurement result. Most of them showing the measurement result is compatible with the light composition above 10 to the 18th electron volt region. The composition study with the PASD data has been progressing recently with a machine learning method based on BDT. With 16 compositionally sensitive observables and 12 years of TASD observation data, the composition study result is shown in the figures here. And for TA, above 10 to the 18th electron volt, the result is compatible with the light composition also. And the other result shows that the composition is getting heavier with the energy increases. Another neural network study with PASD data is classifying photon-induced shower. With the energy above the 10 to the 19th electron volt, the PASD data show almost identical to the proton Monte Carlo. With observation data, the new gamma ray flux limit could be set, and they are shown in the light figure here. Also, a hadroning interaction study is done with the measurement of proton and air cross-section. This is done by measuring X-max attenuation lengths in hybrid mode of telescope array experiment. It is estimated that cross-section and the result is shown in the light figure in the big lead circle marked around here. And recently, TA has been working on several kinds of anisotropy study. The first one is dipole study, which is also reported by Pierre Oze Observatory. In TA, with the energy threshold of 8.8 electron volt, it is searched that the dipole by estimating residual intensity between data and isotropic distribution. This uses 12 years of TASD data, and the study showed that the amplitude for dipole is 3.1%, which can be compared to the OJ result that is 4.7%. Another anisotropy study is about hotspot, which is originally reported by TA in 2014, with an energy threshold of 57 electron volt. TA reported the hotspot around the constellation Ursa Major. And now with 11 years of SD data, the post-trial significance is estimated by 3.2 sigma. The event growth rate inside the hotspot is consistent within the 1 sigma when linear growth is assumed, when the isotropic increases indicated here. And the other anisotropy study is about the medium scale. There is a hint of excess in the direction of Perseus supercluster with a post-trial significance of 3.6 sigma. The various energy threshold has been tested for this study from 10 to the 19.4 and 19.5, 19.6, and the maximum significance indicates the Perseus cluster here. And this is the light figure shows the zoom of the corresponding region. The interesting disciplinary study comes from the observation of terrestrial gamma ray flash with TASD. With a broadband interferometer and fast atmospheric sensor installed in the TA experiment site, it is able to measure the lightning quantitatively and with precise timestamp. You can see the TASD signals corresponding the other signals measured by the other instruments here. Another interdisciplinary study is about thunderstorm. It has been measured that the TASD's level 0 trigger rate. Level 0 means the lowest level of trigger for TASD. The kind of trigger rate is changing during the thunderstorm is happening within the site of telescopic array experiment. The increase or deficit like this, the blue region is showing the deficit of trigger rate, and the red region is showing the increase of trigger rate. And that depends on the electric field type of thunderstorms. It is estimated the difference in deficit and increases depending on the type of electric field. And the next upgrade plan for TA experiment is the tail infill project. By deploying SD array that is more dense than the current tail SD array, we aim to shed light on physics of PUV cosmic ray with the same instrument the tail and TA has. The spacing is considered 100 meter and 200 meters, covering 0.8 square kilometer of area. So the summary is that the energy spectrum measured for 5 decades and 10 to the 15.5 to 10 to the 20.5 electron volt. And the new feature instead in the energy spectrum is found at the 10 to the 19.3 electron volt. The tail energy spectrum indicated that the second knee may be resulted from the Peter cycle. And tail Xmax shows the composition becoming heavier between knee and second knee. And TA hybrid data is compatible with the predominantly light elements between the energy region of 10 to the 18th electron volt and 10 to the 91 electron volt. And there are indications of anisotropy at the highest energy. The hotspot from it means 11, not 12, yields of data in the direction of Ursa Major, and the post-trial significance with a post-trial significance of 3.2 sigma. And there is a hint of excess in the direction of Perseus. This is supercluster at around the energy above 10 to the 19.3 electron volt. And most importantly, TA times 4 started operation and preliminary energy spectrum is measured. So we can measure more high energy shower, which is very promising. And there is more expansion plan that is a tail infill for the lowest energy of cosmic ray shower, which is around the PeV, and it's ongoing. That's all for my talk. Thank you very much.
Thank you very much for the interesting talk. And we have time now for discussion. Please raise your hands for questions or comments. Of course, I can pose many questions myself, since we work together in the ultra energy field. Let me just ask, for example, just curiosity, how many stations of TA times 4 are already operating? And when do you think you can complete the full number of stations that you foresee for TA times 4?
Yes, very important question for TA times 4. Well, currently the two FT stations for TA times 4 are working now, but for TA-ST, you can see that the large LED squares here and the small squares here. I mean the circles, the LED circles and small circles here. The only large circles area we deploy the STs. So currently we are the effective area for the observation is 2.5 times than the conventional TA. And actually, under this COVID crisis, we cannot send the Japanese personnel to the construction site. So when we are allowed to travel to Utah and of course get the more budget for the more deployment, we can proceed to make it really fourfold effective area. That is by deploying the STs for this small circle region.
Yeah, we all have the same problem about the new deployment. Yes, you're right.
Yes, I really want to go to Utah. I missed it.
Yes. So, questions from the audience? No questions. So I will ask one thing more about slide 14, I think. If you can go to slide 14, this is the usual question about composition. If I look at the TA hybrid trigger, I see that there is a clear break at 18.3 or so. So have you compared a linear fit going to protons, as you say you are compatible to up to the highest energy, with a fit with a broken power law, and see which is the best fit? Because I see a clear break here. And of course, you know very well that in our common working group on composition, it was shown that the telescope array, at least before TA times 4, cannot distinguish between a pure proton and a mixed composition, at least up to 10 to the 19. This would be a very important question also for hadronic interactions, because it would change the contamination in the cross-section. So can you comment about this?
Yes, in TA hybrid trigger measurement, there is clearly the change of slope around 80.2 or 3 or around this region. And actually the characteristics of TA hybrid trigger measurement is that above the energy region of 18.5, it is the trigger is competing with a conventional TA-ST, so we have very small number of actual events. So with the TA hybrid trigger, it is hard to get enough statistics, even statistics above this kind of height, above the 80.7 and 8 region. So we need more statistics to see around here, and then actually there is more data set for hybrid trigger measurement, but it is the analysis still ongoing. So maybe we can show the more, robust version of hybrid trigger analysis soon.
Okay, thank you very much. I think that if there are no more questions, we can thank our speaker again and go to the last talk by Anatoly. Hi, Anatoly, how are you?
Okay.
This is muon puzzle in cosmic rays, please. Can you share your screen?
Okay. I open my presentation, but it's not.
There is a share screen button which you can use.
There is a green button in Zoom program with the sharing screen, демонстрация экрана.
Yes, I put demonstration and I see my presentation, but not. Oh, okay. Okay, much better.
Yes.
Just a minute.
Maybe you can go to full screen so it's better visible.
Oh, okay. Okay.
Perfect.
Good morning, dear colleagues. Buongiorno, dear Antonella. And my talk about muon puzzle in cosmic rays. Listen me, okay?
Yes, we can hear very well.
Okay. My talk will be about muon puzzle in cosmic rays. Now, historically, the words muon and puzzle were synonyms beginning from muon discovery. I remember these puzzles. What is muon if it is not a quantum or strong interaction? The first puzzle. What is difference between muon and electron except the mass? The second. Then does exist anomalous interaction of muon compared to electron? And do exist so-called prompt muons, etc. Now, muon puzzle is growing with energy excess of muon bundles or groups muons in extensive showers generated by cosmic rays of very high energies, more than 10 to 15 eV. Of course, appear question, excess compared to what? Answer is very simple, compared to simulation. This is scheme of extensive showers development. Primary particle interact with nucleus of atom of atmosphere and generated many secondary particles. These particles interact in their turn, and we have large extensive air shower. Size can be a kilometer and more. The scheme of simulation is very simple, but there are three unknown functions: energy spectrum, composition, and interaction model. These functions are known at very high energies. Taking into account some models of these three functions, we can calculate extensive air showers and get values which we can measure with our shower arrays. This is a scheme of ideal extensive shower array. Most part, this is scintillation or Cherenkov water counters for electron, more exactly charged particles detection, some central part for hadron or tracking detector, and practically all arrays have muon detectors on the ground or sometimes deep underground. Additionally, we can detect fluorescent detection, fluorescent light, and Cherenkov light, which can give us profile of extensive air showers. Though all extensive air showers array have muon detectors, various type counters or scintillation detectors, the problem of measuring muon bundles is not so simple. Counters can measure density of muon in groups if average distance between muons is larger than the sizes of counter. In the opposite case, we can get less number than real muons number. Scintillation detector measures the initiation loss of muons, but cannot separate contribution of other particles, delta electrons, for example, small cascade showers generated by muons, etc. For correct measurements of the number of muons or muon density, the detectors with very good spatial resolution are required. Therefore, the first reliable results above excess of muons were obtained in CERN and lab detectors, Aleph, Delphi, and L3. This is well-known detectors. They have very good muon detectors with good resolution. This is sample of detection muon groups in cosmic rays. Usually very short run for cosmic rays, but the results are very impressive. This you can see a result of Aleph and Delphi. You can see some excess of muons around multiplicity about 100 muons. This large excess, this Delphi not so large. And comparison with calculation shows this is proton composition, this is iron composition near. More impressive results were obtained in ALICE. You can see this is more big detector and can detect up to 300 muons. They obtained the distribution of muon bundles which we can weight from simulation. This part is another scale, but 5 events were with very large multiplicity, which don't describe modern models. What is difference between muon bundles detected in accelerated and cosmic ray experiments? In experiments with accelerated detectors, the energy of primary cosmic rays, which generate muon bundles, is not evaluated. It cannot be evaluated. In cosmic ray experiment, the energy of primary particles is evaluated, not measured, is evaluated by using the result of detection of different components of extensive wave showers. Therefore, in this experiment, in cosmic ray experiment, it is possible to investigate the dependence of muon bundle excess on energy of primary particles. But exists of problem muon data comparison. Though the term muon puzzle was introduced in 2014, it was difficult to compare results of different experiments in which muon excess was observed for the following reasons. Firstly, different measured values, number of muons, multiplicity, muon density, different interval of energies and zenith angles, different models in comparison with prediction of which muon excess was determined, and different cosmic ray energy spectrum and composition which were used in simulations. Sorry. Some revolution was in 2018. In August month during TEFPA conference in Berlin, Hans Dembinski organized the international working group and proposed a very simple method for comparison of different experimental results by using the parameter Z. This is a very simple solution. This is number, experimental number. It can be number of muon, multiplicity, density. This is the same values, but in simulation, calculated for few protons, few protons and few iron. And you can see that if experimental data are near proton composition, that will be equal to 0. If this be iron composition, near iron composition, that will be equal 1. And this group summarize result of 10 experiments. This is paper, this picture from paper which was presented conference Hacker 2018. And these 10 experiments, results of which are presented here. You can see the most part results give some growing behavior of these muon bundles. This is 6 identical pictures for different models. You can see that some models can move the result a little left or right, down or up. No, the picture in the whole is the same. Most impressive results were obtained in 3 experiments, and black ice cube, brown Neo decor, and red Pierre Auger experiment. This is 3 results shown here. The interval of ice cube 10 to 15, 10 to 17, ice cube, the Pierre Auger give small but very high energy interval of energy, and Neo decor gives the record energy interval for orders. The comparison of this detector shows that the area of ice cube is 1 square kilometer, Pierre Auger 3,000 square kilometer. Size of Neo decor experiment is about 100 meters square. But our results were obtained earlier than Pierre Auger and ice cube. What is it? What is it? How is it possible? This is Neo decor experiment. This building, the main feature of our experiment is that our coordinate tracking detector placed vertically, not horizontally, vertically. And there's a good condition for detection inclined showers, inclined muons up to horizon. We used technical local muon density spectra for description of our results. Very interesting situation. Since we at large zenith angles, size of shower can reach several kilometers, tens kilometers. The effective collection will depend not will determine not the size of detector, but size of extensive shower. You can see result of simulation. This is without Earth's magnetic field and with taking into account. So you can see that this is 1 square kilometer, this is 10 square kilometer. This subtitles allows us to measure very wide energy interval. This is samples of real events. This is 9 muons. This is direction correspond 90 degrees, zenith angle 90 degrees horizontally. This is this azimuthal distribution, azimuthal angle. You can see 9 muons, and it's 78 degrees. You can calculate this, you can calculate this particles your own finger, 9 particles. This is the record muon bundles event, which detected at 90 degrees. We calculated 132 muons, but this is maybe possible some mistake. What is interesting thing? If to fix muon density, for example, this is 0.2 muon per square meter, in total about 15 muons in our detector, and change zenith angle, the distribution of primary particles which are responsible for these muon groups will move right and reach 10 to 19 at large zenith angles. Now, how explain the excess of muons? In principle, are possible two approaches for analysis measured muon component. The cosmophysical approach and nuclear physical approach. In the first, energy spectrum and composition known, interaction model known. Nuclear physics opposite situation, energy spectrum and composition known, but interaction model unknown. As a result, we will search primary cosmic ray parameters for an interaction model. Now, how to do choice between the two approaches? The only one extensive shower parameter exists which can give answer to these questions. This question. This is energy of muons. If the excess of muons is caused by the appearance of primary cosmic rays heavy nuclei, for example, uranium, or changes energy spectrum or other cosmological things, spectrum of muons should practically not changes, practically the same. If the excess of muons is related with inclusion of new process, of new state of matter, of muon generation, at energies above some threshold, then such muons should have higher energies. this is depend on threshold. And to measure energy characteristic of muon bundles, two independent detectors are required. One for registration of the number of muons and other for the energy deposit measurements. Currently, the Neva Decor complex is the only facility in the world on which such experiment can be carried out, since two independent detectors exist. The core coordinate tracking detector can measure number of muons, and Neva Cherenkov water calorimeter can measure energy deposit of muon bundles. This picture illustrates the situation. We don't know what energies can begin new physical processes. Maybe this is some wide interval, but about 10, 17 or higher, these new processes must be appeared if muon excess is connected with changes of modal interaction. Now this experiment is existing now. I can show you some preliminary data. This is dependence muon density energy deposit in the ratio muon deposit to the number of muons. Practically, this is energy deposit for 1 muon. This value, of course, increased with zenith angle, since energy spectrum muons with increasing of zenith angle will be more hard, and this is calculation for various. This point corresponds some effective energies. More interesting dependence of muon density. You can see our experimental points, and this is evaluation of primary energies. This is not so large zenith angles, only this interval, but we have some excess of muon energy, which can evident that in a favor of change interaction model. And since our detector Decor has some drawbacks, he not cover full site of Cherenkov water detector, and has not so good special sensitivity. Now we construct a new detector named Track. This coordinate tracking detector from drift chambers, and the purpose of this new detector is increase the sizes of the tracking detector, improve the accuracy. We will use drift chamber with large volume, 4 meters long and 1/2 meter width, and 12 centimeter deep. This large drift chamber has only 4 wire, but has a resolution 1 millimeter. Total area will be 20 250 meters square, resolution 1 millimeter, which allows separate two particle tracks at distance of 3 millimeter. Now we have 3 centimeter, 10 times better than existing. It's a very interesting event, and we invite all interesting people to participate in this experiment. Now, my conclusion. Muon puzzle was formulated on the base of results obtained in different experiments with accelerator and cosmic ray detectors. With a high probability for the appearance of the excess of muon bundles, new processes in nucleus-nucleus interaction are responsible, since cosmic rays consist mainly of nuclei which interact with nuclei. If this idea is correct, it can be investigated at LHC in detail, but it is necessary to search for new state of matter at LHC, not in proton-proton interaction, but in nucleus-nucleus interaction. Of course, this task is not so simple, since in our case, if, for example, heavy particles decay into muon, we will have very large energy, about 10 TeV or maybe 100 TeV. In LHC, these muons will have energy about 40 GeV, since it's a very complex task. In cosmic rays, this idea will be investigated in neo-decor track experiment. Thank you very much for your attention.
Thank you, Anatoly. We have just 1 minute. If there is an urgent question, we can take it, please.
I have one question.
Yes, please.
Suppose that we believe that the number of muons which arrive to the Earth is different from what we expect. And muons are known to be associated with the muon neutrinos. So it will result in the fact that the number of muon neutrinos should be also different. And it means that the it means that the picture of oscillations of atmospheric neutrinos should be somehow modified. So what do you think about it?
You are right. You are right. If the investigation of very high energy muons is a very good test for the astrophysical neutrinos. If muons very high energies can generate it in atmosphere, that neutrino will generate it in atmosphere also. Therefore, it is a very interesting thing. But for that required measure directly muon energy spectrum in the atmosphere. Is not a very simple task, since such muons come with many other muons, and separate. We have no methods for energy measurement, exclude cascade showers and pay meter technique by using electron-positron small cascade showers. Of course, this is problem are connected very close, and this problem interested not only muon but neutrino also. Thank you.
So, do you expect that there is not so much contribution of this problem to the modification of atmospheric mixing angle, for example?
No, no, of course.
I'm sorry, maybe you can discuss this offline, because we are already outside our timing, and we are going to be late. I would just like to urge all the interested people also to to have a look at the review that Hans Dembinski made at the last ICRC, where different possibilities to explain this, I would say, deficit in models and not excess, because data are data. So it would be interesting also to have a look at that for different alternatives. So I'm sorry to stop the discussion here, but let me thank all the speakers once again and leave floor to the organizers. Thank you very much.
Well, thank you very much. I would like to thank all the speakers of this session, and I highly appreciate very important contribution Antonella Castellina has provided for the 20th Lomonosov conference, being the speaker and also the chairperson at the plenary sessions. Well, thank you very much, and we shall meet just according to our schedule at 10:50. See you very soon. Thank you very much.
Александр Иванович, это Михаил говорит, Фильченков. Нельзя перенести мой доклад на завтра? Я вам прислал письмо.
Ну, думаю, что нет, потому что там все уже забито. Там у нас пленарные доклады до вечера.
Нет, ну не пленарные, куда-нибудь, хотя бы 10 минут.
Ну, давайте мы приватно с вами поговорим.
Нет, а как мы поговорим? Я с вами не могу связаться, мне не мобильного.
Напишите на почту мне, пожалуйста. Сейчас перерыв у нас.
Хорошо, я вам написал уже.
So, hello. So I would like to welcome all participants and Grigory Rubtsov, who will chair this session. And I would like to ask everybody to follow the prescription or just a way how the previous session was organized and try to follow exactly the time of each presentation. And this is the duty of the speaker, just to leave some minutes inside the given time for discussions. Well, thank you very much, and please, Professor Rubtsov, start your job. Thank you.
Pleasure to see all of you at the plenary session of Lomonosov conference. And I am pleased to welcome the first speaker, Nikolai Farnenko from University of Torino, overview of particle dark matter searches through cross-correlation. Please, 25 minutes.
Thank you. Thank you very much. Thank you very much also for the opportunity to give this presentation here. I hope that you can see my slides. So I'm going to talk about a topic which is maybe not very well known to all of you, about a way to look for particle dark matter through a technique which is called cross-correlation. So we'll first go through motivations while using this technique, and then show some results that have been obtained in the last 3-4 years on this topic. I will leave you also a list of references at the end, most of our work, but there are also other good works. So this is the starting point. We all know this, dark matter evidence is actually overwhelming, but it's only gravitational from the point of view of gravity. There are a long list of ways to know that there is dark matter in the universe, but all of this information comes from gravity probes. A common interpretation of dark matter is that dark matter is a new particle. However, if it is a new particle, we would like to see a non-gravitational signal, which is due to its particle physics nature. And we can look in many places in the universe. Everywhere there is dark matter, we can look for a signal. This is just the list of what actually is exploited and can be even more exploited on what will I tell you in a moment. So we can look inside our galaxy, signal from our galaxy. A very nice place to look at are satellite galaxies of the Milky Way, the dwarf galaxies, because they are believed to be dark matter dominated more than other systems, or even galaxy clusters. They are far apart, but they're very big. And they, moreover, like our galaxy, they have different level of components, or at least this is what is expected from a smooth component, subcomponents, and so on. In principle, we could even look at the full cosmic web. So the distribution of dark matter, which even if it is at a low contrast than clusters or galaxies, in principle, it's there. Even voids, I will not talk about that today, but that is also an interesting counterpart to look at. We have a lot of options, many types of signals. This section is mostly devoted to direct detection. I will not talk about direct detection, but I will talk about indirect detection mostly in the photon channel. All these are probing different structures in the universe, different places. Direct detection probes the local dark matter in the universe, while charged cosmic rays, neutrinos, and photons can probe our own galaxies, but neutral probes can probe also the extragalactic environment. I'm talking about gamma rays, but also X-rays, radio emission. Any type of dark matter can emit typically photons at some level, and even heavy dark matter can produce radio, but I will stick to gamma rays to be definite, even though what I will say later on can be applied also to the other neutral messengers. The main point is that even though we have a lot of options, dark matter signals are typically very, very faint when we compare them to the backgrounds or foregrounds, are typically called sometimes in astrophysics. So the question is, can we do can we exploit some additional information which is actually encoded in what we receive from the message in the sky to look more deeply to that? I will take as a exercise the gamma ray, and this is just an example of the Fermi-Lat map, where we see above some energy, I think it's 1 GeV here, what we see in the sky. And we see the very bright emission of the galactic plane. We see individual point-like sources, which are very likely astrophysical sources. And then the dark matter signal is very likely hidden somewhere in this diffuse gamma ray background, the blue points. We also have some hint of potential signal at the center of a galaxy, but it's a very complicated place because it's we are in the plane, we are integrating everything on the plane, the galactic center is complicated. So this is what I was saying, the background is overwhelming, no? And therefore, can we exploit something more? From the gamma ray sky, the typical way of looking at what is coming from outside our galaxy is once you remove the galactic foreground, once you remove or mask point-like emission, you are left with some diffuse gamma ray intensity, typically called isotropic background, which is sort of well reproduced by astrophysical sources. Star-forming galaxies, blazar, missile energy, and millisecond pulsars even, but mostly something which is unresolved. What I'm talking about here is something that is not so bright to be identified, but contributes to a diffuse background. Dark matter can contribute too, of course. This is the place where the dark matter signal is likely hidden, because at the moment we don't have any clear identification of a gamma ray target. The good thing is that the behavior in energy of a dark matter signal is different from the astrophysical signals, which are typically power low. On the other hand, it's very likely typically much smaller than what we fear. Moreover, everything already here is explained very likely by astrophysical sources. So it's not easy only to exploit energy information to dig out and find out a dark matter signal from the diffuse gamma ray background. So the question is, can we exploit more information? Well, the point I want to raise here is that even though we call it typically isotropic gamma ray background, these gamma ray backgrounds at any frequency are actually not isotropic at a deeper level. Moreover, since they are produced, if we think about dark matter, by dark matter structures present at any scale, they must be anisotropic. Even though we are not able to pinpoint individual sources, and nevertheless, these fluctuations of the emitted field, which is anisotropic, can affect statistics of photons. So we can look at the statistics of photons across the sky and see if we can correlate these statistics to what? To the place where dark matter is distributed. This is just the point I was raising. If you look at the gamma ray emission, this is a simulation, of course, the gamma ray emission needs to be produced by the complex cosmic web, of course. Gamma rays do not have any tag on the end, on the distance where they were come from, so we basically integrate over all distances. If we integrate up to very high, well, very high, I mean, to some relatively high redshift, we actually have what we call an isotropic distribution. We do not have manifest structure there, even though these points are fluctuated, correlated to the way that matter is distributed. If we were able to actually have redshift information in gamma rays, we will look something like that if we take only very low redshift. And then we can do some tomography, okay? This actually, if we look only a very small slice in redshift, very low redshift, is actually showing that the distribution we should see in the gamma ray sky coming from dark matter should actually be like the distribution of objects in the universe, galaxies and galaxy clusters. Unfortunately, we cannot do this with gamma rays alone. So the idea is to actually cross-correlate the gamma ray information with something that brings this information on how dark matter is distributed in the universe. And this is what I would call gravitational probes, but for that I will list in a moment what I'm meaning. And therefore use a correlation of the two fields, something that tells us how dark matter is distributed in the universe, something that actually tells us our particle physics signal. In a sense, this could also bring additional information to the particle physics signal. We can use a lot of gravitational traces. The best in principle is the cosmic shear, because it's a non-biased, as it's called, matter tracer, because it directly traces the whole dark matter distribution in the universe. And we can use that. It's a lengthened, gravitational lengthening observable. Even CMB is known to be lengthened, so we can also use CMB lengthening. Or another way is to use some other observable, like a galaxy catalog, for which we have very large statistics and even more in the future. Galaxies trace dark matter by tracing the light. So there is some bias, as it is called, with respect to the underlying dark matter field, but this can be modeled and taken into account. We can look at the distribution of clusters, and more recently, we attempt a new technique, which is actually something that observation is starting to be relevant now. It's the distribution of neutral hydrogen, which is actually able to fill baryons in the universe, which are then inside dark matter objects, without the necessity to resolve an individual galaxy. This is done with a technique which is called intensity mapping through the 21 centimeter emission line. So we have a lot of ways to trace matter in the universe, and we can correlate that with the typical dark matter signal. So we have two source intensity fields, let's put in this way, which actually are an integral over the distance over the redshift of what? Of how your photons or how your galaxies are distributed in redshift or distance, and something which intersects the fluctuations of these fields. And we can do a correlation, like if we put the two images one on the other and look statistical correlation at given angles in the sky, similar to what is done with the CMB. I don't want to be too technical because the time is not much. I have some slides with more technicalities, but typically what is done is that the field, either gamma rays or galaxy distributions, is decomposed in harmonics, and the correlator is basically the angular power spectrum, like in the CMB. This observable will actually depend on the distance from which your gamma ray is emitted, or from the distance at which your lens, for instance, is placed in the sky, and something which intercepts fluctuations, which is the matter power spectrum. Clearly, gamma rays have only theoretical dependence on Z. We don't measure that, but since the observable we want to look at is dependent on the product of the two objects, if we use something that from the gravitational side is actually selecting a given redshift information, we are actually bringing indirectly information also on the gamma ray emission. And this can be interesting because this is just a window function as a function of redshift. This is dark matter, which is typically more emitting at low redshift. These are annihilating dark matter particles, and much less at higher redshift. The signal is concentrated at lower redshift, and these are window functions due to some two masses a galaxy survey. This is cosmic shear. This is another survey, and this is the CMB lensing kernel. For instance, if we look at this two-mass galaxy distribution, we are actually able to select only very low redshifts in the game. If we have shear, of course, the kernel is wider, but it has redshift information. So we can optimize the response of our cross-correlation signal by using this information. Astrophysical sources are typically unresolved. Astrophysical sources are typically emitting light from higher redshift. For instance, blazars, most of the local blazars, close blazars, are observed as individual sources, so they don't enter in the game. And so the window function is actually more concentrated at higher distances. And there are differences with the other astrophysical sources. So by using this is an additional information that we can bring into the game. And then, of course, we can use also the energy information, which gives us information on the mass of the dark matter particle, the annihilation channel, and so on. So we can do actually a tomographic spectral approach. I don't enter into the technical details. If you are interested, we can go back to. I'm just showing a results that have been obtained by attempting this technique. The first I show you is the cross-correlation observable between gamma rays Fermi-Lat measurements and the Planck CMB lensing measurement, which is a very strong measurement done by the Planck collaboration. When we cross-correlated the two, we actually have a mild indication that the gamma rays correlate with the CMB lensing. And CMB lensing is actually due to the distribution of matter in the universe. So see, there is an indirect, not so easy to extract information, but it's there. And this is the signal. You see the error bars are relatively large. There's also information on energy, of course. On the other hand, it's just a free sigma hint. From the shape of this signal, the angular power spectrum, we can infer that it's likely compatible with AGA, astrophysical sources, emission, and not dark matter. But this is not unexpected, because, as I said, CMB lensing is actually producing a cross-correlation signal from higher redshift, because it's actually something integrated up to the last scattering surface. Moreover, it does not have redshift information, so it's sort of average quantity. But since it's more concentrated at high redshift, should be potentially useful to extract information on the astrophysical sources and fix that model better, and then leave room to low redshift probes to cross-correlate it with gamma rays, and then have more hint, more grasp on dark matter. This is what is done best with, for instance, galaxy catalogs. And here I'm showing two masses where actually we are pinpointing very low redshift. It's better for dark matter searches. This has been done also with other catalogs, and this is actually one result shown in terms of the cross-correlation in angle. We see that there is a hint of a signal here. In the end, once you take into account all the uncertainties, at 3.5 sigma, so we cannot say there is a clear signal, there is a hint. Nevertheless, the shape it has, it's quite compatible with the dark matter. It extends to several degrees in the sky, which is beyond the Fermi-Lat resolution, Fermi-Lat PSF, which means that it's actually intercepting something on larger scale, which are good because dark matter halos are extended. If we interpret that as a dark matter signal, this is actually what we see here from the colored lines. And this is actually what this potential, let's call it like that, signal seen in the cross-correlation would actually reflect into the total isotropic flux. Much smaller than what is measured, difficult to extract this information from just the energy dependence, while the correlation can give more information. This, of course, can be reflected into either bounds or positive signal determination in terms of the dark matter particle physics properties. Here we are feeling dark matter annihilation, so we are feeling dark matter annihilation rate and mass of the dark matter plus the annihilation channel. This is what how we could transfer the information on that observable into dark matter bounds by using Fermi cross to the two-mass galaxy catalog. And we see that we have a bound which is touching the thermal cross-section at low masses. This is 10 GeV. Unfortunately, the modeling at the moment for annihilated dark matter has a big uncertainty. This is just to show the most conservative bound, which is if I have no substructures in halos of dark matter, which is very likely unphysical, or at least very not like the case. This is where we adopt a low or a high boost, and we should be between these two lines. So the bounds are not meaningless, because the bounds from dwarf galaxies are not far from this dashed black line. Of course, we can also interpret that since we have the 3.5 sigma effect as a signal. In this case, these are the closed region which would reproduce that, and the arrow bar is the interval due to the modeling uncertainty. They are more or less in the same ballpark as the galactic center excess. Nevertheless, bounds are the conservative approach. Let me just go through quickly. This is stuck. Sorry. Can you still hear me?
Yes. Yes.
Okay, sorry, but it was stuck. I just to go to the conclusion quickly. This is with Galaxy Catalog, where we have an interesting observation, still not so strong as our observation. Galaxy cluster also can be used. We see here, this is basically information of the redshift distribution of different catalogs of galaxy clusters. Some points are higher redshift, but these are selected to be low redshift, as you can see. And this is lower redshift. And the extension of the angular sizes of these catalogs is actually not very large, of course, but relatively even beyond. I mean, this is in Archimedes, so this is the extension. This is the best in the energy range we are looking at Fermi-Lat resolution. So we are typically inside the PSF, unfortunately, for the moment. Also here, there is a potential observation, at least there is a 4.7 sigma effect. This is the correlation as a function of the multiple. And this is a little bit tricky because what we got from this information is that a cross-correlation signal is sort of there up to 1 degree, which is beyond the Fermi PSF. So it's pointing towards something which is extended. And a typical cluster distance, this 1 degree, implies something of the order of 10 megaparsec sort of dimension, which is something big, large in size. This could mean that a large fraction of the signal, or a fraction of the signal, seems to be not physically associated to the individual cluster, and therefore it can be either produced by astrophysical sources which are actually residing not in the cluster but in the larger scales of the cosmic web, or the dark matter itself. Statistics is not enough to distinguish these two options, but still it's an interesting thing that could be improved with more statistics from the cluster size. And then I just finish with the more recent result, which was also the original motivation of our study, which is to use, again, gamma ray data from Fermi-Lat, but the cosmic shear, because this is an unbiased, it fits the whole dark matter in the universe. There is a signal, in this case, the evidence is at 5.3 sigma, and this is actually the angular behavior of the signal, still difficult to interpret. Notice that we have used 9 years of Fermi-Lat data, but the only 1 year of DES, dark energy survey data, because that was what was available at the moment. We are working on the 3 years data. So the signal is actually relatively good, well localized at small angular scales. And this is quite compatible with blazars. It's not strange that this is the case, but this is, in any case, interesting. So there is a hint of correlation, but there is also a hint of correlation. It's still a hint of correlation. If we just take the average, or everything here is not compatible with zero. Given mean angle, they are very large errors. So since the signal seems to be localized at small angular angles, this is more compatible with blazar emissions, if this is the only origin of the effect. It's basically this yellow line. Statistics is not enough to actually interpret this large scale potential, but still no hint, very important hint here at higher angles, because dark matter would work well. Blazars could also contribute, but one should move this line up to here, which is not easy. So we will see in the future. Actually, I finished my time, so I want just to recap very briefly. And the idea here is to use some kind of filter to enhance the options to look for a dark matter signal in gamma rays, but this can also be used in radio or in X-rays. There are already attempts, the largest significance is with cosmic shear, And these are prospects for the future, which actually I leave you here for you to read. And I thank you very much for the attention.
Thank you for a very intriguing talk. Any questions? We have time for a few questions. Then I will start the discussion with a question. What do you expect? What you're waiting for as the most interesting next result?
Well, the one which is actually interesting to look at is with the cosmic shear, because DES now has completed the analysis and released the data with 3 years. The final goal of DES will be 5 years or even a little bit more. So that would be the goal. This was also the original proposal we actually put out. 3 years is actually, we are starting to look into the data, so no results are there. So this is very likely the most important. Even in that case, maybe statistics will be not enough yet, but there are options for the future, because this actually will be improved by both LSST and Euclid from the shear side. And well, Fermi is accumulating statistics. It will not improve much from that side, but now we are already more than 10 years. So this is actually important to use that.
Thank you. More questions? Actually, I have one more question. How will you confirm that the signal is really dark matter?
Well,
not anything else?
Ideally, even though one would need good statistics, the point is the following. Astrophysical sources are point-like, a very small object in the sky. So the way the power spectrum behaves, if this is due to that, is different from dark matter objects because they are extended objects. So basically what you have is that when you look at the fluctuation field, if you go to very small angles, small depends on the ability of your detector, then you can start feeling if there is inner structure of these objects. So you have basically a suppression of the power spectrum in the smaller inner parts. For gamma rays, of course, the resolution of a gamma ray detector, Fermi is, let's say, 0.1 in a good energy range. That's why I brought opportunity for CTA. We are investigating that too, because that could have an even better resolution. On the other hand, one can look also at X-rays or even better radio. Radio has a very good angular resolution. So in that case, you can potentially go to smaller angles in your correlation, and there you can start distinguish whether the fluctuations are the point-like sources or something which is more extended like a halo. This is, in short, a potential way of looking at that. Because it's different to have fluctuation due to points or to have fluctuation due to objects which are more extended. I didn't have time to show this, but I had a plot here which sort of, or maybe I didn't put it because it was too complete. I mean, it took time to explain that, but this is a way to look at that. So the message is the power spectrum due to point sources and extended objects exhibits differences below some angular scale. And therefore, if you can access that, maybe you can have a better hint on what is emitting your photons in the sky.
Thank you, Nikolai, for interesting comment, and we go further, and I welcome Yuri Suvorov from University of Naples reviewed on the dark side collaboration.
Yes,
Yuri,
hello.
please.
Let me share the screen. This one. Tell me if you see the screen.
I do. You may do full screen as well.
Give me just a second. I tried to close the menu. Just a second. Full screen. Okay. Do you see it now?
Not exactly. It's dark. Can you switch it up and down slide?
Maybe because it's.
It is dark.
Okay.
Okay, it may be fine without full screen as well.
No, let's do differently. Just a second.
Maybe you share the window, not the screen.
Yeah, well, what I do is, yeah, it's maybe a little bit heavy into this. Okay, let's try here again. It's a bit heavy, but
oh, now excellent.
Okay, perfect. So I completely changed the topic, and I will go to more in technology and experiment. And let me give you general outlook of the dark side collaboration. We are looking for dark matter with direct search, with usage of double phase time projection chamber filled with liquid argon. So these are techniques, and we started with the building of first prototype 10 kilograms detector in 2010. It was designed and built at Princeton, and then we moved it to underground laboratory at Gran Sasso, Italy, for the underground run, and you see the device on the picture on top here. Then soon after we moved to the bigger detector, we constructed Dark Side 50 experiment. And we had a 4 years scientific run. In 2015, we formed a global argon dark matter collaboration where we united more projects such as DEEP, 3600, Mini Clean, and RDM, with the unique goal to push for search of the dark matter with a direct search based on argon and TPC technique. And the goal of this collaboration is to first build the dark side 20K detector, which will be located at LNGS in Italy, and then move to the final detector of 300 tons, which will be Argo and possibly will be located at Snow Lab. So our recipe, let's say, for the research is the following. We first rely on the location. We choose underground, deep underground location. In first place, LNGS, and then at the end, Snow Lab. We rely on double phase time projection chamber as the method of study in order to explore the scintillation light and ionization signal. V2 detectors for Newton and for the muon. And of course, the target material for us is the low radioactivity argon, which is underground argon. On the picture below, you can see the TPC. This is an example of the TPC of the dark side 50. Here is the assembly of the detector, the water Cherenkov of detector together with the liquid scintillator sphere. And finally, here is the source of our argon, the purification column at Fermilab. So really quickly, detection principle of the time projection chamber. Here, schematically, you can see the model of how it looks like. Usually you have a cylinder made of acrylic or PTFE, which delimits the sensitive area. And it's limited on top and at the bottom with the transparent windows. Usually you put some coating with a material which is transparent and conductive in order to convert this to the electrodes. And therefore you have a cathode and anode in order to apply the voltage, the potential to them and create fields inside the sensitive volume. Also, we have a grid just below the border of the liquid. And then on the very top below the anode window, we have a gas thin pocket. This is why it's double phase. So what usually happens is when particle cross the argon, it do two things. It excites the argon atoms and ionize them. Excitations leads to the scintillation, signal S1. And then free electrons released in the ionization drift upwards to the gas pocket, get released, extracted from liquid, accelerating gas, and this produces another scintillation, which we call ionization signal S2. So basically this at the end gives you a 3D reconstruction of the event because the top array of the PMTs or silicon PMs, for example, give you XY resolution position of the event, and the drift time which electrons need to go from the point of interaction to the gas phase give you the Z position. Another interesting and important feature of liquid argon is extremely powerful pulse shape discrimination, which is based on two time constants, which determine the time profile of the S1 signal. It has two states, the singlet states, and triple states, and the time constant is 3,000 times different, 7 nanoseconds and 1,600 nanoseconds. This well-distinguished states allow us to be sensitive to the type of the particle, nuclear recoil or electron recoil. So as I said in the beginning, first detector was dioxide 10, and it's a small cylinder. Here you see the overview picture of the TPC. It's the acrylic 1 centimeter thick cylinder, 23 by 24 centimeters, roughly speaking, closed on top and the bottom with a few silica windows, and viewed by 7 PMTs, 3-inch PMTs, 7 on the top and 7 on the bottom. In 2011, we brought the detector in the ground, and here you can see the cryostat where the TPC was closed, and at the end, the assembly where you have a passive shielding represented by the water tanks, small tanks filled with water. We did multiple runs with external gamma sources and laser calibration. Here I show you just 2 examples. More can be found in this article because we published the results, and the measurement of the light, the goal run with this detector was very successful, 9 photoelectron per PeV. So after this success, we definitely moved immediately to the construction of the bigger detector. This is dark side 50 detector. It's again a cylinder, as you can see here on the picture. PTFE, in this case, bigger, so that we have 46 kilograms of active mass. We have more PMTs, same type as before, 19 on the top and 19 on the bottom. Here you can see the assembly of the bottom assembly of the PMTs. You have also a fused silica window for the cathode. The PMTs, by the way, are coupled with specially designed at Gran Sasso cold amplifiers, which improve the behavior at liquid argon temperatures of the devices. In order to obtain the uniform drift field, we use copper field shaping rings. Here on the picture, you can see these lines. And cathode and anode are formed by coating a thin indium tin oxide layer, about 50 nanometers, on the surface of these windows. Obviously, all inner surfaces are coated with the wavelength shifter in order to move the original line 128 nanometers producing liquid argon with one more suitable with the PMT's efficiency in detection at 420 nanometers. And this shadow whitish thing is the TPB. So altogether, it's a typical matryoshka design. At the data center, you have TPC closed inside the stainless steel cryostat, double wall, vacuum insulated. The cryostat is located inside the sphere, 4 meters in diameter, filled with 30 tons of the boron-loaded liquid scintillator in order to enhance probability of interaction of neutrons. And it's viewed by 110 8-inch PMTs. You can see here the luminar foil is applied to the inner surfaces in order to improve the light collection. And at the end, the sphere is located inside the water Cherenkov detector filled with 1 kiloton of high purity water. And we have 80 PMTs of 8-inch in order to view this volume. Tyvek is used in order to improve the light collection efficiency. As I mentioned before, one of the main goals of ours is to use a special target. It's low radioactivity argon. From the very beginning, you wanted to find the source of this. And so we start our enterprise, let's say, 2009. So basically what happens here is that the atmospheric argon has a ratio between radioactive component argon-39 and stable component argon-40 of the level 10 to the minus 16, and already this gives you a rate of undesired bad events in the detector of 1 becquerel per kilogram. So the idea is to follow the same philosophy of Vorexino experiment, where we solved this problem, which was concerning the carbon 12, carbon 14, And we went to underground sources. So the idea is to look for the wells with CO2 and see the traces of argon in those places where basically is shielded by the crust, and therefore the radioactive component decay and it's not regenerated again from the atmosphere. So we found this place in Colorado and Cortez. There is a Kinder Morgan company which extracts helium. So we made an agreement with them and we built a first extraction plant, you can see it here, in order to extract and enrich argon. We pass from 400 ppm to 5%. The next step is go to Fermilab, where we have this 3.2 meters distillation column in order to further purify the mixture. And at the end, the result was placed in the gas bottles and shipped to Gran Sasso for filling. So the first run in Darkside 50 was with atmospheric argon, and we take this black curve spectra in S1 signal, and then we pass to underground run. And so you see this green line shows you the drastic reduction of these events. We measure factor of 1,400 of argon-39 depletion with respect to atmospheric argon. So definitely this technique works. We want to rely on it, and it's okay. So as I said, from 2015 to 19, we was running with the detector and collecting data. This data was already shown also in this conference in the past, in particular to articles, low mass analysis and high mass analysis. I don't want to go too deep into the in the discussion. The only thing I want to show you, this red curve, it's a sensitivity which we reached in Darkside 50 in 2018 for the high mass and for the low mass. And we basically proved that as a scintillator, liquid argon works really fine. The technique of the double phase TPC, it's perfect, and the underground argon works. So the idea is to go bigger, to get bigger, and try to push the sensitivity towards the neutrino floor. How this can be done? Obviously, we have to go bigger. And the idea to make a new detector, and this is under construction actually now. So we pass from 46 kilograms to 51 tons. Unfortunately, in Gran Sasso, there is no more possible to use liquid scintillators. So this kind of matryoshka is not acceptable any longer. So we made a new proposal where we will use only liquid argon, atmospheric and underground. So since we have now need of much more underground argon, we need to build a much bigger plant. I remind you that in 6 years, we produce 155 kilograms in order to fill Darkside 50. Now we need enormous amount of argon. So this was addressed with 2 new projects, Urania project and Aria project. Urania is basically an industrial scale extraction plant with a production rate of 330 kilograms a day. So it's twice what we produced previously in 6 years. And it will be located at the same place in Colorado Cortez. Actually, this plant was already built, and you can see here in the pictures a few models ready to be shipped to Cortez. So next year, we plan to prepare the site in Colorado and install the plant. And the actual extraction hopefully will start in 2023. For what concerns the purification, we need to move from 3.2 meters to something much bigger. And actually the column we designed and again built, it's 350 meters tall with 30 centimeters of inner diameter. And it will be installed in Sardinia in one of the wells of the coal mine in order not to have it on the surface outside. So it will be covered within, let's say, well. The production speed is 1 ton per day. Again, before I was talking about 1 kilogram per day. In the meanwhile, yes, the column was built, all models were prepared and shipped to Sardinia. And we also built a demonstrator, a small column, which has a reboiler, condenser, and the middle module in order to explore the capability of this column. And we obtained really promising results. I invite people interested to look at this article for more details. Really briefly, the column was supposed to be assembled last year, but due to pandemic, we slowed down our activity. In any case, this spring, we managed to perform a test installation. We took one module and we lowered it into the shaft just to check the procedure. It went well, so we're happy and hoping next year we will start the full assembly of the column inside the well. At the end, it would be nice to be able to check the purity between the batches of your purification. And for this, we came up with a new detector, DART. It's a small cylinder of high purity copper with a PMMA structure inside that will contain liquefied underground argon of about 1.4 kilograms of active mass. It will be viewed by 2 centimeters squared silicon PMs. These are the silicon PMs. This is a structure, the cylinder. And the nice thing about this is that it will be placed inside another detector, RDM, which is presently at Carfranc Underground Laboratory in Spain. So this detector will be an active veto. It will have 850 kilograms of atmospheric argon viewed by PMTs, and inside we'll have this nice device capable of detecting the depletion factor of about 1,000 and reaching 10% of precision in 1 week of run. So DART is already in Spain, and colleagues do measurements with them, and at the end, in the fall of this year, we hope to install DART inside RDM to start measurements, test measurements. Okay, so when we clear the question with the target material, another important topic is the light sensors. So based on our experience in DarkSide 50, we decided to abandon PMT technology, and we moved to silicon photomultipliers. We formed a collaboration with the Bruno Kessler Foundation in 2014 and developed a new device suitable for our goals, capable of working in underground laboratory, but this is not that important, but more importantly, at temperature of liquid argon. So this device is NUV HD Cryo. It's rectangular in shape, 12 by 8 square millimeters. Assembling 24 of them, we obtain what we call tile, and this is the picture of it. So this tile then get coupled with the front-end board, populate with electronics, transimpedance amplifiers, which then get summed and produce the output signal in differential. Altogether, placed inside the plastic cage, gives us the photo detecting module. Next step is to place 25 of this on the specially designed copper plate, and 25 PDMs together form PDU, photo detecting unit, and it has 25 channels. So it's quite heavy object. It's 5 kilograms because of the copper is a massive plate there, 6 centimeters high, and 25 channels, 25 by 25 square centimeters. Overall, for DarkSide 20K, we will need 28 square meters coverage, and this will be produced in LFoundry, the raw material wafer LFoundry, and all the assembly and forming of PDM and PDUs will be done in dedicated facility at Gran Sasso. In 2019 and 18, we produced 2 PDUs. You can see it here, and these are the pictures from the testing at Gran Sasso and also at CERN, which were done in liquid nitrogen and liquid argon. Unfortunately, this activity was stopped also due to the pandemic, but we tried to regain it again. The results were somewhat promising. We had some issues, but nothing showstoppers were found. Another activity which was done in 2019 is that they took 2 tiles, 5 by 5 centimeters, and placed it to the very small time projection chamber of red experiment. This is an experiment dedicated to recall directionality study. But at the beginning, we had a very long run, 5 months, in order to characterize TPC and, more importantly, silicon PMs, and to see how it behaves. So we took a lot of runs in a single phase, double phase, with the multiple calibration sources, gamma, Newton, and Newton-GaN, americium beryllium run, source calibrations, laser runs. We came up with articles, so I invite people to have a look. The results are very promising. This is an example of single photoelectron response. Individual peaks are very well separated and visible. And more importantly, the stability over 5 months. This is the longest run calibration did with silicon PMs. Looks very promising. So based on all these activities of testing and assembly, we try to think what can be done next, how we can simplify and improve the design of the PDUs. And actually we came up with two options. One is to simplify the PDM and make, instead of orthogonal connection, parallel connection as in red case, and shrink in this case the PDMs. We will use the same copper plate and the same way of connecting between PDMs and copper plate. Otherwise, we join together tile and front-end board. So you have a substrate. On one side, you have a silicon PMs. On the other side, you have an assembly with electron components. So in this case, the PDM becomes a very thin plate thing. Few of these devices were already produced at Gran Sasso and look perfectly, promising. What you do next, instead of having 25 elements on the plate, you can assemble a simpler device. Basically, this is 4 tiles, 5 by 5, already combined with electronics. And one of this becomes one of 4 placed together, which gives you the new PDU. It will be smaller, 20 by 20 centimeters, because it has only 14 tiles. Moreover, you can sum 4 tiles in one channel and come up with just 4 signals out of 20 by 20 square centimeters. You reduce weight, you reduce size, you reduce height, and you improve the protection, because you can also put the plastic cover on top to protect the wire bondings. All these things are under construction, and we try to test few examples in Naples at the beginning, in the middle of September, sorry. Few words about the facility. This is a dedicated facility, a huge clean room. We're building in Montaggio and above ground lab at Gran Sasso. It will have 400 square meters of available space in order to put all machinery, all the test benches and working spaces. So the idea is to first check the mass production of a foundry, the raw wafers in cold temperature of 77 Kelvin and room temperature. Then we start to cut them into the pieces, the small silicon PMs, and then assemble PDUs and PDMs. All PDUs assembled in NOAA, obviously, then will be shipped to Naples for testing. And in Naples, we have a dedicated facility. You can see the pictures of it. It is already there, a custom-made 1-ton cryostat with dedicated cryogenics. All this was assembled at the beginning of the summer. And before the break, we managed to commission the plant. We filled it with liquid nitrogen, drain it, and determine the more important parameters. So system is ready, and we hope starts testing in mid of September. So really briefly, altogether of the DarkSide 20K design, how it would looks like. You've seen this picture already, so it will be 11 by 11 by 11 cube. And this is a prototype membrane cryostat. Copper paradite cage in brown. Before that, it will be filled with argon, 700 tons of argon. Then there will be a sealed ultra pure acrylic vessel as a TPC. So maybe on this right plot, you can see it more clearly. It's not in scale. So outside you have a cryostat, then you have a cage, and then we have this active Newton Vita made of acrylic plates, panels doped with gadolinium. So before that and after that, you have 2 buffers, outer active veto and inner active veto. The space is about 40 centimeters. And this volume is viewed by silicon PMs. It's the same silicon PMs, but coupled with different electronics, especially designed for the veto. Inside the inner volume, we have a sealed acrylic vessel, which is the TPC, and it contains 51 tons of underground argon. Cryostat, nothing special here. The well-established technique in CERN, they already built 2 for Proto-June. So this will be, I hope, a nice and easy contribution, and the construction will start next year at Gran Sasso Underground. Vito, it's another development which we're doing. We actually develop a new acrylic panels doped with 1-2% of gadolinium. We will need quite some amount of these blocks in order to form the orthogonal shell around the TPC. So as I said, we have 2 buffers. It will the assembly will be sandwiched between these things. The whole volume is divided in 8 sectors. And it will be covered with silicon PMs and CMOS integral cold electronics developed by Torino Group. Obviously, all surfaces will be treated with the reflectors and wavelength shifters. TPC, octagonal shape, acrylic sealed vessel, 3.5 in height, 3.5 in wide. We have a strong team from Deep Experiment which take care of this, so we in good hands, let's say. Acrylic panels will be used also for anode and cathode windows. We will not use copper, we will not use ITO, we move to Clavius conductive polymer in order to form this transparent conductive layer to form anode and cathode electrodes. And also for the shaping rings, we will use groove filled with Clavius. Obviously, also here we will use ESR foils to improve the light collection and TPV coating to move the light. As a grid, we will use the SS frame with the wires located inside this acrylic vessel. This program was unfortunately stopped by COVID, but we tried to regain it as soon as possible, basically at the beginning of the next year. In 2019, we did this test. Now we move to the 2 PDMs assembled to the same time projection chamber. And then soon after, we will want to build a smaller model of the DarkSide 20K, but exact model, coupled with 5 PDUs on top and 5 PDUs on the bottom. Instead of go to the conclusion, let me share just this plot to show where we want to push our sensitivity in the long run with DarkSide 20K. This is, let's say, should be inclusion of our effort. Thank you very much.
Thank you for very promising presentation. We have a time for one short question. I don't see hands. Someone. Nicolau, please.
Yes, I wanted to ask you one thing. You actually show that you have a new design for the PDU, which are sort of a little bit smaller, but they should be an improvement because they are, if I understood, they are lighter and the structure is simplified. So my question is this the final design, and why you are thinking of modifying the PDU structure? So what was the motivation for that?
Well, the idea behind is just, let me say, goodwill. If there is a cheap way to simplify things, because keep in mind that we're talking about 25 square meters. So these things, we will need more than 100 on the top and more than 100 on the bottom. Therefore, the installation, the secure and guaranteed installation is very important. The integration group works really hard to find the best option. This is not the freeze design yet. This is just something on the table which we are discussing within the collaboration. Our basic design is this one, the original design. But there are some ideas which, if will cost us nothing, why not apply them? That's basically the reasoning behind.
Yeah, thanks. Interesting. It's an interesting idea.
Thank you for the question.
Thanks again, Yuri, for nice presentation. And we move forward to the talk by Andrei Alexandrov, INFN and University of Naples, Directional Dark Matter Search with NewsDM. Andrei, please share your presentation.
Okay. Hello, everybody. Let me share my screen. Okay, can you see it? Please confirm.
Yes.
Okay, so my today's talk is about new achievements and status of the NewsDM collaboration. So the The NUSDM stands for Nuclear Motion Beam Search with a directional measurement, and the collaboration consists of about 80 physicists, 23 institutions, and from 5 countries. Below you can see the website link and the link to the letter of intent. So is an outline. According to the classical cosmological models, the solar system moves inside a halo of dark matter particle, and the detector located at the surface of the Earth will see these particles as an incoming wind from a definite direction, from direction of Cygnus constellation. Then once detected this anisotropy in recoil of target nuclei, which should be correlated with the direction of this dark matter wind, and once it is detected, it will become an unambiguous proof of the galactic origin of dark matter particles. Moreover, this can be a unique possibility for a detector to operate below the so-called neutrino floor. And nuclear motion in this case are perfect detectors for their high granularity, and also for their state. They are solid state with quite high density, and this will allow to reach large masses required for high sensitivity sufficient to reach the neutrino floor. With a relatively compact detector. So first, about the detection principle. Nuclear motion consists of crystal of silver bromide, which microphotograph is here on top. And below is schematized as a scheme where the Argentine crystal is just a sphere. When a charged particle crosses a crystal, it creates ionization, and electrons from this ionization, they migrate inside the crystal and are collected or trapped on surface lattice defects. If one lattice defect can trap more than one electron, so it can trap several electrons, and this creates electric field which attracts interstitial silver ions that migrate to the same defect and recombine with electrons and create so-called latent image, which can persist until the emulsion is developed. During the development, it is placed in a special liquid called developer, and this and the presence of latent image on a surface of a crystal triggers growth of silver filaments. Then when development is stopped, it is placed in fixer, and the crystals not activated crystals are developed, are dissolved and removed, and only silver filaments, which are also called silver grains, remain. Then, after film drying, they're placed on optical microscopes and are seen as something like that on the microscope. So, if charged particle crosses more than one crystal, activates more than one crystal, then its track can be visible as a line sequence of silver grains. Especially for the NUSDM experiment, there were designed two types of nanometric emulsion, one called NIT, nano imaging tracker, and the other one is ultra NIT. The first one has crystals, mean crystal size of about 40 nanometers and the granularity of about 70 nanometers, and the second one has crystal size of about 20 nanometers with a granularity of about 40 nanometers. So in principle, nuclear motion, this special type of nuclear motion can record very short tracks. But the real problem here is the extraction of this information from a motion in reasonable time, since there are techniques like electronic microscope or X-ray microscope that have very high resolution and can be used, but the great disadvantage is that they're extremely slow. And if one needs to process about several tons of emotion, it will be impossible to do it in reasonable time. So the only possibility would be to use optical microscopes like those used in Otter experiment, which are relatively fast. But the main problem is that due to existence of diffraction limit, due to the best optical microscope cannot access to the details smaller than 200 nanometers. And as you can see in this plot, it's a simulation of track length, expected track length of nuclear recoils for dark matter particles from 10 to 100 GeV, and all of them are well below 1 micron. And since the vertical scale is logarithmic, the major part has length below 200 nanometers, and these tracks will be visible as single objects. For example, there are 3 tracks of different lengths, and below X-ray images, and above row is images taken at optical microscope. So as you can see, grains are mainly not resolved, and then the shortest track is visible as a slightly elliptical object spot. So we need super resolution to extract this information from detector. So the first approach developed by our collaboration was to use this anisotropy in shape, the ellipticity to detect if it is a single grain which mainly creates a spherical spot, or it is a track composed of 2 close grains. They are not resolved, but they produce an elliptical spot. So this the shape of a spot can be assessed and measured by a special algorithm, and then using a cut on ellipticity with some efficiency, it is possible to separate tracks from single grains that are typically due to random thermal activation of crystals, or it can be also due to gamma or electron interactions inside the emulsion. Okay, this approach has been confirmed by processing a beam of carbon ions with the energy of 100 keV, and we see an excess of tracks of events that have direction along the known beam direction. Then another approach is to use the so-called plasmon resonance effect. Plasmon resonance happens when a small silver, in general metallic nanoparticle, is immersed in dielectric medium. Then when it is illuminated by an electromagnetic wave, which is like light, it makes the electron cloud to perform collective oscillations. And when the frequency of external field coincides with the intrinsic frequency of this Yakalauta oscillator, then a resonance occurs and it changes drastically the optical properties of this of the whole nanoparticle. Cross sections, both cross sections absorption and reflection cross sections increase, and if the nanoparticle is not spherical, then it is also sensitive to the polarization of incoming light. Direction of polarization coincides with direction of electromagnetic field, and for example, if it is illuminated with polarization, if polarization is directed along the smallest dimension, then it will produce resonance at smaller wavelength. If we change polarization and make it aligned with the longest direction, the wavelength of resonance will move to longer wavelengths. So if we fix working wavelength and there is also a detection cut on the brightness. In this case, if, for example, if we fix at the right wavelength, then that means that at some polarizations, that this polarization will see this nanoparticle, and if we rotate it 90 degrees, we will not see it, so it will act as a switch, so we can switch on and switch off close nanoparticle. So to illustrate it, okay, if we have two close nanoparticles, it will work in like this. So without polarization, we will see them as equally illuminated, and it will produce us a slightly elliptical spot. So, but if we introduce polarization, and if we assume that the maximum of polarization occurs at different angles, then we will see they will appear to us something like in this animation. So they will also alternate. But in microscope, we will see not the direct image, but convolution with its point spread function. So it will be always a single spot, but it will start moving. So, and this feature can be used to improve the resolution of the microscope. So we have tried two approaches. First one is the analysis of the barycenter shift, and the second is the most recent one, the joint image deconvolution. So I will start with the barycenter shift analysis, a real image in this case, not simulated, of 100 keV carbon track without polarizing, and on the left with polarization rotating. Then it is possible to trace the center at each image, and we will, for tracks, we will see a trajectory like this, which is elongated along the track direction. For single grains, it will be more less elongated and more compact. So this allows us to introduce a threshold on barycenter shift, and take the direction of track as the direction of barycenter shift, which is defined as the largest direction of between 2 points in the trajectory. So this approach was confirmed by processing 60 keV carbon ion beams. So we see that for there were two populations separated by threshold of 21 nanometers. And we see that there is an excess in non-beam direction for a longer population, and short, which typically single grains have an isotropic angular distribution. Okay, turning back to the second option, which was the joint image deconvolution. Actually, it's possible to do the inverse procedure. So take 8 images, first measure 8 point spread functions for each polarization, then take 8 images and perform a numerical deconvolution of these images. In this case, since we have 8 images at input, if we have 8 polarizations, we have 8 images on input, and we need to produce only 1 image at output. We get an additional information which is represented by color, and this color means the phase of that pixel corresponding to the polarization angle where it gets maximum of the brightness. So as you can see, the reconstructed scheme is very similar to the original one. Okay, if we also tried this with real carbon ion tracks. On the left is what we see at microscope. It's animation composed of 8 polarization, eight images corresponding to different polarizations. And on the right, you can see a reconstructed image. And in the inset, it is compared with the same image of the very same events. So as you can see, it is both shape and length are very similar. So this method allows to measure not only the direction, but also the length of track. And if we take as a reference measurement done with electronic microscope, then this method and the microscope allows to measure length with accuracy of about 28 nanometers, which is comparable to pixel size of optical microscope. And the spatial resolution of the system was estimated to be about 80 nanometers, which is very close to the granularity of the NAT emulsion. And actually it is limited by hardware, by pixel size. So this limit was obtained by using the Nyquist theorem, and we expect that after upgrade, after reducing the pixel size, we will be able to improve this resolution. Okay. The microscope assembled in our laboratory in Naples that allowed to perform the super resolution measurement is shown in here. Its core element is liquid crystal polarization analyzer developed by us. We use liquid crystal since it allows us to rotate polarization without any actual mechanical movement. Otherwise, it would introduce vibrations, and this allows us to achieve spatial accuracy measurement of barycenter shift measurement, barycenter position measurement accuracy of about 3 nanometers, so both in X and Y direction. And this microscope is described in this article. So the very same analysis can be used to perform measurements in 3D with a special microscope, which was also designed in our laboratory, and we got an international patent for that. This microscope the special design will allow to create the second plane, which is vertical, so it will have 2 planes. One is conventional horizontal plane, which allows to measurement in X and Y, and another plane will be vertical, so with possibility to rotate it and align it with the track. So we will see 2 projections, 2 orthogonal projections of the track, and this allows us to make the same measurement, nanometric measurement in 3 dimensions. Okay. Another important feature of that can be used is the dependency of resonance wavelength on size of nanoparticle. So on the left, you can see the that with the increasing dimension of nanoparticle from 10 to 100 nanometer, the resonant wavelengths shift to the right, it becomes more red. And in case of non-spherical nanoparticle, as you see in animations on the right, it also starts change color when you with change in polarization. In case of nanorote 45/80 from blue to green, and in case of longer nanoparticle from blue to orange. So this feature can be used to detect this, to define the stopping point of recoil. So, for example, on the left, you can see a track of alpha track, which has stopped here in top near the top left corner, and it produces a very red grain. So, meaning that the major of ionization has been produced there. Okay, and the size of grains is correlated with the ionization produced in that point. So this can be used not only for alpha particle tracks, but also we see not that explicitly, but also for very short carbon ion tracks. So they not only moving, in this case it is illuminated with white light, but also change color and produce kind of gradients. And as first step, we try to use all polarization, but a single image and to detect this gradient, which is barely visible with naked eye. We have constructed, we have developed a dedicated neural network that can and trained it to distinguish the direction, the head-tail sense of a track, and only with a single image only, it is capable of predicting with 65% accuracy, which is a very good sign, meaning that when we add also polarization information, the accuracy should be improved. Another use of machine learning in our experiment is that we use it for background rejection. Here the plot signal efficiency versus background rejection power for 30 keV carbons and 400 keV carbons, and as you can see, so we still have high efficiency, about 30% in both cases, and we managed to distinguish it from single grains with the level from 10 to the minus 3 to 10 to the minus 4 as a rejection power. This also has been done with neural networks, and the results are submitted to physics communication, computational physics communication journal. Okay, about the current status of the experiments. So unfortunately, there was a very long stop from March until December of the last year. Since December, we have built a new facility. The gel production machine that was installed, so we moved the gel production underground to avoid accumulation of background during its production and transportation, and they were done a lot of other works, and then in March it was started assembling of 10-gram detector, and the run has started in the beginning of the summer, and it is about to finish. For tomorrow it is planned the extraction of the last emulsion batch. So the parameters are given in the table. So there are 10 grams, 40 days at temperature -50 to reduce spurious thermal activation, and also sensitivity to gamma and electrons is reduced at lower temperature. Okay, and also this summer in July, they was submitted a conceptual design report for a bigger 10-kilogram scale experiment, which, okay, the scheme is shown here in the picture, and the shield is a picture on top right. So it will be about 1 meter of polyethylene shielding, and it will be equipped with an equatorial mount to maintain direction to the Cygnus constellation. And it will also operate as planned at least at -80 degrees Celsius. So as a conclusion, the goal of the CDR is to build a 10-kilogram scale detector. With this detector, we will be able to explore, for example, Dama region with a complementary approach that will use also the directionality if necessary. Also to build, it will be the first heavy solid state directional detector, and as a long-running goal, we are planning to build a detector that will reach neutrino flow, so we can take advantage of the directionality in its operation. So, thank you for the attention.
Thank you for this interesting and detailed presentation. We have short time for one question. Please, Marco.
Yes, as you know, we are very interested in your work, and the dark matter part is very interesting. How would you think is scalable actually between 10 kilograms and a ton in terms of the mass that you need to scan? Is it something that you are already studying, that you have some idea? It might be not trivial to scale just in mass because you need to analyze all this big mass with very fine detail. Thank you.
Yes, yes. Thank you for the question. Well, actually, there are two approaches. One is to increase mass, and another one is to decrease the detection threshold. So we're working in both directions. To scan. So we have projects that will allow scanning of with a speed of about several hundreds of kilograms per year. So also in scanning, there is the approach is step by step. So there will be several steps. First, we have very fast microscopes that cannot do super resolution, but they can be used to produce predictions. So and then we will use super resolution microscope that will scan only. They are slower, but we can scan only prediction points. And for another reason for the reduction of threshold, we also have a project. We're developing a new type of microscope that will use photothermal detection, since there is to go down in detection threshold, we need to reduce grains. We need to reduce granularity, and we will use ultra-native emulsion with 20 nanometer grains, and they are very difficult to see in traditional optical microscopes. So we will use photothermal detection in this case, which will allow us to go even smaller grains and smaller detections. And since this scale is logarithmical, so the length it decreases as exponentially with the number of recalls decreases exponentially with length. So we don't need to build a 100 or 10 tons detector. Probably 1 ton will be enough.
Thank you.
We have one short question from Rita Bernabé. Rita, please. Rita, do you have a question?
No, I have a question. I just have not the audio. I want to say just two small things. The comparison is not made correctly, but I will mention a few in my talk, and this has already been discussed several times. But even assuming this, you know that the exclusion plot hold it just if the systematic error is exactly 0, because otherwise the confidence level has no more statistical meaning. How you can exclude the systematic error considering the huge data handling and the process that you have very interesting shown as simulated?
Do you mean systematic error in measurement?
For sure. Because you discuss things, but you never, it seems that in all these steps, which are very hard, very difficult, very appreciable, you never find any contribution from systematics, which is surprising, because the real life is different from simulation. In the simulation, you decide the life. In the reality, no.
Well, no, not all the results. Okay, it's we're in the beginning of the experiment, but not all the results are simulated. So there are, of course, we need to accumulate much more statistics. So now with extraction of 10 grams, probably we will have. Okay, we will have to analyze them.
I also believe so.
So and we will find out this.
Yes, thank you.
Thank you. And we proceed in the next talk by Rita Bernabé from INFN and University of Rome 2. Recent results from Dama, Libra, and comparisons. Rita, please.
I hope that you are. You okay? Yes, yes. Okay. I will briefly give some information about the new result released in July by our experiment and make some comparison which are often claimed from different experiments. I remind that Dama setup is an observatory for rare process which has realized several low background setup with general purpose and many rare process investigation and detector development. Many of them have been already completed and closed. In particular, for the dark matter, our pioneer experiment, Dama NE, has worked and was then substituted by Dama Libra Phase 1, which was upgraded in Dama Libra Phase 2. I will also mention shortly the possibility that on which we have worked in the last year. As you know very well, the annual modulation signature is in an ambiguous way to investigate the presence of dark matter in the galactic halo, since the signal should respect simultaneously many peculiarities, and to mimic the signature, spurious effect inside the reaction must not only be able to account for the fully observed modulation amplitude, but also to simultaneously satisfy all these requirements. The pioneer Dama NE experiment has published the 7 annual cycle for a fantastic statistic at that time, and get a fast model independent evidence on the basis of a dark matter annual modulation signature with significant confidence level. It has also published several other results and other approach. It was then substituted by the second generation Dama Libra setup, 200 kilogram of ultra low background sodium iodide. And also this has published many results and details of the experimental feature, and has published the 7 annual cycle for 1 ton, more than 1 ton per year exposure, and has confirmed the evidence, increasing the confidence level at 9.3. In particular, Dama Libra phase 2 was the first case in which we try to lower the software energy threshold. And in fact, the Dama Libra phase 1 has a software energy threshold of 1 keV, while Dama Libra phase 2 has a threshold of 1 keV. But in any case, to disentangle among the different scenarios and candidates, it will be even better to further lower the software energy threshold, as I will shortly mention at the end of the presentation. The upgrade occurred at the end of 2010, and we also have a new high quantum efficiency for the multiplier, and with also lower contamination. I will keep the description of our setup, but just put this, is not just a few statements of main aspect, that to compare, one should know very deeply the experimental details. Here in this table, you see summarized the characteristic of the first 7 annual cycle already published in the past by Dama Libra phase 2 and by the 2 new annual cycle released in July 2021. Here you see that, for example, the parameter alpha minus beta minus squared beta is well consistent with the expected 0.5, which is necessary to analyze the annual modulation in having data taken evening along the years. The calibration over the 4 annual cycle has collected about 1.66 10 to 8 events from sources, and the acceptance window efficiency near energy threshold over the 4 annual cycle has collected about 4.2 10 to 6 events. The exposure with this new data release of Dama Libra phase 2 is 1.53 ton per year, and the exposure of a free experiment is about 3 ton per year. Here you see the usual picture of residuals, where we have now also the last 2 new annual cycles as a function of the time and of the energy. The continuous line is a cosine-like fit with period of 1 year and phase of 2nd June, while the amplitude is the fitted value over all the data. The modulation, the absence of modulation can be discarded with high probability, and now already the data of only Dama Libra phase 2 favor the presence of modulated behavior with proper feature at the level more than 11 sigma confidence level. In this picture, you see the free experiment, the residual of free experiment from 2 to 6 PV, because Dama NE has and Dama Libra phase 1 has a software and threshold 2 PV. And as you see, there is a perfect agreement among all of them, and the confidence level now is above 13 sigma. In the table, you see what you get when releasing also the period and phase in the fit. You see the period and phase agree with the expectation. Here you have also the related confidence level, and here you find the amplitude, which is well consistent among the different experimental situations. We have, as also in the past, analyzed again the rate above 60 kV, which show no modulation. Here you see the amplitude, and also the fact that there is no modulation in the full energy spectrum. Here you see they found the amplitude for each annual cycle, and here you see the difference of integral rate minus the mean value, its mean value divided mean value, which is, you see that the sigma is of order of 1%. It's important, this fact show that there is no modulation above 6 eV, and this account for all sources of background, and is consistent with the studies with the various components. We have repeated using also the data of the 2 last cycle, the investigation of multiplicate events. In fact, multiplicate events correspond to have switched off the dark matter particles. Here you see the result. In red, the modulation we already observed by the fact, and the data are presented as if they have been collected in a single annual cycle here. And in green, you see the multiplicate event, which show no modulation at all. And this result is very important because it corresponds also to have tested the background in the region where you find the signal. And the analysis in frequency has been also repeated. There's also in this case, with the larger exposure, also in this case, the only principal mode appreciable is the one at about 1 year period. Among the many analyses, we also performed the maximum likelihood analysis of the events, and for all the 3 experiments. And again, you see here you have a modulation amplitude versus energy. You see that the modulation amplitude is different, significantly different with 0 in the lowest energy bin. Among the many check and investigation, we have also show here the amplitude versus for each annual cycle versus the annual cycle, and you see that the signal is well distributed over all the annual cycles, which are reported here, and in each energy bin. This is supported by the run test. We have further checked, adding also the new data, if there is a contribution of sinusoidal contribution in the signal. Also, it means the phase is different from about the 2nd June. In this case, with few mathematics, the rate can be rewritten with the new amplitude and the 3 phases. If we were observing a dark matter signal, the new amplitude should be almost equal to the purely cosine-like amplitude, and the 3 phases should be again around the 2nd June. Here you see on the vertical the sine-like modulation amplitude versus the cosine-like modulation amplitude. As you see, just above the 6 kV, you got compatibility with the absence of modulation in both cases, while here you see that for the lowest energy bin, you are compatible with 0 for the sine-like modulation, and you found again a modulation with an amplitude consistent with the results of the other kind of analysis. Here you see the 3 phases versus the amplitude, and here you see again that above 6 kV the phase is determined and the amplitude is consistent with 0, while for the lowest energy bin you are compatible with 2nd June phase, and the amplitude is consistent with the results of the other analysis. Since we have, as I told you, it's very important to decrease the software energy threshold. The sensitivity of an experiment do not depend only on the mass. The sensitivity of an experiment depends on many parameters, and in particular on the exposure, which is which take into account the product of the mass and of the running time. So one can also, instead to increase the mass, continuous well controlled the running time. To show that there is possibility with some small improvements of the Libra phase 2 to investigate down to, we plan 0.5 kV, but we reanalyze all the data of the Libra phase 2 for the 8 annual cycle below 1 keV for an energy of 0.75 keV. As you see, the error is larger because we have not made this improvement, so we should account the uncertainties. But these already prove that you can investigate below and try to disentangle at least among some of the many possible scenarios. The running condition has been regularly controlled for each channel cycle. They are at a level better than 1%, and moreover, no one can mimic the signature. A very deep investigation of all possible systematics and side reaction has been carried out, also in answering to erroneous claim or suggestion by others. And you found here some literature where you can find arguments. In particular, we have also evaluated that we can get Cauchy's upper limit, which are quantitatively extremely reduced that cannot impact on our results. But even more, no one can satisfy simultaneously all the requirements of the signature. Often I go to the comparison. Often you will see something like this. This is a standard reference, which is a stupidity, because as you see, if you compare the region and the things are not always the same, obviously. But this is a way which is not the response of comparison dark matter, because this is just a largely arbitrary, incorrect, and partial exercise, because there are so many uncertainties, both on theory and on experimental aspect, and because the comparison is incorrect, because they are compared by different levels, and also this exclusion plot do not depend on the measured rate, and neither on the many statistical discrimination, sometimes also from subtraction of hypotheses at the background model. And so it's very hard that systematic can be exactly zero, as it is necessary, because the confidence level of this exclusion plot old and the exclusion plot itself old. Recently, there have been get out after 30 years some results on sodium iodide, but obviously realized with a different methodology. In particular, I say just one thing about Cosine 100. The result is model dependent, because it depends on the hypothesis and the modelization of the background, and the observable is claimed by them, that is the constant part of a signal, which is, you understand that the error should be well different. In particular, their model in the first paper missed the contribution of iodine 129 and overestimated the contribution of lead 2010, which affect the reconstruction in the lowest energy part. Then they make some amended, they amended this fact later, but they don't change the exclusion limit, which is somehow surprising. But in any case, let us consider their background model as correct. Nevertheless, the analysis has some fault, because they get null residual in each crystal, even always negative, which is saying something, starting from an incorrect background hypothesis. They miss the iodine 129. But in any case, if we make a data minus model, we get again a negative value, plus or minus a larger error, from which with standard procedure, one should calculate an upper limit on the constant part of the signal from their own data, from their own model, which is less than 0.36 count per kilogram per keV at 90%. So there is still large space for dark matter, and is not in evident contradiction with us. Even more, we do not. Our experiment is not dedicated to the search, to the investigation of the constant part of a signal. There are also other factors that I do not comment here. After me, there will be the talk by Maria Martinez that will be certainly very interesting. However, since she speaks after me, I comment now. Anais has a 5 times larger counting rate in the first bid than Dama Libra phase 2. Moreover, like counting rate is explaining with population other the background that could be linked, which are their words. Some can have origin in PMT, are unexplained. I suppose that is also is linked to subtraction with the Monte Carlo over order of magnitude energy, which obviously is affected by strong uncertainties. Moreover, also the fact that the rate is going down when you go to the model should be treated carefully. Moreover, even a 3 per thousand instability of an Anais counting rate in the 1/6 kV energy region is sufficient to hide the annual modulation signal detected by DAMA. And you can see here, these are the data of Anais, and here you see in green what is the signal of DAMA on this data. Moreover, in Anais, the detection efficiency of applied cut are not periodically evaluated with dedicated calibration at very low energy as Dama Libra do. So there could be also other differences for systematics. And I skip some other observation. I'll just remind that the statistic is low because there are about 100 events in bin of 10 days. That means that one should expect a 10% error per bin. So a fit of this data, including a modulated component, show that they cannot exclude effect at a level of 2–3%, which is much higher than the needed stability to extract our signal. While the search effect requires stability of efficiency at a level of 4 per thousand, in particular for the first energy bin. Analogous consideration can be extracted in the above bin by studying the potassium 40 double coincidence, because the sensitivity get out is about 1%, while it is needed to detect the signal less than 1 per thousand. Moreover, there is a problem, this is general, is for Anais, but many experiments have similar flow. Moreover, there is another difference, that is the difference in quenching factor. If you put together with the measured quenching factor for sodium iodine crystal, you find a large spread and even measure very precise, which are either high or either low, because they depend on the use of the growing technique, on the different olive doping concentration uniform, additives, and more. A clear evidence of different quenching factor is, for example, clearly derived between Dama and Cosine 100 crystal when comparing the alpha over beta ratio. Cosine has a lower alpha over beta ratio, and thus the quenching factor FPV region for recoils also should be lower, even more. Also, however, I want to say that correctly, the Anais paper say that this effect can introduce further systematic uncertainties when comparing with Dama, but you will see, we will hear details from the next presentation. Sorry. Perché non si muove? One moment, please. I don't, eccolo, l'ho trovato. Okay. Just for memories, when you speak about recent sodium iodide, you should remind that there are so many different technical and experimental differences that should be considered. The signal observed by Dama Libra is can be interpreted in several scenarios you find in literature, both our and from other. Sometimes the things are not correct because people fix on parameters which are uncertain and they prefer the value. In any case, you see that also for the case of isospin violating spin-independent coupling, we have a region alloyed, and we have also discussed the fact that even a relatively small spin-independent contribution can drastically change the region in the plane mass of the particle and spin-independent cross-section. There are many other cases which have been investigated. For us, you can see the most recent progress in particle and nuclear physics published in the past year. This slide we already show in the past, always speaking, demonstrating how the models can be, at least in large part, discriminated. You see the modulation amplitudes are the point, while in red you have the expectation for different dark matter scenarios. So as you see, in any case, if you can lower the software energy threshold, you become, at least for some cases, able to discriminate among several of the possible scenarios. We have worked, in the last years to try to realize the possibility to lower the software energy threshold to 0.5 keV, maintaining high efficiency, so you will not have so large error. And we have investigated, we have been founded for R&D, we have investigated various ideas. We started from the possibility to touch the detector itself, but both for technical reason and for general consideration, at the end we have found an alternative strategy in which we use a new miniaturized low background preamps directly installed of the basis of the voltage dividers of the low background photomultiplier, and we use a new transient digitizer with the 14 bit. All the needed material has been developed, tested, reported, been presented to funding agency, and what has been shown that this solution allows us to improve the signal over noise ratio of a factor from 3 to 9, the discrimination of a single photoelectron for electronic noise from 3 to 8, the peak valley ratio from 4.7 to 11.6, and so and other and also the residual radioactivity, since this part to extract the electronic signal is different. In conclusion, we have a model independent evidence for a signal that satisfies all the requirements of a dark matter annual modulation signature at more than 13 sigma confidence level, of 22 independent annual cycle, that means 22 independent experiment by the fact, with 3 different setups for about 3 ton year exposure. The modulation parameters are determined with increase in precision. New investigation on different peculiarities of the dark matter signal is in progress. We have full sensitivity to many kinds of dark matter candidate interaction type, and also to low and high mass candidate. The corollary, oh sorry, apologize, I don't know what happens. Okay. Apologize. No. However, is the last one. Ok, niente, facciamo così. Abbiamo rifatto. One moment, please. No, adesso ecco qua, mi fermo qui. Ok, the corollary model dependent analysis improved the confidence level and restrict allowed the parameter space for various scenarios. Updates are in progress. The Malibra is running. Preliminary efforts to lower the software energy threshold even in the present situation have been done. Effort to empower the Malibra phase 2 has been carried out, and all the needed material is at hand, apart 3 transient digitizer. The detector development and investigation of other rare processes are in progress, and I remind that the group is pursuing the idea to use anisotropic scintillator for dark matter directionality with zinc to state scintillator, and we have measured their response to nuclear recoils at Enea Casaccia. Thanks for attention.
Thank you, Rita, for comprehensive presentation of many years results and comparisons. We have some time for questions. Please, Maria.
Thank you. Thank you, Rita, for your presentation. I will have can you hear me?
Thank you to you, Maria.
Okay. So I have a comment and a question. For the comment, I don't agree in all the statements that have been presented regarding how the instability can affect our results. Anais 112 results. We have performed a lot of the calculus simulations and on this regard and conclude that our results are robust. On the other hand, I agree with you in the importance of the quantum factor measurement. And in my presentation, I will also talk about this. So this is for the comment. Then I have also a question regarding your threshold reduction. I also think it's a very, very important point. I'm curious about if you are, have you think about removing your light guides, the light guides of the photomultipliers in order to increase your light collection?
Thank you very much for the question. At the beginning of our plan to lower the software energy threshold, we speak about the double Libra phase 3, no? Because we planned to effectively to remove the light guide. But at the end, we decide not to do, and we have already tested that we can reach with high efficiency the 0.5 in the TV, the new configuration. Why we did not? As you probably remind, the light guide in our detector is also the optical window of the detector. So to remove the light guide, you should dismount completely the detector, which is an heavy danger for maintaining both the volume and the radio purity. This was the reason why we look for an alternative solution. Moreover, in any case, the light guide reduces the contribution of the photomultiplier. So in principle, I am always in favor of a light guide, even if you have a good, very good photomultiplier.
Okay, thank you.
Thank you.
Thank you again. Let's move forward. Next presentation by Maria Martinez, University of Zaragoza. Dark matter annual modulation with Anais 112 3-year results. Please, Maria.
Okay. So, yeah, okay. Now I can share my screen. Okay, I hope you see my screen.
Oh, yes, it's seen very well.
Okay, so first of all, thank you for the kind invitation to present you the results of Anais 112, the 3-year results in dark matter annual modulation. So this is the outline of my presentation. I will start with a brief introduction and then I will present you the setup of our experiment, the detector performance, and the 3-year results on annual modulation. Then I conclude with our projected sensitivity. So, well, after the Rita's presentation, I think that I can skip most of this. As you know, DAMAS is a very clear annual modulation signal that is compatible with dark matter, that is incompatible with other searches that use different targets. As Rita has said, this comparison is model dependent. We cannot do a direct comparison with different targets. So we need an independent confirmation of the signal using the same target. So this is the experimental situation now. There are many experiments using sodium iodine in preparation or in data taking. Among the experiments in preparation, we have cosinus that we heard about in the next talk, and we have also Sabre and Piccolone experiments. And we have 2 experiments in data taking now that are cosine 100 in Korea, in South Korea, and Anais 112 in Spain. Although Anais 100 started 1 year before Anais, they have less effective mass because 3 of the crystals are not working properly. So now Anais is the experiment that has accumulated more statistics behind Gamma Libra, of course, in the search of testing this thing. So a nice 100 experiment is installed in the Canfranc underground laboratory. The goal, as I said, is give this independent confirmation of the gamma Libra modulation signal with the same target, the same technique, but some different experimental approaches and environmental conditions, as I will mention. The detector is a 3x3 matrix of sodium iodine crystals with a total mass of 112.5 kilograms. As I said, it's in Canfranc underground laboratories in the Spanish Pyrenees. And we started the data taking in August 2017. So the experiment consists in 9 cylindrical sodium iodine crystals forming a 3x3 matrix. The crystals are ultra pure sodium iodine crystals run by Alpha Spectra company, and each one is coupled to a Hamamatsu high quantum efficiency photomultiplier. The crystals are inside the usual shieldings, 30 centimeters of lead and anti-radon box. Then we have also muon vitos. Here I would like also to remind that in Canfranc we have 10 more time muons that in Gran Sasso laboratory due to different coverage. So for us, the muon vito is an important part of the experiment. And then we have also the usual neutron shielding. An important point of a nice experiment is the low energy calibration. Our detectors are equipped with a Mylar window that allow us to calibrate with gamma sources with very low energy down to the region of interest. So we are calibrating with these gamma ray lines, and we are calibrate simultaneously all the modules by means of a radon-free system that allow us to calibrate the crystals without opening the shielding, and we perform these tasks every 2 weeks. Regarding our data acquisition system, we are digitalizing both signals of the 2 photomultipliers of every crystal, every detector, and it's digitized with high precision. We work with 14 bits in the vertical way and 2 gigasamples per second. So it allows us to see very well the individual photoelectrons that compound the signal at very low energy, events of very low energy. For example, here you can see the 2 signals of the 2 photomultipliers corresponding to 1 keV energy deposition. We are also monitoring all the environmental parameters like radon content, humidity, pressure, temperatures at different positions, high voltage of the photomultipliers, and so on. So we can have all these parameters under control. Okay, now moving to the performance of our detectors. During these 3 years, the duty cycle has been excellent. We are measuring around 95% of the time. The downtime is around 2.7%. It's only due to the calibration that we perform every 2 weeks. And the dead time of our acquisition system is around 3%. As regards the gain stability, here you can see the position of the 3 cadmium lines of the calibration over the time for the 9 detectors. So the stability is quite good for all the detectors, except for 2 of them. We have some instabilities at the beginning of the first year due to the high voltage of these photomultipliers. Then we changed it for the second year, and now we have a more stable behavior. In any case, we are correcting this instability thanks to our periodic calibration. As regards the light collection, this is very good for an ice crystal. We are measuring around 15 photoelectrons per keV. And this allows us to put a low threshold, especially the trigger threshold is well below 1 keV. We can check it with these two populations that are present in our detectors, corresponding to sodium 22 contamination and potassium 40 contamination, both of them decay by electron capture, and you can see the atomic excitation in coincidence with the gamma ray in another crystal. So we can tag perfectly these two populations and see these two peaks that we are using also for calibration and for efficiency computation. So this is our analysis strategy. We're following a blinded analysis. We blind from the beginning all the multiplicity 1 events in the ROI of region of interest is from 1 to 6 kiloelectron volts. And we use multiplicity 2 events in the ROI that comes from these two populations that I've mentioned before, and calibration events to tune the filtering algorithms and to calculate the efficiency of this filtering. And we have unblinded 30 days of the first year to do the background assessment. Here you can see our background before filtering the data. Our background, you can see here is high rate because it's dominated by non-bulk scintillation events that we have to filter. How do we do that? So this is our procedure. We apply mainly 2 cuts to remove those non-bulk scintillation events. The first one is based on the pulse shape associated to a sodium iodine scintillator event by means of these 2 pulse shape parameters. So we reject very fast events that are not due to sodium iodine scintillation, and this reduces a lot of background. Here you can see the magenta line is after this cut. Then we remove also asymmetric events that has origin in the photomultipliers. These events dominate the region below 2 keV. Here you can see the effect of this cut is mainly below 2 keV. And then we also remove events happening 1 second after a muon passage, that are mainly the tails of long pulses. And we keep only events with multiplicity 1. So after all this filtering, this blue line is our resulting background. And here you can see the total efficiency for the 9 detectors. You can see that the efficiency is quite high, but good, down to 2 kiloelectron volts, and then it decreases a lot, mainly due to the second cut. We check the stability of our efficiency calculation by these 2 populations that I've mentioned before. The potassium 40 that the 3 keV deposition corresponding to potassium 40 that we expect to be constant in time because of the long lifetime, and near 1 keV corresponding to sodium 22 that we see how decreases with a lifetime in agreement with the lifetime of sodium 22. Both populations follow the expected behavior. As regards our background, we have also developed a model to explain the background in our crystals, considering external components for which we have measured the activity with high purity germanium and the internal contamination of the crystal itself, that we were assisted directly from the data. We have determined that the main contributions correspond to the crystal itself, in particular potassium 40 and sodium 22 that I have already talked about, lead 210, and tritium. So according to our model, this green line is our expectation. You can see that the agreement is very good with our measurement down to 2 kiloelectron volt, then we have a region that we cannot explain with our model. Either we have something in the model that is not, something in the data that our background model is not correctly explaining, or there are some noise events that are leaking or filtering protocols. Here, by comparison, you can see also the gamma background, so you can see how our background is larger than gamma Libra 1. Okay, the good point of for background model is reproduce satisfactorily the time evolution for blind, non-blind population. These are multiplicity 1 event outside the region of interest and multiplicity 2 events in the region of interest. So we will use this background model in the searching for the modulation. So now, sorry, I move to present you the results of ANAIS for the 3 years of data taking. First of all, let me explain the characteristics of the analysis that we are doing. We focus in a model-independent analysis, searching for a modulation. And in order to better compare with gamma Libra results, we use the same energy regions, 2 to 6 kiloelectron volts and 2 to 6 kiloelectron volts, and fix the period to 1 year and the phase to the second extreme. And then we perform a chi-square minimization. As of background is decaying, as you have seen in the previous slides. So in order to do the modulation analysis, we need to model the decreasing background. And this is the function that we use to do the fit, a decreasing background plus a modulation component. And this is the modulation amplitude that we will fix to 0 in the null hypothesis, and we will let free in the modulation hypothesis. So we need a model for the decreasing background, and we have followed 2 approaches. The first one is the one that we use in our first publication for 1.5 years and 2 years. We just assume an exponential decay. And we have these 3 parameters, 3 free parameters for the background model and the modulation amplitude. In this case, for this analysis, we have also added a second model for the background, decaying background. We use our Monte Carlo simulation that we transform in a PDF. So in this case, we have only 2 free parameters related to background plus the modulation amplitude. So these are the results that we have obtained for the 2 models in the rows and for the 2 energy regions that we are checking, 1 to 6 in the first column and 2 to 6 in the second column. In red, you can see the results for the null hypothesis, and in blue for the modulation hypothesis. So in all cases, we have the null hypothesis described for data. In the case of 1 to 6, we obtain a lower Q value than in the case of 2 to 6. In 2 to 6, we obtain something around 0.2. In 1 to 6, a lower P value. I will come to this later. Here in this slide, you can see also the comparison with gamma Libra that you can see here in green. In the lower panel, I show you also the residuals, the result of the fit over the residuals. So you can see here for the gamma Libra modulation amplitude, we obtain in both cases a lower P value. We have also trying to improve the data description. We have added a third model to describe our data, that is to consider the background models individually for every detector. So in this case, we have 2 background parameters associated to every crystal plus the modulation amplitude. So in total, we have 19 free parameters. And this here are the results. Sorry that it's very long, maybe very small to see, but in a while in the next slide I will present a summary of all these results. But okay, again, we obtain with the modulation hypothesis, we obtain modulation amplitude that is still compatible with 0. I would like to bring your attention to the p-values that we obtain in the case of doing separately for every detector. You can see how for all of them in the 1 to 6 keV region, results are very good, except for 2 of the detectors. So it points to it's a key to say that maybe we have some noise in some of the detectors that is filtering, is leaking or filtering protocols. So now we are working in improving the filtering protocols. We are working with some machine learning techniques, and we have already some results. So we expect to release these results very soon. Okay, this is the summary of what we obtained. In the case of the results with the 3 models are compatible, and in all cases, the data supports the null hypothesis. We obtained the best result for the better model, that is the model which gives a more precise description. The model in which we fit independently the background of the 9 detectors. So it's the one that you use to quote our final result. Here, this plot, you can see a summary of our results in 1 to 6 kiloelectron volt and 2 to 6 kiloelectron volt compared with the Dama Libra modulation amplitude. So the black points are nice results. You can see that within the uncertainty are compatible with 0, and the bands are or current sensitivity, 1 sigma, 2 sigma, 3 sigma. So currently, our best fits modulation amplitude are compatible with 0 at 1 sigma and incompatible with Dama Libra result at 2.6 sigma or 3.3 sigma, depending on the energy region. And our current sensitivity is 2.5 sigma or 2.7 sigma for the 2 energy regions. Well, we have also performed some inconsistency checks. For example, we have studied the effect of the time binding. We have studied different bin sizes and found that the effect is negligible. And we have also performed Monte Carlo checks to study if the fit is biased or not, and in fact it's unbiased. Oh, sorry. We have also performed a free analysis, an analysis with the phase free. But in this case, we have checked that, as expected, because the fit is non-linear in the parameters, the fit is biased. We have calculated the bias to be proportional to the statistical, to the standard deviation of the modulation amplitude. Anyway, here you can see the results of this phase-free analysis. The points are nice results. The red cross are Dama Libra results. So else in this case, considering the bias, the results are compatible with the absence of modulation and incompatible with Dama at something around 3 sigma. We have also performed a frequency analysis. You can see here the results. The conclusion is that no statistically significant modulation is found at any frequency. Okay, so just to finish, let me present you our expected sensitivity that we have calculated according to our expected background, the efficiency estimate, and this error, and the lifetime distribution. And we are plotting it here as the ratio between the Dama signal and the standard deviation of our modulation amplitude. This study has been confirmed by our measurements. So here you can see the results that we obtained in the 3 data releases that we have performed so far for 1.5 years, 2 years, and 3 years. So the data is confirming our sensitivity projection, that is to achieve something more than 3 sigma sensitivity in the 5 years of data taking that are scheduled for the experiment. Okay, and yeah, after that, let me also talk a bit about the effect of the quantum factor, to put as the question if this is really a model independent test of the Dama Libra result. So the answer is that using the same target material is in fact a direct comparison, but in electron recoil energy. So for those of you that are not familiar maybe with scintillator, let me remind that in a scintillator, an electron recoil produce much more light than a nuclear recoil of the same energy. As we are calibrating our spectrum with gamma sources, our results are given in electron equivalent energy in order to be interpreted as dark matter, so as nuclear recoils. We have to correct them with what we call the quenching factor, which is the ratio between the signal produced by a nuclear recoil and an electron recoil of the same energy. Here you see an example of the effect of the quenching factor. This is the signal that you would expect in nuclear recoil energy for a certain WIMP. This is what you are really measuring in electron equivalent energy when you apply a certain quenching factor that you have to measure in your data. So the response of different detectors to dark matter particles could differ if the quenching factor is different. And in fact, there are some spread in the measurements of the quantum factors performed so far with sodium iodine scintillator. Here you can see the experimental situation. Dama Libra has measured constant values for the sodium at around 30%. Other measurements are giving lower values. But the main question is, does this quantum factor depend on the crystal, on impurities, value level, crystal quality, or is this spread in measurements due to other systematics? Okay, yes, we think that this is a really important question. So we are working together with Cosine and other groups in measuring the quantum factors of anise and cosine crystal and other crystals of different qualities in the same setup. We have performed this measurement that with the different crystals in the same setup, and we expect to have the results very soon, and we expect that this will throw some light in this issue. Okay, so this is just the end of my presentation. Yes, this is the summary. Just remind you that ANAIS is taking data since August 2017. Up to now, we have accumulated more than 300 kilograms year exposure, and by now our results are compatible with the absence of modulation and incompatible with Dama Libra with a sensitivity of something around 2.5 sigma. We will continue measurement up to the 5 scheduled data taking period that will be in about 1 year from now. In the meantime, we are also working in improving our filter protocols with machine learning techniques, and we are analyzing this quantum factor on sodium iodine crystal to discover uncertainties in the comparison. We also plan to make ANAIS data public after use that will be in 1 year from now. Okay, this is all. Thank you very much for your attention.
Thank you, Maria, for very interesting comparison, interesting results with the test. And I think we may have a few minutes for discussion. Rita has a question, please. Rita, can you hear me?
Okay, I will make just a few questions. First, the analysis procedure are not the same, as can be easily understood. The kind of detector are not the same. These are realized in a different way. Third, it's not that we measure constant. It's the fact that we use a different procedure that was used also by Egiri at that time, which has even a larger quenching factor for their for their detectors. This was integrated over this region. There are uncertainties is much larger than you see. So the quenching factor are different. It's not that we have both sodium iodine, because this, when you ask for this kind of specification, you should give all the differentials which exist in the production of a detector, in the material, and so you can also explain something like this. Moreover, also the growing procedure which give low value for quenching factor, as you see, they are not only systematic, they are incompatible experiment among them. This cannot be only systematic, it's differentials in the production. And even more, I say, here also you miss the results of AGIRI. In any case, I also want to say, so it will be interesting that you will measure the quenching factor for this detector, but it changes nothing to the fact that the detectors are well different in construction and in features. The other things I want to say is quite strange that you cannot exclude our signal, but you claim that you are inconsistent. I found this very, very funny, I can say. Okay, for now, stop. Thank you very much.
Okay, thank you, Rita. Let me also comment.
The presentation should be more linked to the data. I have only a suggestion. Do less Monte Carlo and enter more in the laboratory. So maybe you understand the nature of the unexplained events best.
Okay, thank you, Rita. Yes, for the quenching factor, yeah, I agree with you. It's not only the experiment that we have measured, that we have performed with to be a step forward, the comprehension of the issue. We have also performed a neutron calibration in our crystals, so we will combine this data with the measurement to give more real, in the sense of in the same crystals, measurement of the quenching factor. Yeah, but in fact, I think that it's a very important issue, and more effort should be dedicated to clarify the quenching factor.
Yes, but this is not discovered in 2020 or 2021, because this data, as you see, were collected from early 90. You miss here also, for example, the GD data. Later, and are measured with different detector and with different procedure for growing and with different measurement. When you say that we say is constant, this is a reality averaged because it's measured in another way, not with is measured by using a source, a neutron source, not a generator. You understand? So you make a convolution of a spectra. This was invented as first by AGIRI. Okay, thank you.
Okay, thank you, Rita.
Thank you again for the talk. The next and the last talk in the plenary session of today is a talk by Felix Wagner, Institute of High Energy Physics, Austrian Academy of Sciences. Cosinus dark matter search with cryogenic scintillating sodium iodide colorimeters. Wagner, Felix, please.
Thank you, and thank you for the opportunity to speak at this prestigious conference. I will share my screen now. So today I'm presenting on behalf of the Cosinus collaboration. Cosinus is a dark matter search with cryogenic sodium iodide detectors. To be specific, it's a dark matter direct detection experiment. For dark matter direct detection experiments, we want to measure relic dark matter particles scattering off a detector material. And for this scenario, we can calculate an expected differential recoil rate with the formula shown here. There are several factors contributing to the overall rate. For one, from particle physics, the cross-section between dark matter and the detector nucleons. and from astrophysics, the velocity distribution at the position of the detector. And exactly for this velocity distribution, we expect modulation due to the Earth's movement around the sun. The modulation should be around 5% of the total signal. All of this we have heard already in the two previous talks. And what we also have heard is that the Dharma Libra experiment observes a signal for more than 20 years now, which is very much consistent with all these expectations for a dark matter signal. This is the energy spectrum from the publication in 2018, where they lowered the energy threshold to 1 kilo electron volt electron equivalent, and their measurement principle is to measure the scintillation light of sodium iodide crystals with photomultiplier tubes. What is not possible is an intrinsic particle discrimination between nuclear and electron recoils, because only one channel, namely only the scintillation light, is measured. With this measured signal, there is a confidence level of 12.9 sigma for an exposure of around 2.5 ton years for 20 annual cycles for this modulation. So there is no doubt that this modulation exists in the data. The big question, which was discussed already for the past hour, is how is this compatible with the results of other experiments? And here we see a dark matter landscape from the APEC report in 2021. These exclusion limits are based on standard scenario assumptions. And here we see that many experiments have exclusion limits lower than the two Dharma islands, especially the cosine experiment and also the Anais experiment, which both use the same target material, sodium iodide. Also, the Sabre experiment is planned to achieve the same goal. So the mystery has to be somewhere in the uncertainties, and one of these uncertainties, which was discussed right before my talk, this was actually a very good transition, are the quenching factors, because the nuclear recoil energy scale, when one is only measuring scintillation light, then the nuclear recoil energy scale depends on assumptions or measurements of these quenching factors. And this is where the experiment ends the stage. Namely, the Kosinus experiment will measure a heat channel and a light channel, so not only the scintillation light, but also the total energy deposition by particle recoils inside the sodium iodide. For this, so this means we have an automatic calibration of the nuclear recoil energy scale. And by using the same target, we are also immune against material dependence. And by operating sodium iodide as cryogenic detector, we will achieve a very low energy threshold below 1 kilo electron volt nuclear recoil energy threshold. To say something about this detection principle, these are cryogenic calorimeters. The principle is to operate a small crystal of only about 50 grams at cryogenic temperatures. This is around 10 to 20 millikelvin. And these low temperatures, one individual particle recoil produces a heat signal inside the crystal, as well as a signal of scintillation light. The heat signal is then measured with a sensitive thermometer. For this, we use TES, transition edge sensors. And the scintillation light is collected by a light detector. This is a more realistic sketch of how such a detector looks like. Actually, this is this is our baseline model, which is planned to for the finished setup. So this is the sodium iodide target crystal, and it is surrounded by a beaker-shaped silicium light absorber. And both on this sodium iodide target crystal as well as on the light absorber, there is a TES, it's a very sensitive thermometer measuring the recoils. So with this, we measure for one recoil two signals, namely the heat signal inside the crystal and the light signal. And as we know, the produced amount of scintillation light depends on the type of recoil. Namely, a nuclear recoil produces much less, roughly by a factor of 5 to 10 less amount scintillation light than an electron recoil. And this fact can be visualized. For this, we use the so-called light yield parameter. The light yield parameter is the ratio of produced scintillation light to produced phonon energy. And this parameter plotted over the total energy, the total deposited energy. So this is the sum of the deposited light energy and the phonon energy. This light yield parameter, this then we call a light yield plot. And in this light yield plot, we can see specific bands for specific recoil types. Especially here we see the large band for all the electron recoils, which is calibrated to be on a light yield around 1. And then we have at much lower light yields the nuclear recoil bands. And there we can even discriminate between a nuclear recoil band for sodium and for iodine. This is all this data on this plot is simulated. So this here we see the electron recoils, and down here we see how a dark matter signal would look like in these bands. This is the signal compatible with the sodium islands the sodium islands from Dama in the dark matter landscape. And this gray area, especially this lower end of the gray area, is the energy threshold of experiments that measures only scintillation light, as for instance, Dama does and Anais does. So in the Dama data, we would see everything above the lower end of this gray area. And here we see that there would be some of the dark matter events inside this, above this threshold, and therefore visible for a poor scintillation light experiment. But what is not observed is all these dark matter events, which would very well be observed by an experiment like cosinus, which measures the heat, the produced heat directly. So with a cosinus-like experiment, we would observe much more signal than with a pure scintillation experiment. We have a very detailed detector response model for these cryogenic calorimeters. This was put forward by Franz Probst in the 90s. In this model, we model the detector as an equivalent thermal circuit. This is a standard method in electrical engineering, where each thermal component is modeled with heat capacity and with thermal resistances between the components. And then a differential equation describes the system of the detector, depending on the power input. This power input is the particle recoil in one component of the detector. For a standard detector, we would have two components, namely the crystal phonons and the thermometer electrons. And if one models this power input with an exponential decay, which is typical for particle recoils, then one can even calculate an analytic solution for the temperature rise inside the thermometer after a particle recoil. And this analytic solution is written down here. It has two components, one non-thermal component and one thermal component, and 3 time constants, depending on the rise and decay times. And the response of the detector looks like a pulse. This is a recorded pulse from one of the detector prototypes. And this analytical model can be fitted very nicely to the pulse. And with this, we can even disentangle the different contributions, the different energy contributions of this detector response. For a sensitive experiment, we also need sensitive analysis methods. So we plan to use a continuous data taking. This enables fine-tuning of the energy threshold, and also several simulation methods, for instance, for efficiency events or for labeled data sets for machine learning applications. We have 2 independent software packages for cross-checks and validation. One of them is based on Root and C++, which are standard tools in in the particle physics community. The other one, which was produced recently and published recently, is an open source Python package, which focuses especially on machine learning based analysis. This is published on the Python package index and on Zenodo. So for instance, here we see some simulated events because there are in every measurement not only clean and nice recoil events, but there are also many artifacts, and discriminating these artifacts from the proper physics data is especially important if one works with very low thresholds where everything gets very noisy and very messy. To come to the timescale of the Cosinus experiment, the setup is in construction already by today, and it will finish in the coming year. The detector development is ongoing. The final detector development, the final detector design will be finished next year. Then we will produce 12 detectors so that we can start data taking in 2023. And from 2023 to 24, we will collect 100 kilogram days of data. And with this amount of data, there is a publication from in collaboration with Felix Karlhöfer, which verifies that with this amount of data in 2024, this will be sufficient to validate the signal claim of Dharma Libra in a model independent way, especially not depending on any quenching factor assumptions. After this, from 2026 ongoing, we'll investigate any annual modulation signatures with Cosinus. To come to the current developments and current status of the experiments, the Cosinus will be located in the Laboratorio Nazionale del Gran Sasso in Hall B. In Hall B, there is also the Xenon 1T experiment. So this is a picture from the hall from above, and here this construction site is the place where Cosinus is built. This is a picture of the setup when it's finished. Especially here we have the water tank. Inside this water tank there will be located the detectors. The water tank acts as an active and passive shield. For this water tank, we published just a few weeks ago an archive simulation study for the exact size and properties of this water tank, and the results of the simulation studies were that we use a cylindrical water tank with 7 meters height and diameter, a 8 centimeters copper layer as a shielding around the detectors, but no specific lead and polyethylene layers, which are commonly used to provide a shielding against gammas and neutrons, because the water itself provides already enough shielding against neutrons. As you can see in this plot, where we plot the fraction of surviving particles above the water thickness, there is only one significantly surviving background, namely the muon-induced neutrons. And actually, neutrons are a very harmful background for our experiment because we cannot discriminate them with the two-channel readout method from dark matter particles. But for this reason, and these are muon-induced neutrons, for this reason, we will equip this water tank with photomultiplier tubes, because the muons produce Cherenkov light inside the water. This Cherenkov light is then measured by the PMTs, and with this we can build an active veto against any muon events. So we also have a method to deal with this background. Now we'll say something about the current detector development. So our latest published results was in 2018, and the measurement was in late 2017. Back then, it was possible to operate sodium iodide as a cryogenic detector, namely a 66 gram sodium iodide crystal with 1.3 kilogram days of exposure. This was the design which I schematically showed already in the picture before. And here there are two photos of this detector. This is the sodium iodide inside a copper housing with a glued interface to the transition edge sensor. And this is the beaker-shaped light detector put on top of the sodium iodide crystal. These are pulses that we observed in this measurement, and we learned something peculiar about these pulse shapes by using the standard two-component pulse shape model, the detector response model, which I presented before. There are large residuals in the fit, But by adding an additional thermal component, these residuals are almost gone. And this is very much in agreement with the original detector response model, because in the current design, we have one additional component which is not modeled in the detector response model, namely this carrier crystal. This carrier crystal itself, on top of which the TES is mounted, is an additional component and produces one additional component of the detector response. Back in this measurement, we faced several challenges that were very well expected with sodium iodide crystals. So the challenges are especially the hygroscopicity of the crystals, so they can only be handled in glove boxes, also a high debye temperature and high potassium contaminations. For the last one of these issues, we're now building super pure crystals with the SICAS Institute in Shanghai. So this third of the three issues we have resolved by today, but back then it was a huge challenge. We had an energy threshold of 8.2 keV, which is still above the anticipated energy threshold of only 1 keV. But it was possible to operate sodium iodide as a cryogenic detector, which is already a huge step. And we learned a lot about the crystals and the methods we need to analyze the measurement. Especially, this is a current development and it's not yet published, but the paper is in preparation. Vanessa Zema refined this detector response model. Especially, there was a second part added, which models the scintillation light of the absorber crystal, which is recollected by the carrier crystal. This is an effect which was not observed before with this type of detectors. And so we can disentangle this detector response in one phonon part and one light part. And by taking only the phonon part, this is the small blue curve here, which doesn't really make a peak. By taking only the phonon part for the energy reconstruction, we can much better discriminate this gamma band from the neutron band. So in this plot, this is a measurement where an NTD was operated in parallel to the TES on the absorber crystal. So we had an additional verification, and with the NTD, it was possible to take high energetic neutron events. And therefore, these are the red dots here. And we can see, if we reconstruct with this method, the energy and the light yields with the TES measured data, then we see these two bands, this gamma band and this neutron band. So this is one step further for using this baseline design for discriminating different types of events. And a very current development, we're intensively working on lowering the energy threshold. And for this, there was an idea put forward by Matt Pyle in 2015 called the REMO TES. And the idea of the REMO TES is to use no carrier crystal for the TES, but a gold wire to connect the TES to the absorber crystal. This especially provides a good coupling of the electrons and phonons inside the sodium iodide and the gold. And the carrier crystal, which we still need to, because the TES has to be located somewhere, but this is then only an athermal component. So this would not contribute to the detector response. And by this design, we expect to measure a much lower energy threshold. We have tested this with silicium and tellurium oxide. For a silicium REMO TES, we get a threshold as low as 300 electron volt, with tellurium oxide about 1 keV. And as a very recent information, just this very week, we are measuring in the Cryo2 facility of Rest at the Max Planck Institute in Munich, the first sodium iodide REMO TES. So here are some pictures of the detector, and this is from the live data acquisition. This picture was taken just yesterday, the very first pulse we observe in the sodium iodide. So it is possible to build a REMO as sodium iodide REMO TES. And this is already a huge breakthrough. And I personally am very curious, and we all are very curious for the coming weeks when we will analyze this measurement, and we certainly hope to do another breakthrough in terms of energy threshold with this sodium iodide hemothiolase. So to come to a summary, the use for working dark matter sodium iodide creatine detector is first of all to show that it can operate as cryogenic detector at all. Then this concept of the beaker-shaped light detector to have radio pure sodium iodide crystals, and this extended pulse shape model for a correct energy reconstruction. And this all is done. What we're currently working at is just further lowering the energy threshold. In summary, COSINUS provides particle identification on an event-by-event basis, a lower energy threshold for nuclear recoil, precise energy information independent of the event type, and the same sensitivity at smaller target masses, and brings therefore everything we need to validate the DARMA claim. And this will be 3 years from now when we collected 100 kilogram days of data. To show who everybody is working on this, so these are our collaborating institutes. I'm from the Institute of High Energy Physics in Vienna of the Austrian Academy of Sciences. And this is a picture of our last collaboration meeting, which was held online, as everything is these days, as well as this conference. Thanks a lot for your attention, and I'm happy to answer any questions now.
Thank you for nice presentation. I see the hand by Rita. Rita, please.
Okay, I thank him to want to validate or invalidate our 20 years evidence with 1 kilogram per year, no, 1 kilogram per year. But I have a question more simple and more technical, if you could help me. As I understood, you are claiming that you use sodium iodide in millikelvin, and you have no breaking going down in temperature. How you have solved this problem? Secondly, generally, when you are at a very low temperature, the scintillation is lost. And I know from the Spanish old result, they say that maybe it open another lambda at low temperature. How you solve this? Finally, I have correctly understood that you plan to put this, the bare crystal in, in nitrogen, in air, what you want, when making the measurements.
Okay, I will first answer the question about the loss of scintillation.
I also want to remind you that there is no standard assumption in the erroneous comparison that you are propagating together with many others. However, please, the technical question.
Okay, I will start with answering the question about the loss of scintillation light at low energies. Of course, there's less, we can see here in this plot, these bands widen up at a lower total energy. And of course, if we observe an event which has a light yield of, let's say, 0.5 at exactly a threshold, then we can, for this one event, not exactly say if this belongs to the sodium band or if this belongs to the gamma band.
Sorry, I was probably not clear. More simply, which is the lambda of the scintillation light at this temperature? This is crucial. You are claiming that is the same than we are doing, at least to know if we are observing the same scintillation.
Yeah, but in principle, with this band fit method, we can very well observe where how these recoil events behave at lower and lower energies. I mean, we can see in this plot the bands developing into low energies. We can see that the band widens up. We can
yes,
also...
but I can see if the lambda is in a region which is realistic for the temperature and acceptable for the collection. Oh, however, it's okay. Just I want, please answer to the fact that you have this choice to have no housing at all, if I correctly understood.
We will have no lead and no polyethylene layers, but we will have a large water tank shielding the experiment. And the result of our simulation studies was that this water tank already provides a better shielding against neutrons and gammas than the lead and polyethylene layers.
Probably I was not clear. The sodium, I don't know, is not thallium doped, this one? Because you never write thallium doped.
Yeah,
so
exactly.
it's pure sodium iodide?
Yeah.
Or not?
Yes. This is sodium iodide, yeah.
Without thallium?
Yes, exactly, yeah.
And so it's also for this is a completely different scenario. But I say, okay, to close because it will be too long. It's important to know the lambda of the scintillation, to know if the scintillation is there, how efficiently it scintillates, so the realistic collection and the number of events you get out. And also all the other things related to the fact that really you can collect light at millikelvin as you are climbing from simulation, if I correctly understood. In any case, it will be bare, pure sodium iodide without housing.
It will be, yes, so it is inside this, this is the sodium, I mean, this is even a picture of the detector prototype. This is the sodium iodide, and here around we have only a copper housing, but this is placed inside the shielding of the water tank.
So this is not sodium iodide thallium doped, but is pure sodium iodide.
Yes, yeah.
For example, in normal temperature, sodium iodide has an extremely low scintillation efficiency. Increase at millikelvin. Pure sodium iodide is very poor in scintillation at normal temperature. Vabbè, okay, thank you. It's too long a time.
Thank you for your feedback.
Sì.
So thank you. If we don't have more questions, we'll thank again the speaker and thank all the speakers and participants of this plenary session. So thank you for participation, Alexander Ivanovich.
Okay, well, thank you very much. Well, I would also like to thank all the speakers and the convener, the chairperson of this session, the plenary session dedicated to dark matter. And indeed, the problem of detection of dark matter is one of the hot topics in the present fundamental physics. The results of different experiments seem to be inconsistent with each other. And this can be considered at a very positive point, stimulating further consolidation of efforts to achieve the truth. Well, I would like to thank all participants of this.
Sorry, Alexander, but the inconsistency should be real. Now, so you are comparing two real identical things and they are different. But if the things are different and you compare if they are equal, this is just a wrong comparison. Apologize.
Okay, well, okay. Thank you for your remark. But if you just, I just say seem, yeah. This I just add results are different. Seem to be different. Yeah. Okay. Well, in any case, the future is very attractive, and we hope that very soon, once all these issues will be solved. And
sorry, Alexander, I like you very much. Let me say, but this means that we know which is the candidate, the detector are equal. That is no, we do not know. Really, this field should be addressed with much more, in my opinion, open mind and less lobbystic effort. Sorry.
Okay, well, we as organizers, we appreciate all these discussions and all new results that are shown and discussed. So this is one of the goals of these kind of events. Yeah, and I would like to thank everybody for very active discussion and presenting new results. And we hope that in the next Lomonosov conference, we shall have additional information, and all these issues will be studied. And finally, I think that our goal just that different people just agree all together on the statement. So this is the goal of events.
You are right, but it should be done in a correct way.
Yeah, sure, of course.
I sometimes see things erroneous repeated for to climb things out of reality. In any case, I agree with you. Thanks to all, because all these strange things demonstrate that 30 years ago, when I pushed to make the experiment, was in this field, this was a very new idea. And now all people want to do this. Thank you for all, Alexander.
Okay, thank you. Thank you for all these discussions and presentations that are very stimulating indeed. Yeah, okay. Thank you once again. So, and we shall meet on the parallel sessions. There will be 2 parallel sessions at 2:15, please. Thank you very much. Thank you.
Well, video.
Sorry, but I can't share my video, my desktop.
Yeah, please, we are going to start the session, and as first speaker, we have Censo Caracciolo, who will introduce the crystal scintillator for dark matter directionality approach. Thanks, Michelle. Please respect strictly the time allocated for your talk. Thank you.
Excuse me.
Can you hear me?
No, you should upload so to do something
hear
with your
me?
microphone. Yeah, now it is okay. Yeah.
Okay.
Yeah, thank
Sorry,
you.
excuse me.
Yeah, thank you. Yeah, please. Okay.
Excuse me. Okay, thank you very much, the organizer, for this nice conference. I will talk about the some specific technique in order to investigate the so-called directionality approach. We know indirect search for dark matter particle in galactic halo, a very powerful tool is the use of a model independent signature in order to emphasize the signal with respect to the background. The main one of this is the so-called annual modulation, already successfully exploited by Dama collaboration. But we have also other secondary effects. For example, we have the diurnal modulation due to the Earth revolution around its axis, but also a daily variation of the interaction rate due to the different Earth depth crossed by the DMP particles. And this is work well only for enough high cross section. Instead, there is beside this, there is another interesting tool, the directionality approach. This is based on the study of the arrival direction of dark matter particle and the Earth motion respect to the galactic frame. The idea is to study the direction of nuclear recoil induced by such type of the candidates. I mean the nuclear recoil induced by this interaction. Thus, is important to exploit this signature, develop a direction sensitive detector. In principle, a good detector could be a low pressure time projection chamber. because with this, because the nuclear recoil in the very low pressure gas mixture is of the order of millimeters. Instead, as told also for news, the length of the range is of the order of micron or also less, depending on the energy deposited. But this technique, unfortunately, have some several disadvantages. For example, it's necessary an extreme high operational stability. The radio purity technique is not measured for this type of detector, and it's necessary a very high energy resolution, spatial resolution, angle resolution, and a very large detector size. To overcome these problematics, our group follow a new approach based on the use of the anisotropic scintillator. Originally, the idea was proposed in 1992 using anthracene crystal scintillator, but recently it is revised using more promising crystal scintillator, a zinc tungstate crystal scintillator. Why this is very, what mean the detector have anisotropic features? If you look in this picture, you can see the in this axis the quenching factor of alpha particle with the energy in the MeV region, electron equivalent in the MeV region. But the important thing is that the quenching factor depends on the particle impinging direction with respect to the crystallographic axis. This behavior is not present for electromagnetic excitation, as for example when the scintillation is induced by gamma or electrons. Moreover, not only the quenching factor show this behavior, but also the pulse shape, or in case of heavy, in case of nuclear recoil of heavy particle, has the same same anisotropic response. Thus, the zinc tungstate crystal scintillator is interesting because it show very good anisotropic features. We can have a high level of radio purity and a very good light yield in order to approach very low energy threshold. But we can have also good stability in the running condition, and moreover, because the presence of 3 different nuclei, we can have sensible to a very large range of dark matter, of mass of dark matter particle, and we can build in principle a crystal of few kilograms. But we need some R&D to understand if the idea is really possible. For example, we are in progress different R&D considering the increasing of radio purity level, improving optical properties, all this in order to decrease the energy threshold, but also to study the nuclear recoil in the energy of interest for dark matter particle. In particular, I skip this slide. In particular, here is reported the new data acquired to check the anisotropic response when an alpha sources irradiate the crystal scintillator. In red and in colored point, there are the new our new measurements. And in black points, instead we have the measurements already shown in the first slide here. Just for example, you can see the energy distribution of the three nuclear recoil that are these three points. Then we confirm at the level of the alpha energy the anisotropic future. Moreover, a new campaign of measurements using a neutron gun of 14 MeV in the Enea Casaccia have been done in order to study the nuclear recoil on oxygen. And the idea is to use a very small crystal scintillator in zinc state to minimize the probability of multiple scattering of neutron inside the crystal. The crystal was coupled with two photomultiplier, and the scattered neutron was detected by a neutron detector. Two neutron detectors. Then fixing the angle theta, we can know the energy released by cinematic consideration in the crystal. Here is reported two examples of the signal acquired. In particular, here is reported the energy distribution of the nuclear recoil release in zinc state in case the scattering angle is 18 degrees, and the nuclear the beam of the neutron is parallel to axis 3 and axis 1. In red is reported the signal that in blue instead is reported the random coincidence. The analysis published recently in 2020 show a very high anisotropic property at level in this energy range, few hundred keV of nuclear recoil on oxygen, at level of 5.4 sigma of confidence level. But I would like to spend just a few words. How can we profit of the anisotropic scintillator futures? In case you can assume a very simple scheme of anisotropic crystal scintillator. Here is reported in particular the expected signal counting rate in a specific energy range versus the time, and we underline some of the many parameters needed to assume that are model dependent or depending on the crystal property. Okay, here there are some information about the halo model considered, but not only astrophysical consideration, but also nuclear particle, dark matter particle consideration. Here is reported instead the quenching factor, which output is depending on the laboratory frame. Then in this way we can simulate the anisotropic future of the quenching factor for nuclear recoil in these crystals. And here is reported two simple examples in case of a cross-section of 5 times 10 to minus 5 picobar with a 10 GeV mass or 100 GeV mass, and in the energy region of 2-3 keV and 6-7 keV. Here is reported the counting rate per kilogram per keV per day, and here is stated the days. As you can see, you can recognize here the typical shape of annual modulation. Instead, here along the sideral day, you can profit of the different counting rate due to the Earth revolution, and thus the quenching factor that is varying during the day. The same behavior is present also for this other example, but this is just an example having assumed a given scenario as briefly told before. In particular, if you consider a matrix detector with an overall mass of 200 kilograms of zinc dusty crystal scintillator, 5 years of data taking, and an energy threshold of 2 kV threshold, 2 kV, here is reported the sensitivity reachable in case you have for this model, in case you have four level of background, and just for comparison, in the red, in the colored area are reported the allowed region inferred by coloral analysis of the Dama Libra phase 1 data. Now we know the statistics is very high, is higher than this confidence level. Just a few words for the progress, for the future. We are in progress other work in order to try to increase the light yield. For example, studying the light output versus the operational temperature. And we are in progress some measurement with an already done little cryostat, but we want to also match better the response, the spectral response of PMT with the light emission, the spectra emitted by the scintillator. And we are in progress also other neutron measurements in order to study the energy recoil lower than 100 kV, but also for the other two nucleus, tungsten and zinc. So in conclusion, this approach, the decoctionality one, can give complementary information on the nature and the interaction type of some dark matter particle candidates. The zinc dusty crystal scintillator is a promising detector in order to investigate such approach, because they show a very good anisotropic properties. And recently we have proof these anisotropic features in case of oxygen nuclear recoil in the energy region of some hundreds kV with a significance of 5.4 sigma of confidence level. And thank you for your attention.
Okay, thank you, Vincenzo, for the presentation. There are questions, and to be in time, and there are questions from someone. No? I don't know if you have evidenciated the good things, for example, with respect to the approach we measure the tracks. In this case, with this approach, one merit is not to have the necessity to measure a very short tracks.
Yes, in this case, we have overcome this problem because the crystal scintillator show this type of crystal scintillator show this anisotropic feature. And this is the basic the idea beyond this technique, this solution to the problem of the directionality approach.
Okay, there are some other questions. No. Okay, if not, we thank Vincenzo, and we go to the presentation by Lernert Tormaelen. I hope to have said correctly, which will discuss about the hidden photon dark matter in the light of xenon quantum and stellar.
Okay, I'll try to share my slides. I hope you can see my screen and that you hear me okay.
Yes, it's okay.
Okay, so thank you, first of all, for the invitation to speak here today. I'm Leonard Tomé, and I'm a PhD student here in Heidelberg of Jörg Jeckel, and I will talk about the possibility that the xenon one-ton axis could be caused by hidden photon dark matter, and also how stellar cooling observations turn out to be an asset of this explanation. And all of this is based on a short note that we published in collaboration with colleagues from Aachen. So first, let me remind everyone what the xenon one-ton axis is. Last year, the Xenon collaboration released their latest result of the xenon one-ton experiment. And interestingly, in this experiment that was originally designed to detect nuclear recoils, an excess in the electronic recoil events was found. So the associated energy was at the lower end of the sensitivity between 2 and 3 keV, where the energy resolution is quite poor. But nevertheless, the statistical significance of the signal after subtracting all the background came out to be 3.5 sigma, and that was quite enough to generate a lot of attention. Unfortunately, xenon one-ton is not running anymore because they are currently upgrading to xenon n-ton. But on the other hand, that means that we will very soon have more data from an even more sensitive detector, which could confirm or correct this axis. So following the publication of this result, many different explanations were proposed, of which I list only a few here. Notably, they were not able to definitively rule out additional background. So tritium contamination in the detector could actually also explain the signal, even though the xenon collaboration themselves regard this as very unlikely. I will focus on a specific explanation, which would be that xenon one-ton observed hidden photons. Even though all of this is speculative, admittedly, it is absolutely interesting and necessary to discuss what the assets or downsides of certain explanations are, and what we have to do to either confirm them or to rule them out. So in the course of this talk, I will address 3 key questions. Firstly, whether the xenon one-ton axis can indeed be satisfactorily explained by hidden photon dark matter. Secondly, if a hidden photon of the kind required to explain the xenon signal is a viable dark matter candidate. And lastly, I will discuss how the hidden photon compares with stellar cooling observations. So briefly, what is the setup, or what is a hidden photon at all? A hidden photon, or called dark photon, is the gauge field of a new U1 symmetry. We denote this new field and its field strength tensor here as X. And we assume that this field receives a mass term either through a Higgs or Stückelberg mechanism. So that and in addition, the hidden photon is kinetically mixed with the standard model electromagnetic field by a small kinetic mixing parameter epsilon. When we apply a suitable field redefinition, we can trade this kinetic mixing for coupling of the hidden photon to the standard model electromagnetic current, which we denote J here. So in essence, the hidden photon couples just like the standard model photon, but with a suppression by the small kinetic mixing parameter. So as a result, the absorption of non-relativistic hidden photons in xenon can be related to the photoelectric cross-section. The result is shown here, and the corresponding rate, scales with 1 over the mass of the hidden photon, because we assume that the hidden photon makes up the full dark matter density. Because the dark matter is non-relativistic, the absorption would produce a monoenergetic peak at the mass of the hidden photon. And this is then only smeared out significantly by the detector resolution, which, as I mentioned earlier, is only about 20% at the energy range that we are interested in. So we then fitted a hidden photon signal to the observed axis and get this nice looking result. So there's a Gaussian peak on top of the background at a couple of keV in energy. In the hidden photon parameter space, with the mass plotted on the x-axis here and the kinetic mixing on the y-axis, we find the best fit point at a mass of 2.8 keV and kinetic mixing of 8.6 times 10 to the minus 16, so a tiny mixing. We were happy to see that this result was confirmed by other papers, but we also calculated the 1 and 2 sigma certainty limits, which are also plotted here on the right. the global significance of this signal is just about 2 sigma. This is less than, for instance, the solar axion interpretation, even though that's ruled out by astrophysical effects. But the reason that this significance is weaker is just because of the look elsewhere effect. So it is not so much that the hidden photon doesn't fit the data, but rather that it would also fit many other hypothetical possible observations. We can conclude that a hidden photon with a mass between 2 and 3 keV can very well explain the excess in xenon 1 ton. So with that, I think we can proceed to the second question, which is how do hidden photons perform as dark matter? As for all light dark matter candidates, the production in the early universe cannot happen thermally, because if it did, they would have been relativistic long enough to prohibit structure formations. Luckily, there are a couple of non-thermal production mechanisms which can generate a vector particle like the hidden photon in sufficient amounts. Firstly, there's the misalignment mechanism. This is similar to the pseudoscalar case, but the energy density stored in a vector field dilutes during inflation, which means that the misalignment production for vector fields typically suffers from very large or even super Planckian field values. So maybe a better possibility would be the production from fluctuations during inflation. The final yield here only depends on the Hubble scale during inflation and the mass of the hidden photon, of course, as well. For our 2.8 keV hidden photons, we would, for instance, require an inflation scale of 7 × 10 to the 11 GeV. In this approach, one has to be very careful with either curvature constraints at scales of the cosmic microwave background, but for vectors, this is mostly less problematic than for scalars, so the hidden photon saves us a bit here. Higher scales of inflation are also possible when non-minimal coupling to gravity is included. So we are not completely fixed to this lower scale of inflation that I gave above. So what one has to do for that is to add a term to the Lagrangian like this one, with R being the Ricci scalar and kappa an order 1 parameter. And in this case, the Hubble scale during inflation can be as high as 10 to the 14 GeV for our mass of interest of 2.8 keV. So a common outcome of this production from inflationary fluctuations is that a lot of the energy is stored in small scale fluctuations. And we will come back to that later. Hidden photons could also be decay products of other fields like an axion, a dark Higgs, the inflaton, or even cosmic strings. So all in all, we can conclude that there certainly are ways to produce hidden photons in the early universe. So hidden photons would be a viable dark matter candidate. And with that, we can go to the next. First, of course, another condition for dark matter is that it should be stable on cosmological timescales. It is easy to see that instability of the hidden photon will not be a problem, because for such a light hidden photon, the dominant decay channels are the ones to 3 photons and to a neutrino-antineutrino pair. In the first case, there's an electron running in the loop, and as a result, the interaction is suppressed by a large power of the electron mass. The result is completely negligible for a hidden photon mass of 2.8 keV as the one that we're interested in. And the other channel is slightly dominant for the mass range, but also unproblematic. So the hidden photon is stable on cosmological timescales and is a good dark matter candidate. But now we finally come to stellar cooling, which was in the title of the talk. This might make the hidden photon interpretation particularly interesting. Various kinds of stars actually can emit light bosons like axions or hidden photons in large abundances. And this is essentially because the hot, dense stellar plasma is the perfect environment for the production of these light particles. This is because once these particles are produced, they are streaming freely and carry away significant amounts of energy. This is why stellar cooling can provide constraints, but also observations of several kinds of stars point towards a small amount of additional cooling compared to what we would have expected from models of stellar evolution. So in this nice plot from Gianotti et al., we see the additional luminosity relative to the expected luminosity for horizontal branch stars, for red giants, white dwarfs, which actually make up all the bottom 4 variables here. We also see that in some cases, in some of these systems, additional cooling is observed, which can be interpreted as a hint for light-near physics. For hidden photons, the horizontal branch stars are the most relevant ones in terms of cooling. They also give one of the most solid cooling hints, actually. The emission of hidden photons is dominated by the conversion of transversal modes inside the plasma. And this can actually occur resonantly if the plasma frequency is similar to the mass of the hidden photon. Now, hidden photon cooling only has a significant impact on the evolution of a horizontal branch star if this resonance condition is fulfilled anywhere inside the star, so in some spherical shell inside the star. When we plot the most recent bounds and hints from horizontal branch stars together with our preferred parameters from the xenon 1 anomaly, we actually get a significant overlap. So horizontal branch stars exclude this lighter area up here and hint towards the darker shaded area labeled HB anomaly. And indeed, a hidden photon, just like the one we may have seen in xenon 1, does not only evade the stellar cooling constraints, but is also close enough to the limit as to explain the observed cooling excess of horizontal branch stars. And this, we believe, is a nice feature of this interpretation of the axis. Okay, one may wonder why the bound of the hint, why both the bound and the hint have this sharp edge at approximately 2.6 keV. This actually comes from the fact that if the mass of the hidden photon is larger than the maximal value of the plasma frequency at the core of the star, then there's no spherical shell in which resonant production can occur. And this core value of the plasma frequency is typically given by something similar to 2.6 keV. And this then gives us this sharp edge. However, the observation leading to this horizontal branch star anomaly is the smallness, is the smallness of the R parameter, which is the number of horizontal branch stars over the number of red giants in a globular cluster. This was carefully analyzed by considering many stellar evolution trajectories, but not including hidden photon cooling, but instead cooling by emission of axions from the Primakov effect. Only later was the observed additional luminosity translated to the case of hidden photons, and that gives the bound that you see here. And that's actually why the hint is certainly somewhere in this region, but what you see in the plot should be considered as an estimate. It would make sense to customize the procedure that gives us this hint to the case of hidden photons. And then it is very well possible that this would extend the hint towards slightly higher masses, because to lower the R parameter, it may be sufficient to cool some horizontal branch stars, but not all of them. So the R parameter, after all, is an ensemble property, and that's why we are optimistic that the true overlap may be even larger than shown here. But we already think that this picture is quite compelling. So we also did a combined analysis of this horizontal branch hints and the xenon results. And the result is that the best fit point shifts to the left, because it of course has to lie within the horizontal branch hint. So a hidden photon of less than 2.6 keV would be able to explain both observations very well. So without a tritium background, the analysis gives us a 3.3 sigma significance, while when we include a completely unbound tritium abundance, we reach just over 2 sigma. We also performed a more rigorous statistical analysis of the combined fit with Bayesian statistics. And here we can use the astrophysical constraints and hint as prior knowledge. Furthermore, we can assign a sensible prior to the tritium abundance, which reflects the experimental expectations. And when we then calculate the base factor for the null hypothesis of no new physics in xenon 1, in comparison to the hidden photon model, the calculation is given here, we get a value of 3.6, and this is commonly referred to as substantial evidence. Also note that Bayesian statistic automatically includes this look elsewhere effect that I mentioned earlier. So this really is the strongest result in support of the hidden photon interpretation. So all in all, we can conclude that hidden photon dark matter could explain the observed excess in xenon 1 and that a hidden photon of this mass could make up all the dark matter in the universe. So this and an additional nice motivation for this explanation comes from the cooling anomaly of horizontal branch stars. So finally, what is there to do? On the one hand, we can reevaluate the horizontal branch hint for hidden photon, as I just mentioned. But more importantly, there are also ways to, how to test this hidden photon hypothesis in the future. So the next generation of direct detection experiments, which are already being built, as I said earlier, they will be able to confirm the excess if it is truly there. And they will also give us details on the time dependence of the signal. And as we have seen, hidden photon dark matter typically comes with large fluctuations at small scales, which would result in a clustering of events at randomly distributed times. Solar signals, on the other hand, would oscillate annually due to the oscillating distance between Sun and Earth. So this definitely gives us a good handle to distinguish different signals in the future. So that's probably one of the coolest things about the xenon 1 anomaly, which is that we will definitely know more about in the not so distant future. So that would be all for me now, and of course I'm happy to answer any questions.
Okay, thank you for the talk. There are questions? There are questions? Well, I start. May you come back to the first slide, since the only things which are important are the data and what the data mean intrinsically. Okay. I see here that you have an excess. An excess with respect, I suppose, a Monte Carlo hypothesis, schematization. I am right, okay? So, yes. So it's true that you could have missed the year or in another part because you use a very large energy scale, very far from the threshold. Maybe you have missed the tritium, which normally can be in trace in such a kind of detector, but could be also that is a very teeny effect. Could be systematics, because I don't hear you to discuss about the systematics both in the Monte Carlo calculations and in the subtraction. Also because this excess is absolutely marginal. In this regard, apologize, later when you give a fit, the fit, I believe for dark photon maybe, you use only two points at the threshold, which is where it is normal that you could have some uncertainty with this kind of approach. 2 points at less than 2 sigma effect. So I appreciate very much the theoretical representation, but I am surprised as an very old physicist that starting from a problem which can be diciamo, phased in a more experimental way, at least in this phase, I say, one start immediately to build all this. You know.
Well, no. So first of all, about the systematics, that's something that we have not studied and that we would have not been able to.
But
study.
The result depends on that.
Well, the systematics are included in the background model of the experimental collaboration.
I duped this because you explain as a possible systematics. For example, when you say that you have to add a contamination that you lose when reading the background model.
Yeah,
and also the systematics could give rise to some differences in the distribution of the subtraction between hypothesized model and the data. However, thank you very much for the talk, because all your study, in any case, in general, is interesting.
Yeah, no.
Thank you. There are other questions or comments. There is no one who wants to say something? If not, we thank very much our colleague.
Thank you.
And go ahead. And now Anatoly Kopilov will give his talk.
Okay, do you hear me? Hello?
Hello?
Do you hear me?
Yes, you should share the
Just a minute.
video.
Yes.
Okay. Okay.
Let's. Okay. Do you see my slides?
No, I see you. You should click on share the video.
Now. Just a minute. Do you see?
Ecco, è andata. Ha avviato. Ok. Ok, ok, now is okay. It's better if you make a full screen.
Okay, just a minute.
Okay. You can go.
Fine. Yes. That's okay.
Yes, yes, yes. Now it's okay.
Okay. First of all, I would like to express gratitude to organizers of this prominent conference for the invitation and for possibility to give my report, what I am actually doing. Well, I will talk about our work to explore the possibility to conduct the experiment on the search of dark photon using a new method suggested and developed by us, especially for this task. This work was done in the Institute for Nuclear Research.
Apologize. May you make an high audio, high level of audio?
Well, I will try closer to the microphone. Is it okay? Well, this work was conducted in the Institute for Nuclear Research, the experimental part right here in Moscow, in Troitsk, in the laboratory at sea level, in collaboration with Igor Orekhov and Valery Petukhov. Okay, the aim of the experiment is to search for dark matter. We know that 84% of matter content in the universe is dark matter, but we don't know what is it and what are properties of this matter. And second, why dark matter is distributed in the galaxy by spherical halo, while baryonic matter in the plane of galaxy. There are many papers trying to explain this enigma. One of the ways to look at this is that cold dark matter is not particles but waves. And if mass of particles is less than 100 electron volts, then we have very high density number and number density. And well, and so that the broad wavelength will be comparable to the distance between particles. Well, here is a well-known picture. Many reporters have shown us this. It explains why we are so sure that dark matter really exists. Not the only argument, of course. The theory of dark photon is presented in several reviews. Here's one of them by Fabrizio Gabriele and Franchi, recently published in Springer Briefs in Physics. Well, PHELEX stands for Photon Electron Experiment. We are using here a suggested and developed multi-cathode counter technique as an extension of a method of addition tended to higher masses. So if the mass energy of the dark photon is higher than 4 electron volts, it means higher than work function of the metal, then in this case, due to low reflectivity of the surface, the photon gets absorbed, not reflected, and emits an electron. So our task is to detect these electrons. So the power collected by cathode in this case is proportional to, not to the volume, to the mass of the gas inside this is proportional counter, but to the surface of the cathode. It's proportional also to rho cold dark matter, which is taken here 0.3 GeV per centimeter cube. But although the no correct value is 0.43 for the region center of the cylinder of the sun. Yes, and then it's proportional to psi squared, where psi is dimensionless parameter quantifying a kinetic mixing, and to alpha squared, which is equal to average value of cosine squared theta, where theta is angle between electric field of a photon and the surface of the cathode. So in this case, where we detect electrons, these power collected by cathode is equal to count rate of single electrons times mass energy of the photon, hidden photon, divided by quantum efficiency. And if you combine these two expressions, we obtain these for sensitivity. Well, this is actually our detector, and this is how it is connected with electronics. So we have here a node of the counter, and the charge collected on this node is going to the input of preamplifier and then to the digitizer. And around central wire, we have a set of wires which produce third cathode. These third, we have first cathode outer cylinder, second cathode is right in the vicinity of the this cathode 5 millimeters distance between first and second cathode, but second cathode is made of wires, tightened wires, and third cathode. Third cathode serves to get high gas amplification of about 2-3 times 10 to 5th, what is necessary to detect single electrons. Well, about first and second cathode a bit later. Well, here in the process of assembling, we have view, general view, they are under test. Well, what we should detect single electrons in the counter. Just for comparison, the signal from the muons crossing the counter. So each time when muon crosses the counter, and we are doing measurements at sea level, then we have a lots of muons, 15 pulses per second crossing the counter. We close the interval 10 milliseconds as a dead interval. And so we obtain 15% dead time, 10 milliseconds per each pulse. And so we should, like this is a rather, it's exotic snapshot. It's not often we see this combination of great pulse and small pulse, just for illustration. And if it's like on this snapshot, then we should restore baseline and restore the amplitude of the pulse. And then we should count these pulses. The energy distribution of single electron pulses is polar distribution. And here we see this polar distribution, and we count pulses from 3 millivolts to 50 millivolts. And estimate, of course, efficiency. So here, what is principle of a multi-cathode counter? Retarding potential of the second cathode in configuration 2. So we have here 2 configurations. We can make measurements in 2 configurations. In first configuration, the potential of the second cathode is such that it does not prevent electrons emitted from the outer cathode to reach central counter. But in this case, apart from these electrons, we count also background from the limited trajectories of pulses near the ends of the count, emission from wires, and so on. So to get effect, we should subtract this background. And for this, we especially use configuration 2, when we supply to the second cathode retarding potential, so that electron emitted from outer cathode cannot reach central counter. It is scattered back. So here we see this picture. Red points are measurements in configuration 1. Blue points in configuration 2. We see that count rates in both configurations are very close, but so the difference will be small. So by this way, we increase very much efficiency, sensitivity of the counting. And because in both configurations, the potentials differ slightly between first and second configuration, it's about 50, 60 electron volts only. So we assume that in both configurations, the counter works in the same way. So we are correct in doing this subtraction. So here are the results obtained. So these are results obtained with neon plus methane gas mixture, obtained during 110 days of measurements. Again, red points, first configuration, blue points, second configuration, and here we have our limit. Upper limit for mixing parametric psi. This result was included in compilation of the data in review of particle physics. Well, but what is important also, that the target is, in our case, is free electrons of a degenerate electron gas of metal. While in other experiments, and the results of these experiments have lower upper limits, but the target here is valence electrons, and these physics in details may differ substantially. So we are considering these measurements as a complementary one. Our counter has a directionality. Is hidden dark photon has internal polarization, and the photon originating from the dark photon should match this polarization. So if the electric field of the photon is along the axis of the counter, cosine squared theta is 0, we should not observe effect. If the electric field is normal to the outer cathode, cosine squared theta is maximum 1/2. When the counter rotates together with the Earth, by rotation of the counter, we should observe variation of the count rate, but only if the surface is mirror-like. The counter with a matte surface should not exhibit this property. It will not have variations. So we can use these counter to control measurements. So here, the calculated variations for 3 orientations of the counter: vertical orientation, east-west orientation, horizontal north-south orientation. Here the axis. Here we have 24 hours in day. And here eta, angle between electric field, vector of electric field of dark photon and the axis of the Earth. And here alpha square, which is actually our effect. So we see that rho for this was calculated for Baksan at 43 degrees north latitude. So we see here that all shapes very different. And second, what is very important, we see that they are symmetrical relative to the moment of the time, 12 hours. Here, 0 time is a moment when the vector of the electric field is in the plane of the corresponding meridian. Well, the same for effect is dependent upon the geographical latitude, naturally. These are the same calculations for India, 10 degrees, and this is the same calculations for Pihasalmi mine in Finland, high latitude 64 degrees. Well, here the latest results we obtained. Red points, first configuration, blue point, second configuration. The effect is difference between these count rates. This is temperature. You see that it's not ideal one because we just doing these engineering tests and so on. Well, here we have 871 points. In previous measurements, we had 200 points. This time is approximately the same, 110 days. Why? Because here we just used more efficiently, you see, organization of the counting process, say, shortly. Well, and these, here we obtained new upper limit, improved upper limit. And here we have diurnal variations of the count rate in configuration 1, in configuration 2, and in the sum of two configurations. We can sum because the count rates are very similar. So we see that actually we don't observe here any variations naturally. And here, the difference between count rates, the effect. You see error bars. Of course, by these error bars, we can't say anything, but just imagine ourselves that error bars are small. And what these blue points, stellar frame, when the day is 23 hours, 56 minutes, and the red points, solar frame, when the day is 24 hours. And I was telling that curves should exhibit symmetry at some point. We don't know what is this point, maybe this, maybe this, maybe this, but should exhibit symmetry. This is very powerful criteria which enables us to reject some possibilities if they are not symmetric. So this is actually what will be the focus of our next year. So to decrease substantially error bars and then analyze where we have symmetry and where not. If we say, discover that, for example, symmetry is around this point, then this is 9 hours, not 12. So 3 hours before this, at this moment, 3 hours before 0, the vector of the electric field was in the plane of the corresponding meridian. We fix direction of the electric field in the galactic frame. That's the task for our future experiment. So as a next step, we are going to use 4 detectors: vertical, horizontal, east-west, horizontal, north-south, and with a matte surface. So each counter will give us a piece of mosaic, and then we collect all together, and we will see what is the image. Summary. The method is working, and first results are encouraging. The observation, if any, of diurnal variations promises a discovery and will enable to determine the direction of a vector of the field in solar star frame. The study can be performed by independent groups in different mines at different geographical latitudes, what will increase the reliability of the results. Our publications. Thank you for attention.
Thank you to you for the talk. There are some questions. No? Some comments? Okay, if not, we thank the speaker again, and we move forward to the talk by Maria Savina about dark matter searches at CMS.
Hello, can you hear me?
Yes.
Okay.
Anatoly, may you keep up? Okay.
Okay.
Thank you.
Thank you.
Okay.
Just a moment. Full screen. Okay. Dear colleague, Today I'll talk about results of the CMS collaboration on dark matter search at the LHC. And the very concept of searching for dark matter on the accelerator is no longer something new. If we believe that dark matter as the universe consists of some unknown elementary particles, then in certain region of masses of those particles or moment transferred on the interaction process of dark and ordinary matter, an accelerator takes its rightful place. The CMS, just like the Atlas collaboration, search for dark matter in the form of weakly interacted massive particles. Suppose that WIMP should have mass about 2 weak scale and small interaction cross-section with baryonic matter. And I will speak about some model approach and search results within this framework. I will touch slightly different topics like ALPS and sterile neutrino. I'll speak only about WIMPs. Okay. Yes, a well-known sketch. It's regularly shown on various conferences on dark matter, and I will show it too. Since we don't know anything exactly about dark matter, except for the fact that it's interact very weakly with ordinary matter and it's electrically neutral, we have a lot of space for model building. As the very first step to describe interactions of dark and ordinary sector, we can use the methods of effective field theory. In this approximation, we deal with contact interactions with, for a given single operator, only 2 free parameters, the characteristic energy scale lambda and the dark matter mass mk. The effective approach is realistic only up to some upper limit of applicability. Then the mass of mediator is larger than the center of mass energy of partner-partner interaction. In our case, it's multi-TF range. And in fact, EFT interpretation is failed at the LHC energies for a large region of parameter space. As the second step, we can move to so-called simplified models, which resolve point-like interactions and involve more search parameters, such as the mediator mass and width, and we can explore more realistic scenarios. And finally, we hope to obtain someday a complete dark matter theory, which may be arbitrarily complex, but it will contain a full right description of all dark and visible interactions. Susie and some other examples could give us a guide how may it look. Before the LHC Run 2, a joint team of theoreticians and experimentalists from the Atlas and CMS collaborations formulated a general framework for describing dark matter models that can be studied at the LHC. It contained a list of requirements and desired properties of the models. Between them, minimal field content and model requirements and model parameters, requirement of the standard flavor violation as in the standard model at the level of the Kabiba-Kobayashi matrix only, not larger, and properties of dark matter particles and mediators. Mediator of interactions from dark to visible sector coupled to both dark and standard model particles. Spin can be different, 0, 1/2, 1, and even 2 for some specific Kaluza-Klein dark matter in some TeV scale multidimensional gravity models like ADD and RS scenarios. Spin of mediators define so-called portals to dark matter. There may be gauge portals, Higgs portals, as well as double portals, combined scalar vector mediated models. Spin of dark matter particles can also differ, and in my talk I'll touch on fermionic and vectorial dark matter. The simplest and most economical way to introduce a dark sector into a standard model is to add only one dark matter particle and one mediator with spin zeros per 1. This approach contains a minimal set of free parameters, it's just 5, and we consider only a channel process in this case. Mediator decay into standard model fermions into dark matter particles gives fully visible and invisible signature, as dark matter doesn't interact with the detector and generates so-called missing energy signals or missing energy transfer signals signature. To have a possibility to observe such a process, we need some label or marker. Such a marker can be mono object radiated in the initial state before interaction. It can be monojet, gauge boson like WOZ, etc. As the LHC accelerates proton beam longitudinally, their transverse momentum and projection in the plane transverse to the beam axis is negligible. So the vectorial sum of all final state particles must be exactly zero. Therefore, if the pair of dark matter particles produced and recoils against detectable particles, we will see transverse momentum imbalance. The net spectra model dependent and an accuracy of result of the experiment is defined by an accuracy of MET simulation and reconstruction. The CMS collaboration operates with MET calculations that show beautiful agreement with observation over 4 orders of magnitude across 1000 GeV, which is quite fantastic, of course, very, very correct simulation and reconstruction. This slide demonstrates limits on dark matter particle mediator mass in the vector and actual vector simplest test channel model. They were obtained as a combination of fully visible and invisible channels. As for visible ones, it's dijet final state. In this channel, we try to final mediator as a new heavy resonance and to put limits on its mass if we see no signal, to include the limits on the dark matter particle mass, not mediator, but dark matter particle. This result must be extended by combining with invisible channel mono X plus MET. And I have to say that when we talk about dijets, in general case, we may suppose that spin 1 mediator decays on also in dielectron final state, not just into digits and to dielectrons also. However, for vector mediator, there are strong experimental limits on coupling constant of interaction coming from Brilliant process. Obtained with very high accuracy. So mediator is often considered as leptophobic. That is, the coupling GL is equal to 0. Combined result is shown for vector and actual vector mediator, shaded areas closed by experiment. The regions bound the great solid curves here and here. Those correspond to the area of parameter space values where relic dark matter density recalculated for a given mass and coupling exceed the real value which we know from astrophysics observations. So, in fact, these regions must be rejected by astrophysical regions in this analysis under its very important moment, minimal hypothesis on diameter field content, one mediator, one particle. If the dark matter sector have non-minimal content, this limit will relax. On the next slide, I present another combined result for leptophilic mediator in dijet and dielectron channel. As I said before, in the case of vector mediator, limitations that come from Brilliant process doesn't allow to have the coupling constant value larger than 0.01. This result looks slightly different than in the previous case due to some redistribution of the decay channels after addition dielectron as a allowed final state. Okay, we can compare with limits and limits which come from direct detection of dark matter particles in terms of spin-independent and spin-dependent Wim-Duclion scattering cross-section at the 90% confidence level. The areas of different colors show parameter regions closed from experiments from different DD and collider studies. Here is shown for mediator vector, spin-independent cross-section, and for actual vector mediator, spin-dependent cross-section. You can see that in the previous case, DD underground experiment have an advantage of up to 6 orders of magnitude, and the LHC experiments and the CMS in particular works good in small mass region only from 1 to 10 GeV. By contrast, for actual vector mediator and spin-dependent Wim cross-section, the LHC have much better perspectives. Okay. Next step from the simplest test channel models to more complicated variants, so-called simplified dark matter models, which are working in an extended framework. Say it can contain extended Higgs and gauge sectors, new specific interactions violating the flavor, etc. What we obtain where we extend our description. And new symmetries give new particles, new couplings beyond the minimal simplest set, and new states, additional Higgs boson, first of all, bosons. New states means new Feynman's graph and new possible processes. And in addition, T-channel exchange by mediator become allowed and important. And shift to SDM give immediately a variety of possibilities and new signatures to observe. On this slide, I collected those new signatures for extended scenarios separately for vector and scalar mediator. You can see that signatures are divided into repeated for different models or universal signatures which have a large information capacity and potential for interpretation in terms of different models. And also specific signatures, which can be a bright signal from one selected model, such as, for example, single top plus meta and same sign top pair. These were for flavor validating models. For the scalar portals, signature also very important, like Higgs decay to invisible and vice versa, decay of new state, heavier scalar state to ordinary Higgs pair. This. On the next slide, I'll give examples of model reinterpretations for several universal signatures. Yes, mono Higgs decaying to BB bar plus MET. Maybe it's the most powerful universal signature for extended dark matter models, which allows to reinterpret the same data in terms of a different set of model parameters. In both cases, consider here, there is an additional gauge group and new vector, and in the second case, also scalar boson. In the baryonic Z prime model, vector boson is coupled to the standard Higgs, which give mass to it. And in the second case, in 2 Higgs doublet model plus Z prime, due to the presence of the extended Higgs sector, a new vector boson is also coupled to additional Higgs boson, what gives us a variety of process and diagrams. Excluding plots obtained for dark matter and mediator mass, also for baryonic Z prime, model interpretation was made in terms of spin-independent scattering cross-section, depending on mass of dark matter particle. The same for reinterpretation for the pseudoscalar mediator in extended Higgs portal model based on 2 Higgs doublet model with adding one more pseudoscalar. In fact, there is a good theoretical interpretation for 2HDM plus A model that such Higgs sector structure reproduced the structure of next to minimal supersymmetry model, NMSSM. It is a well-developed ultraviolet complete theory, a very nice theory. And in the case of exact interpretation in the framework of NMSSM, an additional pseudoscalar denoted as small a should be very light. But in general case, this condition may be relaxed, and upper limits on signal strength, the ratio of standard model and new physics cross-section shown on dependence on the mass of pseudoscalar mediator and mass pseudoscalar mediator and tangent beta, the ratio of 2 vacuum expectation values for 2 doublets in 2HDM model. In our universal signature, also power enough, Z decaying to lepton pair plus MET. This signature allow interpretation as for spin 1 and as for spin 0 mediator. 3 models presented here, the simplest vector and axial vector, 2HDM plus A and Higgs portal model. Then Higgs is decaying to invisible state, a pair of dark matter particles. Results on full are onto statistics from left to right. The simplest vector model exclusion contour for the dark matter particle and mediator mass, reinterpretation in terms of spin dependent for axial vector mediator, beautiful PT spectra, and exclusion plot for the pseudoscalar mediator in the 2HDM plus A model. At the end of this part of my talk, I would like to show results of the analysis of the double portal model, so-called dark Higgs model. The new scalar denoted as S is a singlet under the standard model symmetry group, but is charged under a new U1 local gauge symmetry group. This singlet new Higgs mix weakly with standard model Higgs and give mass to a new heavy vector boson Z prime and to dark fermions. The interaction with standard model matter goes in two ways: in the Higgs sector between scalars and in the gauge sector between the new gauge bosons and the standard model quarks. New scalar S decay in pair of W bosons and with channel dominated with high enough masses of S. And for W, we suppose leptonic decay to the pair of lepton and neutrino. Exclusion plot in the plane of mass of Z prime and mass of singlet scalar S is shown for fixed choice of dark matter particle mass. Sorry, area under curves is excluded. Okay, now I'd like to discuss a slightly different topic. When we developed models to describe dark matter, and when we try to move from the simplest option to more complex ones, we need to expand field content in dark sector. So starting from one dark matter particle and one mediator, then we go to different portals, double portals, interaction become diverse and complex. And from here, in fact, only one step to admit that dark sector can be as complex as the usual visible, and maybe even more complicated. In fact, these hypotheses look more than logical. If we remember that all the matter we know is less than 5% of total matter in the universe, and dark matter, according to the modern data, is 6 times more, why should we assume that all the complexity is contained in our 4 or 5% and not in 26 dark sector percent? The modern theoretical fashion even invite us to consider dark sector as very complex in order to solve a number of theoretical problems, including the hierarchy problem, say in model of twin Higgs and some others, through dark sector. Therefore, in principle, we can well believe that a rich new physics can be hidden in the dark sector. New interactions, new forces, new symmetries, which can manifest themselves through interaction of dark and visible matter. Following this idea, it might be that spectra of new dark particles arranged in some special interesting way, or some symmetries dictate unusual type of decays, or something else in the dark sector works and gives us not just dark particles, but long-lived dark particles. Dark sector search just at the start now, and the concept of long-lived particles play a key role in these studies. Well, what does it mean? Long-lived particles or LLP? Long mean long enough to pass through some piece of detector without interaction and conversion and decay. It's convenient to measure of proper lifetime of particles in terms of c tau. C is velocity of light. That is in fact a distance, not time but distance. Then LLP means that proper lifetime c tau 0 is greater or compatible to the characteristic size of subdetector systems. Here, there are two extreme cases: when c tau is compatible to the inner tracker size, and when it's compatible or greater than a full size of the CMS detector. In the first case, it will be standard prompt decay with primary vertex inside the inner tracker, as variety of standard CMS analysis. And on the other hand, in the last case, it will in either standard case, fully stable particle or MET signature when the particle leaves the detector without interaction. And whereas here in the intermediate case, c tau too long to be prompt decay and short enough to have decay inside the detector. Exactly those signatures named LLP. LLP can be neutral or charged. Charged can be, for example, SUSY partners of quarks and leptons, or say charged neutrinos. And what are those new unusual signatures in detail? First of all, displayed vertices. Usually, when passing through different layers of detector, standard particle leaves traces in all those layers, track segments, which can be connected into one line during reconstruction. Reconstruction algorithms, in particular, assume the vertex approximation from track segments. However, for displaced vertices, it is impossible to carry out such a procedure because the track segments in outer and inner layers of detector don't come together. That is, they don't converge to the supposed vertices. So we need to deal with the shifting of segments, and we need to introduce secondary vertices, so-called secondary vertices, to perform correctly segment joining. Often the situation is more complicated because of no one but many displaced vertices in the vents. In novel LP signatures, for example, disappearing or king tracks, which correspond to decay of charged particle into a neutral one, which doesn't interact and does not leave a trace in the detector in the case of disappearing track, or which recoil against radiated new particles for King's track. One more example, emergent jets, both leptonic and hadronic. That is jets which, in contrast to the standard jets, didn't have a start in the track. They can start too late from the standard point of view in layers of E-cal, H-cal, and even in the inner muon stations. All these signatures, of course, are unique, challenging in conventional, and strictly speaking, it is not exactly the topic for which LHC was created. It requires dedicated analysis strategies, including the new trigger reconstruction and identification algorithms. By the way, this signature allows us to perform interesting studies and to put limits on some special models. On the next slide, I will demonstrate such 3 examples, and I will start from dark photon from mirror dark fusing, one of the variants of complicated dark sector. This is the signature with 2 displaced lepton jets. Lepton jet is just a definition for well-collimated and separated lepton beams from decay of some particles, no more. In this model, we have 2 copies of SUSY, ordinary and dark. Particles from above sectors can interact. So say ordinary Higgs boson can decay into a pair of ordinary neutralino, which can be converted to dark neutralino with radiation of the dark photons, which in turn can be converted into ordinary photons with the mixing parameter of epsilon. And finally, ordinary photons can decay into muon pairs. Those 2 muon pairs give 2 displaced lepton jets, and the study of such a decay chain with LLP signature allowed to put the upper limits on the mixing parameter epsilon independence of the dark photon mass. Those limits are presented for different branching ratios from 40 to 0.1 value for branching ratio. Another example is Higgs decay into a pair of dark photons with 2 ways of conversion. The first one, as in previous, through photon and dark photon mixing, and the second one through Higgs conversion, mixing dark Higgs and usual standard Higgs in Higgs portal. The upper limits for the branching ratio for different dark photon masses are shown dependence of dark photon lifetime. And the last example, dark shower from dark QCD, a mirror copy of the usual QCD. In fact, not a full copy exactly. Those 2 series have different energy scales. Electrically neutral dark quarks, capital Q, self-interacting in the dark sector.
Maria.
Yes.
Apologize. Look at the time, please.
Okay. Just last slide and conclusions. I'm sorry.
Okay. Thank you.
I'm sorry. Dark hadrons can decay into usual hadrons through exchange of the scalar vector mediator, and this process gives us an emergent jets. Upper limits for dark matter mediator lifetime is shown in dependence of its mass. And my conclusions, wide search for dark matter signals carried out in different models, from very simplified to more complex ones. There are no signals, unfortunately, of new physics so far. We have to do further brainstorming, improving on the theoretical base for analysis and expansion of signatures. First of all, take into account T-channel processes, A new generalized approach to data interpretation for scalar mediator based on 2HDM plus A is also coming for collaboration shuttles and CMS. And dark sector search is just at the start, and special LLP signatures can help us to move in this direction. And in general, dark matter studies at the LHC can be considered as one of the most interesting and promising during the run 3 period and after it. Thank you for your attention, and I apologize if I took extra time.
Thank you for your interesting talk. There are questions, comments. If no, we recover some time. Many thanks, Maria, and we proceed with Jirui Wang that will discuss about dark matter searches with the Atlas detector.
Hello, can you hear me and see the screen sharing? Hello, could you confirm if you can hear me and see the screen?
Okay.
Yes, I can.
We hear and the slide is okay.
Okay, thanks. Yeah, that's very good. Yeah, thanks, Chair, and thanks the organizers to have the chance to present the dark matter searches with the Atlas detector on behalf of the Atlas collaboration. Yeah, so there are many things common with the previous night's CMS talk. I won't go into too details, but the so from the astrophysics and cosmology observations, most of the matter content of the universe is transparent. And the dark matter can take up to like 29% of the matter content in the universe. There's one appealing scenario that dark matter is a weakly interacting massive particle, which is also the most studied class of theories. This plot can also be found in the previous talk. There are different types of experiments looking for dark matters. The direct detection experiments searching for the nuclear recoils from the dark matter nuclei scattering. The indirect detection is looking for products from the dark matter annihilation. The dark matter can also be produced on colliders. So, but there's no direct trace of dark matter in collider in the detector, but it could create a PT imbalance. So in this schematic plot, we can see that the red are the visible particles, and the PT imbalance is showing the green arrow, and we call it missing energy, missing ET, and it is a signature of the associated production of dark matter and the standard model particles. Sorry. Yeah, in today's talk, I will give an overview of the dark matter models employed in Atlas experiments, and also briefly go through some recent dark matter single channel searches and the combination and summary of the dark matter searches on Atlas. But I need to mention here, so given the limited time, only a small selection of 4 round 2 Atlas analysis will be presented today. So on this page, I show some representative dark matter models. So for the dark matter searches, it is possible that we look for the mono X signatures and to get the model independent searches. But the theoretical benchmarks are necessary to sharpen the region of interest to optimize the search and for a possible discovery. And it will also give us possibility to be direct compared with the non-collider results. So here are some representative diagrams and models employed in the Atlas, but it's not the full list. So the first one is the simplified S-channel mediated model. It is most widely used. It contains a small set of free parameters to probe the dark matter, but it can also deliver the very interesting interplay between the mono X with the missing ET in the final state and the resonant without missing ET in final state. Another model, the 2HDM plus pseudoscalar, which is also very simple, but gauge invariant, which is recommended by the LHC dark matter working group. It can even deliver richer kinematics and phenomenology by this model. For the Higgs pattern model, it is looking for the possibility that the Higgs boson mediate the interactions between the dark and the standard model sectors, which can enhance the Higgs to invisible decay branching ratio. for the SUSE part, there are many SUSE models predict the existence of the lattice supersymmetric particles, which is a good candidate for the dark matter. And there is also another 2HDM plus Z prime model, mainly probed by the mono H searches. Yeah, then I will go through several single channel analysis on Atlas. The first one I want to mention is the JET plus Missing analysis. The event topology is the JET recalling against missing ET. So the selection we can see it requires very high missing ET, larger than 200 GeV, and it also requires the delta phi between the JET and the missing ET to reduce the multi-JET contribution. The results in this analysis are obtained from simultaneous fit in the signal regions and the control regions. In this plot, we show the signal region distribution, molecular comparison, molecular data comparison. We can see the observable is the hard term of the missing ET. We call it the PT recoil here. Yeah, just need to highlight that they especially in the bottom panel, the uncertainties are reduced to a few percent in each bin for the standard model prediction, which is the background for this analysis, which is a very significant achievement. The interpretation result for this analysis can be found on the right-hand side, including the axial vector mediator and the pseudo-scalar mediator in this integer searches. So there are partial round 2 data set shown in the blue line here. So we can see by comparing the 4 round 2 result and the early round 2 result, we can see the very large improvement achieved in this 4 round 2 Atlas analysis. The next analysis I want to talk about is this mono HBB analysis. So this analysis look for the associated production of dark matter and Higgs boson, which means it can give a larger production rate than those ISR-based production mode. Also gives us higher sensitivity in this channel. So this is Atlas analysis employed both the resolved and the merged topologies, and with the different H2BB reconstruction method. The red data molecular comparison plot shows the signal region distribution in one resolved regions. So this analysis, the results has been interpreted into the different models, the 2HDM plus Z prime on the left-hand side, and the 2HDMA on the right-hand side. So this is the 2D mass plane exclusion plane. So the region inside this contour has been excluded. So just by simply comparing the early round 2 result which is showing the gray field area and the solid black line, we can also find the significant improvement. Yeah. So one analysis with a very similar topology but different object is this mono H2 diphoton analysis. So comparing to the mono H2 mono HBB, given the smaller H2 diphoton decay branching ratio, it has a smaller production rate, but thanks to its clean signature and the possibility the events could be triggered by the diphoton triggers, it gave us much lower and better resolved missing ET in the event and gives complementarity in this analysis. The results for this analysis are extracted from the signal plus background fit in different analysis categories to maximize the sensitivity. So the model interpreted are the same, the 2HDM plus Z prime on the top and the 2HDMA in the bottom. So this is a sine theta, which is the mixing angle of the two pseudo-scalars in this 2HDMA model. So by looking at this plot, we can see under the given parameter of this model, there's a very large fraction of parameter space has been excluded by this single channel. Yeah, on slide 9, here is the recently published mono ZLL Atlas analysis. So this analysis selects events with electronically decaying Z against significant missing ET. The results obtained from simultaneous fit in signal regions and control regions. The control regions are used to constrain the dominant background, including the diboson and also the TT bar. We call it non-resonant in the plot. So the observed Higgs to invisible decaying branching ratio is less than 0.18 at 95% confidence level from this analysis. And some interpretation results can be found on the right-hand side, including the simplified axial vector mediator interpretations on the top and the 2SDMA on the bottom. So both the plot contains the early round 2 result showing the yellow dashed line in the plot. So we can see this very large improvement. It is partially due to the more statistics accumulated in the 2 years, but the major improvement are from the improved calibrations and improved analysis strategies. So the last single channel result I would like to present today is the single top plus mid-CNT. So the signal, so this is a new search mainly targeting for the 2SDMA model. Yeah, so there are different signal topologies targeted in this analysis, including the TG final state and also the TW final state with the 1 lepton or 2 lepton in the final state. This two data molecular comparison plot shows the signal region post-fit result in the 1 lepton region and the dilepton region. So we can see there's a moderate excess in the dilepton region, and reflecting in the exclusion result. So we can see that the observed limit is slightly, the observed contour is slightly smaller than the expected dashed lines. But overall, it is the first time that we're looking for this final state based on the full round 2 data set and deliver a very competitive exclusion result for this model. Okay, so from this page, I will talk about some combination and summary of the dark matter searches to give a more complete picture of the ATLAS result and also to compare with some other experiments. Yeah, the first one, the most widely employed model I still want to talk is the S channels being one mediator model. So as we mentioned before, this model gives very interesting interplays between the mid-CNT in the final state or the non-mid-CNT in the final state, and those searches with sensitivities will vary as a function of the different coupling values of this model, which are highlighted in those plots. So in these two exclusion plots, we can see the vector mediator and axial vector mediator. And to conclude, we can see the very different coverage, exclusion coverage from the mono-X searches and the resonant searches. And for the mid-CNT signature and the mono-X searches, the mono-jet and the mono-photon gives the leading sensitivity. And for the non-mid-CNT signatures, the largest exclusion is from the dijet resonant, but there are also contribution from the trigger level analysis and also like the dilepton resonance. And in this framework, it will also give us possibility to translate the limit and to compare with the direct detector experiments. So I use gray box to highlight the direct detector searches in those plots. And we can find the comparison with the spin dependent exclusion and also the spin independent cross-section exclusion. Yeah, to conclude that the ATLAS results are particularly competitive for the low dark matter masses is where the experiments relying on recoil measurement have limited sensitivity there. But also need to mention the translation is very model dependent. The ATLAS and LHC limits hold exclusively for considered models in those kind of plots. Yeah, another relevant model is the spin zero S-channel mediator. And in this model, the dark matter production is mainly in association with heavy flavor. So the leading sensitivity is from like the heavy flavor plasmicity analysis. And these two plots show the exclusion limit as a function of the mediator mass with the pseudo scalar on the left and the scalar on the right side. So we can find in both of the cases, the strongest limit are placed by the TT bar plasmicity 2 lepton final state, shown in green curves, in two plots. Yeah, on slide 15, here is another newly published result from Atlas. It's the 2H-DMA combination. So this is the first time that we introduce the statistical combination of the two most sensitive channels, the mono HBB and the mono ZLL for this model, which improve the sensitivity a lot. We can see the green contour highlighted in this parameter planes. But I also need to mention that there are significant complementarity from different channels with different signatures. For example, in the left plot, we can see this charged Higgs search, which is this is a non-vicinity in their final state, and it's almost independent with the mass of the light pseudoscalar, so give very complementary exclusion in this parameter space. On slide 16, here's another two exclusion results in this channel. The left is the sin theta scan. Sin theta is the mixing angle between two pseudoscalars. So also here, the strongest limit is placed by the statistical combination of two channels, which is shown in green, and it excludes the full parameter space in this result. And on the right side is the mass of dark matter scan, and we can see that we can see the complementary power from different final state. So the mono X channels, the sensitivity will decrease when the unshelled decay of the two kites are impossible. But this charged Higgs will is independent with this dark matter mass, and it will place the strongest limit in that region. Okay, so the last part of the result I would like to present today is the Higgs portal, the Higgs to invisible combination in Atlas. So this statistical combination allows us to probe the Higgs portal with higher sensitivity. And in this conf note, the results are from the statistical combination of the VBF plus missing T, the TT bar plus missing T, and also the Atlas round 1 Higgs to invisible combination result. You can find some representative diagrams here. So the final observed decay branching ratio is less than 0.11 at 95% confidence level. Just a reminder, in the model, the limit, the decay branching ratio, the H2Z to full neutrino is around 0.1%. And this limit can be further translated into the either scalar or Majorana fermions, and to be compared with the direct detect experiments. So the result can be found on the right bottom part, and we can find it's very similar to the previous S-channel translation. The Atlas results are very competitive, especially in the low dark mass regions. But also need to leave a caveat here. This is a preliminary combination, and for round 2, Atlas will deliver more results into the combination, such as the mono Z mentioned presented before, and some other channels like the VBF plus photon plus infinity. Okay, so all of them bring me to my summary. So there's a large number of searches for dark matter candidates has been performed by Atlas. And based on the selected results presented today, we can find that there are many different dark matter models have been interpreted. And there are complementarity from different signatures reached. And when we compare the Atlas or LHC result with non-collided searches, we can find a significant complementarity in result. Yeah, but there are still many more Atlas round 2 results to be expected, so stay tuned for updates. Thanks, that's all from my side.
Okay, thank you. There are some questions, comments. Colleague, some observation from the people there, in the modelization, in the comparison, and so. No, nothing. Okay. So we thank the speaker again, and we move to Ewan Hill, that will present the latest results of the matter sector and tau physics at the Bell 2.
Hello, thank you. So I have the joy today of covering not just our dark sector stuff, but also some tau physics to be a little bit different. Switch to full screen. So the Bell 2 experiment, along with the Super Keck-B collider in Japan, allows us to probe both at the energy frontier and the intensity frontier of particle physics, allowing us to explore B physics and matter-antimatter asymmetry and precision measurements, etc. The Super Keck-B collider is an E+ E- collider. The majority of the acceleration is performed in our linear accelerator down at the bottom. And then we've got two storage rings. One storage ring has electrons at 7 GeV, the other has positrons at 4 GeV. And because the storage rings are constantly topped up by the linear collider, we have continuous collisions in our storage rings. This allowed us to reach a world record for the instantaneous luminosity of about 3.12 times 10 to the 4 centimeters squared per second squared. With this, over the years, we've now managed to record up to about 213 inverse femtobarns worth of data now. But this is just a drop in the bucket compared to our targets, which is to hit about 50 inverse attobarns. So there's still a long ways to go. The Bell 2 detector, like many particle collider experiments, is a cylindrically shaped detector around the beam pipes. But because our beam energies are asymmetric, thus so is our detector. Like most experiments, we've got some tracking detectors at the very center. We've got electromagnetic calorimeter and some particle identification detectors that allow us to distinguish particles of very similar masses like charged pions and kaons. And finally, we've also got on the outside a detector that allow us to look for K-logs and muons. The center mass energy of the collider is about 10.58 GeV. And it's not a coincidence that this is approximately the mass of the epsilon 4s. This is because the epsilon 4s decays into BB bar mesons over 96% of the time. So the end result is that Super Keck-B is considered a B factor. We make lots of B quarks, allows us as perhaps the main study of Bell 2, which is to study B physics. However, that's not just the only topic of interest. We have two other main goals at Bell 2. One is to search for new physics through precision measurements, which can be sensitive to the presence of heavy virtual particles. So this can involve precision measurements of tau leptons. The cross-section producing di-tau events is actually quite similar to the cross-section producing the epsilon 4s. So we make a lot of taus at Super Keck-B as well. Another main goal is to search for new physics directly. And today we're going to look at that through our dark matter searches. To begin with, let's look at the mass measurements of the tau. The tau mass is a standard model quantity that needs measuring. It's not predicted by the standard model. There are many relations, however, that obviously use the tau mass in it, and so we can go probe some of the aspects of the standard model, to look for new physics. So one thing we can look at is lepton universality. Let's test this. We can look at the branching ratios of taus decaying into electrons and muons, and compare that measured value to the measured value of the tau lifetime, and see if the two results are compatible. The branching ratio is proportional to the mass of tau to the power of 5. So it's extremely sensitive in this relationship to obviously the mass itself, but also its uncertainty. So we want to get the uncertainties of the tau mass low as possible. To perform this measurement, we look at EE goes to tau-tau events in a final state involving 4 tracks, where 1 tau has to decay into 3 charged pions and the other tau decays into just one charged particle, whether it's be leptons or a pion. The method we use to perform the measurement is called the pseudomass method, developed by the Argus collaboration. The pseudomass M min here is an estimate of the tau mass, and we only perform the measurement of the tau using the three-pronged side of this 2 tau decay. The pseudomass is an approximation of the tau mass, but because there are neutrinos, there's obviously some missing information. So whenever you come across something where you don't know, you end up just rounding down effectively, so that pseudomass ends up being a quantity that's always less than or equal to the mass of the tau itself. To do the actual measurement, what we then do is we plot the distribution of the pseudomass and look for the endpoint, where the maximum value is going to give us a measurement of the tau mass. But of course, we apply some corrections based on Monte Carlo to make sure there's no biases. The end result is that Bell2 measures a value that is consistent with the world average from the PDG. And if we look at the plot here, it's the last entry at the bottom. In green, we have our systematic uncertainties and the different experiments plotted. And we can see that the measurement from Bell2 actually has a systematic uncertainty that is smaller than the systematic uncertainties from all the other experiments, with the exception of BEST3, whereby BEST3 did a very different kind of analysis. They did an energy scan instead. Our largest systematic uncertainty from this analysis is due to momentum shifts from our mapping of the magnetic field. However, we know that this is definitely going to be improved in the future. We've remapped our magnetic field and we've compared data to Monte Carlo, and it agrees better now. So the expectations are in the future, after improvements to our systematics, that this analysis becomes systematic dominated after about 300 inverse femtobarns worth of data. Looking now towards lepton flavor violating tau decays, the standard model does not have any violations of these decays. Lepton number is a conserved quantity in the standard model. Now, because we know neutrino oscillations exist, we can introduce this into the standard model in a minimal way. And the end result is that a lepton flavor violating tau decay will have a branching ratio in the order of about 10 to the minus 54. Now, this small number is well beyond the reach of current experiments. However, new physics could potentially introduce lepton flavor violating tau decays with branching ratios on the order of 10 to the minus 10, 10 to the minus 7 levels that we could actually measure. So we can go out and search for these lepton flavor violating tau decays to test lepton flavor conservation in the standard model. Now, there are dozens and dozens of different tau decay channels that could be looked for this kind of search. Because Bell2 has not yet published any results using data, I'll just say that the projections are that with our full data set to 50 inverse attobarns, that we'll be able to push the exclusion limits by about 1 to order of magnitudes, depending on the channel. To look at one specific analysis, which was not part of the Bell2 physics book, we only started looking at it a little bit more recently. It's a search for tau decaying into electron and an alpha, where alpha is an invisible particle. In some searches, one could consider the dark matter candidate. In some models, one could consider alpha to be a dark matter candidate. However, this particular search is going to do a search for alpha where alpha is just more general. Previous searches, like at Mark III and Argus, only involved less than an inverse femtobarns worth of data each. The search here is again going to be looking at a diatau decay with 4 tracks in the final state. The most sensitive variable is going to be looking for the mass, the momentum of the electron in an approximation of the tau rest frame. Currently, we expect that with our current data set, we should have fairly good sensitivity to the search, but we've only done studies using Monte Carlo thus far. Moving towards an actual dark matter search now, we can look at our Z prime search. A little bit differently from other previous searches, we're looking at a model of the Z prime where the Z prime does not interact with first generation leptons. This model is nice because we're going to have some potential dark matter candidates from the decay of the Z prime, but also this model can potentially address the G-2 anomaly. The search that we performed using about half a quarter of an inverse femtobarn worth of data looked at a final state with 2 muons in it, where the Z prime radiates off one of the muons and decays invisibly. You can see an exclusion limit on the right, where the light blue curve is where we make the assumption that the branching ratio of the Z prime to invisible particles is 100%. Simulations have shown that with about 50 inverse femtobarns, we should be able to exclude push these exclusion limits into this red band region, which is the preferred region of phase space for this model that would be preferable for the G-2 anomaly. Moving to dark photons now. The dark photon is a particle that mixes with the photon. And the Feynman diagram I'm showing here is for an inelastic dark matter model version. So here, the dark photon will decay into a Chi1, Chi2, where Chi1 would be our dark matter candidate and Chi2 can decay. Now, depending on the lifetime of the Chi2, it may decay inside the detector, in which case we are going to be performing a displaced vertex search. But if Chi2 is long-lived enough such that it's going to decay outside of the detector, then we don't actually see anything. So we have to have a recoiling object to actually see in the detector and to use with the trigger. So in this case, we require a single photon from initial state radiation. We have a single photon trigger on the experiment, which goes down to about half a GeV in threshold. The largest backgrounds in this search is going to be from electrons going to gamma gamma or 3 photons. But because we're just looking for a single photon in the detector, we're actually going to have a non-negligible cosmic muon background. Since we don't have any results published using data, let's move on to the last analysis of this talk, which is search for axion-like particles. The axion-like particle couples to bosons, so we're going to focus on a situation where the axion-like particle will decay into 2 photons. In this particular scenario, the axion-like particle itself is not going to be a dark matter candidate, but it's going to be a portal or mediator connecting the standard model to a dark sector where we might have dark matter candidates. The final state we're going to be looking for is a 3-photon final state, where we're looking for a resonance of 2 photons. An analysis was performed using about half an inverse femtobarn worth of data taken in 2018. And it's searching for a bump in this standard model background of 3 photons. The analysis selections are relatively simple. One of the ones that we want to point out is that we require all of the photons to have times that are consistent with one another. No significant excess is observed, as one might expect, unfortunately. So we set exclusion limits in phase space of the mass of the axion-like particle and in G. We can see in the blue that with the small data set that we've looked at so far, that we're already managing to exclude parts of phase space that were previously unexplored. So what we see in the end is, just to summarize, that early results from Bell 2 are already probing into unexplored regions, and these early measurements show promise for the future. To get to this, our collider has done nicely. It's set an instantaneous luminosity world record, but there's still a long way yet still to go if we're going to reach the target of 50 inverse attobarns for the experiment. To get to the future, there's still several things to do. We're going to have to remove our draft pixel detector that's currently in place and insert the full one, which is planned to be done, I think, in 2023 or so. And in the short term, upgrades to the accelerator are also going to be required. In the longer term, if we want to go beyond 50 inverse attobars, where we're currently doing studies of what we're going to be required to get to 250 inverse attobars, then upgrades to the detector are going to be required. And we're currently investigating into what those might be. There's also studies of what might be possible if we're looking at polarized beams in the experiment. Thank you very much. I'm happy to take any questions.
Yes, I have a question about the 50 inverse attobar, the so-called final target luminosity. When do you expect to achieve that?
It's an interesting question. So the projections that we've got here is that we're going to reach that in the early 2030s. Now that is dependent upon accelerator upgrades. So we'll have to see how those are all going. Some of the current plans for those upgrades, we don't think are going to quite get us there. So we have expanded our studies into the accelerator upgrades, and we're talking to the wider scientific community about how to get these, what upgrades to do to reach this target. It's not that we're never going to get there. It's just going to take a few more years than we would like. So
thanks.
Early 2030s.
Mm-hmm.
Okay. Well, there are questions? No?
I just ask.
Okay. You have asked your question? No.
Yeah, I did, yes.
Okay, apologize, I was called. Well, we can continue our session, and thanks the previous speaker for the talk. And now we hear the talk by Wei Lin Lin. And he will give a certainly very interesting talk about his activity on the latest result on dark matter search on polarization effect in the search for dark matter vector at the plus and minus collider. Apologize.
Okay, thank you very much. So can everybody hear me? Is my voice clear?
Yes, yes.
And can you see my screen?
Yes.
Okay, that's nice. So I will just switch.
Thank you very much.
Okay, so is the full screen mode now okay? Working okay? Is the screen, full screen looks
yes,
okay?
Yes.
Yes.
Yes, yes, you can present.
Okay, okay, very nice. Okay, so I'd like to thank the organizer for the invitation, and hopefully next time we can meet on site. Okay, so so today I'm going to talk about a search for dark matter in E plus E minus, for dark boson in E plus E minus colliders, including bar, BEL2, and taking advantage of the dark boson polarization. Okay, and so there are growing interest in search for dark matter related phenomena with high statistics and high precision measurements. And so such phenomena has to do with the hidden sector assumed to interact with the visible sector through the messenger particle. So a popular proposal for such a messenger is the so-called dark photon, and which mixes with the hypercharge, U1 hypercharge in standard model. So you can see the references here. So such a mixing induces electromagnetic couplings between dark photon and standard model fermions, and which generate the rich phenomenology. And these people have suggested to look for such light boson, say dark photon through the E plus E minus collisions to dark photon plus gamma. And many new proposals to search for dark photons are also available, and which is listed in the next page. And so these proposals are based upon either a fixed target or electron-positron collider. And today I would like to focus on the later one. Okay, so this is the list of references. So quantitatively, the interaction between dark photon and the EM current is originated from this gauge Lagrangian, where you can see the mixing between the dark photon field strength and the U1 hypercharge with the mixing parameter epsilon to be determined by experiment. And so these mixing can then be summarized into an interaction between the dark photon with the EM current and with the coupling strengths, epsilon gamma multiply the usual charge, electric charge, where epsilon gamma is simply this mixing parameter. And we know that in the limit, the dark photon mass is much less than the Z boson mass. The neutral current interaction is suppressed. And then if one detect A prime, the dark photon, then we can determine these mixing parameters as well as the mass of the dark photon. On the other hand, there could be also other mixing between dark boson and standard model gauge bosons, such as the following mass mixing. So you have the mass mixing term between the dark boson and also the ordinary Z boson. And this is often induced by the extended Higgs sector, as discussed in this article, and also some other related ones. So due to these mass mixing, and one can derive an independent interaction, the neutral current interaction between this dark boson with this neutral current, and the coupling strength is the weight coupling constant multiplied by epsilon Z, and epsilon Z is the so-called mass mixing term divided by the Z boson mass squared. So you have the two independent couplings. You have the gamma, epsilon, epsilon, and also you have the epsilon Z, epsilon gamma, epsilon Z, and you can summarize these two type of couplings in this form. So these are the fermions, and this is the dark boson. Now I just called it, give it a new name, ZD, dark boson, because it has both EM interactions and also neutral current interactions. And so here is a vector coupling, is actual vector couplings, and I choose these normalization. And therefore, epsilon gamma, epsilon Z, these two parameters are replaced by the two equivalent parameters, the epsilon here, and this is overall strength. And there's also a parameter I define as a rho, which is G, the vector coupling multiplied by an actual vector coupling under this normalization. And we know that this rho actually quantify the so-called parity violation. And so in generally we are considering this framework with the parity violation. And so in the search for ZD, the dark boson, in this process can one determine the relative strengths of the vector and actual vector couplings. In other words, we want to discuss the discovery of the dark boson, and also with the sufficient statistics, we ask the question, can we determine the relative strengths of the vector and actual vector coupling? And we will argue that the key is on the polarization of the dark boson. Okay, so this is my outline, and I will show that if the E plus E minus in the particular kinematic region, I will show that actually these boson, the dark boson, will become pretty transversely polarized. And this is important. And then secondly, I will discuss the cross sections of this production for each polarization. And also I discussed the decay of the dark boson to the lepton pairs, which is the way for us to identify this dark boson. And then I discussed to search for these dark bosons and plus gamma with the dark boson decay to muon pairs in Babar and Bell2, and then I will give my summary. Okay, so this is a simple water identities. You have these two Feynman diagrams, and now I like to argue that the longitudinal polarization production is actually suppressed for a particular kinematic region. In other words, if the invariant CM energy of E plus E minus is the largest scale of the problem, then you can write the longitudinal polarization vectors in this way. You just approximate these vectors by the dark boson momentum divided by its mass. And so you multiply the K1 mu into these diagram and the crossing diagrams, you can prove that this is equal to 0 for if you take electron mass goes to 0, okay? So that means that the longitudinal boson production is suppressed, okay, when the CM energy is the largest scale of the problem. In other words, we are talking about kinetic region that the dark boson mass is much less than the CM energy. Okay, and certainly our discussion will also include a more general case. Okay, so this is a current bound for the dark photon search with the dark photon decay to E plus E minus, mu plus mu minus. Okay, so in this exclusive mode, one can see the color in green is the current sensitivity by Babar up to around 500 inverse femtobel, and and these curve the simulation studies by the Bell2. As you can see that now the full integrated luminosity of Bell2 is 100 more than the one reached by Babar. Okay, in this study. Okay. So as I said, this is if we look at the polarized amplitudes, and the theta here is the angle between the outgoing dark boson and with the beam axis, and you can calculate the polarized amplitude for two transverse polarizations and also this longitudinal polarizations. And you can see that for the transverse polarization case, it depends on the parameter rho. And as I said, the rho actually characterize the parity violation. And then if you assume now the S is the largest scale of the problem with the ZD mass much less than the root S, then you see that the transverse contribution inside the parenthesis is actually proportional to the S square, where the longitudinal contribution is only proportional to the S. And so if you look at the cross sections, you can simply just multiply the amplitude square with these kinematic factors. So if we look at the differential cross sections with respect to the angle theta, and you see that we take a so-called V minus A coupling, which is the so-called maximum parity violation case, and also taking the Bell2 CM energy, and we do the calculation. And so when you do that, you find that the longitudinal polarization is simply suppressed, and where the transverse polarization contribution are given by the red curve and also black curve. And as you can see that we take the case that the Z boson mass is only about 10% of the root S. Okay, so this is in the kinetic region that the water identity is true. Okay, and so you see that these two transverse polarization also behave quite differently. I mean, in one case it dominates the backward direction. In another case it dominates the forward directions, and these kind of behavior start to become smaller when you have a bigger dark boson mass. Okay, but still here you still see the roughly the same behavior. You have a very suppressed longitudinal contribution. And if you look at the even heavier dark boson mass, and the transverse polarization no longer dominant, and so you see that this one is longitudinal contribution, and the transverse contribution actually are comparable. Okay, and also the parity violation effect is not very significant, because you see that the black curve and red curve now almost overlapping with each other. Okay, and so this is the situation when you increase the dark boson mass. Okay, all right. So so here we talk about the production distribution for this dark boson, but this dark boson can also decay, because we want to identify this dark boson by exclusive mode, the dark boson decayed, or so-called the visible mode, the dark boson decay to E plus E minus, or mu plus mu minus. Okay, so this is the original boost direction of the dark boson, and this is the lepton, the direction of the lepton in the ZD in the dark boson rest frame, and this angle is the theta d, and we can also calculate the theta d distribution. As you can see that here I have a helicity plus state and helicity minus state distribution, and also longitudinal state distribution. And as you can see that once again, the parity violation parameter rho appears in the helicity plus state and helicity minus state decays. But for longitudinal state, its decay distribution does not involve the parity violation parameter. Okay, so now one can look at an interesting case that now let's combine the production and the decay. Okay, so suppose let's focus on the so-called backward direction. Okay, if the ZD is produced in the backward direction, in other words, the theta is between pi over 2 to pi, and or cosine theta is negative, and also take dark boson mass much less than the root S, and you can see now you have a 3 curve. The blue one is corresponding to rho equal to 2, which is the V minus A or V plus A case. This is an extreme parity violating case, and the black one is either you have a vector coupling or actual vector coupling, and this is the parity conserving case. And so you see that we combine the production and the decay, and we integrated the angle of the dark boson direction. Okay, but we focus on the forward direction, backward direction. I'm sorry, with the theta between pi over 2 and pi, and you see that actually now the leptons also prefer to be in the backward directions. In other words, the theta d, the lepton directions is also between pi over 2 and pi. Okay, so you see this kind of asymmetry, and this asymmetry becomes smaller when you have rho parameter smaller, and with the rho equal to 0, I mean it's a completely symmetric. Okay, so the asymmetry disappears. All right, so so this is for the case that the ZD boson mass, dark boson mass, is much less than the CM energy. But if you have a bigger CM energy, you see down the effects actually becomes now significant. Okay, all right, so we will, so here we can put everything together analytically. And so I look at this double distribution. I have, this is a production, this is a decay, and this is a production angle, cosine theta, and this is decay angle, cosine theta d. So generally, if you work out analytically, you find that actually I have a term so-called Q0, which is not sensitive to the sign of the cosine theta and cosine theta d. However, for the Q2 terms, which is proportional to parity violation parameters, and you find that actually these Q2 terms would be odd in kappa and Kasi. Okay, in other words, the Q2 actually proportional to the product of the cosine theta and the cosine theta d. And obviously, if the cosine theta multiplied by cosine theta d is a positive, or the kappa times the Kasi is a positive, you have a bigger contribution when you have these two in different sign, and then you have a suppressed contribution. Okay, so this is the double distribution. So these motivate us to consider the following asymmetry parameters. So in the Bell-2, you can try to measure the events with the cosine theta multiplied by cosine theta d being positive, and subtract by the negative contributions and divided by the sum of the two. And this is the asymmetry parameters. And when you derive this asymmetry parameter, you find that actually it is proportional to the parity violation parameter rho square. Okay, so so you can obtain some analytical approximations, but to be realistic, this parameter has to be calculated with the actual detector acceptance. So here we have the Bell-2 detector for the gamma, and also for the muons, and so after boosting to the CM frame, you have the rapidity range for the photon, and also rapidity range for the mu plus, mu minus from the decay of the dark bosons. Okay, so we take into account these detector acceptance, and we calculate, so we can calculate the these asymmetry parameters. Okay, so so asymmetry parameters is defined in this way, and which we just defined that, but the statistical errors of these asymmetry parameters actually can be derived in this way. And so if you have root B divided by S, which is just the inverse of the detection significance, then your errors for the asymmetry parameters is given by square root 1 plus asymmetry parameter square. So if you have and so that's assumed that we are quite fortunate that we can reach to the phi sigma detection for dark boson signature at the full Bell-2 integrated luminosity, namely the S equal to phi square root B, and then we can calculate the asymmetry parameters, including those detector acceptance. And here I show you the result. Okay, so here I divide my result according to the different parameter rho. So starting from rho equal to 0.5 up to the rho to the maximum 2.0. And so this is the extreme parity violation case, V minus A or V plus A. And these with the less parity violation effect. And you can see that as you increase rho, you know, the central value of the asymmetry parameters are getting bigger. And also you have a larger significance, more significance that the asymmetry parameters is away from zero, okay, considering the uncertainties, okay, and these A being non-zero, the significance drops as you increase the MZD divided by root S. In other words, the polarization effect now gets smaller and smaller as you increase the Z boson mass, and also the significance of establishing a asymmetry parameter being non-zero is less and less, okay, in this case. Okay, and so here, this slide tells you that if we fit the event, if we divide our event by the kappa times Kasi bigger than 0 being, and kappa times Kasi is less than 0 being, if you consider the two beings and you fit them together, and actually you can reach a better detection significance comparing to the one just counting the overall excess. Okay, so here you have the enhancement factors here, and you see that for larger asymmetry parameters, you tend to get a bigger enhancement. Okay, so let's look at some numbers. So this is we can calculate the background to the above signature. And so we consider E plus E minus to gamma mu plus E minus, and which is the background of our search process. And in doing this background calculation, we know that from the Baba analysis, the energy resolution taken for identify the dark boson peak is between 1.5 MeV to 8 MeV. And here we take it to be 5 MeV for all the mass range. And so for the background, we also use the same event selection window. And so here we have these cross sections for the two benchmark masses. For the dark boson mass equal to 0.5 and 2 GeV. Okay, and so from there, and you fold it with integrated luminosity, you can compute the background events. And if we are lucky enough to have a 5 sigma detection significance, we can also calculate the signature numbers. And this is the numbers for the 0.5 GeV, and this is the number for the dark boson mass equal to 2 GeV. Okay, so so this is almost the end of my my talk. The one of the last slides. So here I just summarize all those numerical results. So here we have the row from 0 to 1.74 and to the 2. Okay, 1.74 is a number obtained by assuming epsilon gamma equal to epsilon z. Okay, so this way you have a more and more parity violation, and this is our benchmark masses for the dark boson mass, 0.5 GeV and 2 GeV. Okay, this is the symmetry parameters, and as you can see that the row, as you increase the row, you have a bigger and bigger symmetry parameters, and these are the signal event numbers. So if you have a more say parity violation, and you see that these two beams have a rather different event numbers. Okay, and if you also take advantage of these, if you perform your fitting to two separate event beams, and you can actually get an even better detection significance by compared to just counting the overall axis. And in the row equal to 1.74 case, you can increase that to 5.4 and 5.5 sigma. And for the row equal to 2, you can increase that to 5.8 sigma. Okay, and so this is the parameter epsilon corresponding to the 5 sigma detection significance. Okay, so it's roughly in the range of 3 to 6 times 10 to the minus 4. Okay, so then we come to the conclusion. So we have discussed the search for dark boson with the process E plus E minus to ZD plus gamma in the E plus E minus colliders. And we show that the dark boson is essentially transversely polarized when the dark boson mass is much less than the CM energy of the collider. And we analyze the mu angular distributions from the polarized dark boson decays and define symmetry parameters, and which is proportional to square of the parity violation parameters. And we calculate a symmetry parameter with Bell-2 detector angular coverage and discuss its consequences on the dark boson search. Thank you.
We thank the speaker for this interesting talk. There are some questions, some specific arguments from the audience. Maybe all people are tired. So if no, we thank the speaker for the presentation, and we go to the last speaker of the session, that is Stefania Gori, who will talk about cosmology and accelerator test of strongly interacting dark matter.
Okay, thanks. Let me share the screen. Okay, here it is. I guess you can see my screen, correct?
Yes, yes.
Okay, great. Yeah, so thanks a lot for inviting me. And today I'm going to talk about strongly interacting dark matter. So since this is gonna be a talk about dark matter, let me first introduce the energy scale associated to dark matter. And as we all know, we don't know what the energy scale is. Dark matter can be super light. We can have axon dark matter or stellar neutrino dark matter. Dark matter can be very heavy, and we can have primordial black holes. But then also we have this intermediate mass range between, say, the MeV and the TeV scale. That is particularly interesting, and where dark matter can be thermal, and it can reach the measured relic abundance thanks to the mechanism of result. For this mechanism to be efficient enough, if dark matter has a mass of below the few GeV scale, then as we know, we need additional particles. So dark matter should be in its own dark sector where we have more than just one particle. And so let's discuss a little bit about WIMPs. As we know, weakly interacting massive particles have been the dominant models for the last three decades or so. The mechanism for WIMPs is quite interesting because we have a thermal dark matter that is kept thermal because of its interactions with the standard model particles. And at a certain point in the early universe, one of these reactions goes out of equilibrium, and then dark matter starts annihilating and depleting its own abundance. But then at a certain point, we don't have enough dark matter particles around, and then the dark matter freezes out, so that its own abundance just gets to a constant. And this is what we measure now. What is very interesting of this WIMP paradigm is that if we take a dark matter mass at around 100 GeV that interacts with the standard model with weak coupling constant, then we know that the abundance is the abundance that we measured. And this has been called the WIMP miracle, or if you want, a coincidence. Now, if this is very interesting, but then we know that we have stringent constraints on this type of dark matter coming either from the LHC or direct detection. And here, just to give you an idea, I'm putting what is the prediction of simple vanilla WIMP models where you have a mediation of a Z boson or a Higgs boson for this cross-section of spin-independent scattering between dark matter and nuclei. And we see that overall, we have already excluded these vanilla models. But then we see that if we go to lighter masses, these constraints from direct detections experiment become weaker. So what we want to ask for this talk is what happens here. So what happens if we have a mass of dark matter that is lighter than, say, a few GeV or 10 GeV? Can we write any model here, and what are the experimental tests? And the model that I'm going to discuss are models with strongly interacting massive particles. And so the idea is that dark matter resides in its own dark sector. This dark sector is actually in thermal equilibrium at a certain point in the early universe with the standard model. To deplete its own abundance, dark matter is having these 3-to-2 interactions, where basically you can take 3 dark matter particles, you scatter them, and then you end up having only 2 dark matter particles. So this is a process that can give us the measure of the relic abundance for dark matter if we start with a thermal population. And what is interesting of this scenario is that we can estimate the dark matter mass that is needed in such a way to have this mechanism in place. And what we discover is that the dark matter masses should be at around 100 MeV or 1 GeV. So basically, this mechanism is giving us a very good motivation for considering much lighter dark matter states if compared to dark matter as predicted by WIMP models at around the electroweak or TeV scale. Okay. So this is in a nutshell what strongly interacting massive particles are, strongly because we consider this reaction to be mediated by some strong coupling constant, some large coupling constant. And then the question is how to realize this type of scenarios. We can realize them in a QCD-like theory, in which you have a large global symmetry, like a SUN flavor times SUN flavor, that you break to the diagonal SUN. And then you will have many light pions, more specifically, a number of flavor square -1 pions. We expect them to be light, and they will interact with their self through this type of Lagrangian. Here you can see the Wess-Sumino-Witten term. And this is a 5-point interaction that that can indeed mediate this 3-to-2 interaction. So these dark pions, as we'll see, will be our dark matter candidate. We also said that we need to have some interaction between the dark sector and the standard model in such a way to maintain thermal equilibrium. And then the question is, if these interactions are not too small, can we detect this type of dark matter? Okay. So let's start with the discussion of the cosmology of this type of models. In particular, let's start with early studies. This plot has been taken from this paper, and in this plot, what we can see is a model in which you have this SUN flavor times SUN flavor broken into a SUN flavor, depending on the number of flavors that we see listed here. And in this type of theories, we can estimate the width for this 3-to-2 interaction, and the width will scale like the 10th power of the mass of the dark pion over the decay constant of this dark pion. And these solid curves tell us what is the value of this m pi over f pi if we want to have the right relic abundance. And we see that since this m pi over f pi cannot be too large if we want to have a perturbative model, then this tells us that the mass of dark matter cannot be too heavy. The mass of dark matter and mass of the dark pion is upper bounded. At the same time, once that you specify the value of m pi over f pi and the mass of dark matter, we can also predict what is the self-scattering of dark matter. And the prediction is shown in these dashed lines. We see that the prediction goes down as the mass of dark matter goes up. We know also that we have constraints on this self-scattering coming from bullet cluster, for example. The bullet cluster constraint is telling us that we have a lower bound on the mass of dark matter. So overall, putting together perturbativity and the bullet cluster constraint, we see that there is only a narrow range of allowed masses at around indeed a few hundred MeV. Okay. So this was an early study, and from this early study, we learned that actually the mass of the dark matter is bounded, and also this ratio between m pi and f pi is relatively bounded, and is close to the perturbativity bound. And if we are here with this ratio, we also learned that since we have a QCD-like theory, the mass of the vector mesons will also be nearby. So they won't be too far away from the mass of the dark pions. And what we have studied in our paper are the implications of having the vector mesons to be around. And first, we have studied the spectrum of this type of theory. We have dark pions at the bottom of this dark sector spectrum. We need to have some connection between the dark sector and the standard model. We wrote down this connection using a dark photon that is connected to the standard model through this kinetic mixing operator. And we want to have the dark photon heavier than the dark pion to prevent constraints from CMB. We studied specifically a theory with three dark flavors. And then we obtained 8 dark pions, the same way as QCD has. And then this, we have learned that dark vectors will also have a mass that is not too far away from the dark pions. And we studied the theory in which dark vectors are here with a mass between the mass of the pion and 2 times the mass of the pions. And then we have several dark vectors as we listed here. And again, this is very much in analogy with our own QCD. So this is all the spectrum of our dark sector theory. And we have studied the stability of the dark pions because we want to have these dark pions being a dark matter candidate. And what we discovered is that actually it's very hard to make the neutral pions stable. They tend to decay the same way that the pions in QCD decay. So either they decay through diagrams like this, where you have the mediation of a off-shell dark photon. But this actually can be prevented if we choose properly the charges of the dark quarks of our theory. So we can put to zero this type of decays. But then we have additional operators that will let the neutral dark pion decay. So operator like this. So at the end of the day, we'll have neutral dark pions that will decay with a lifetime that is comparable to the time of recombination. But this can be okay with our theory. So we'll have some unstable species. And this is okay as long as these neutral dark pions are heavier than the charged dark pions that will be actually stable, and they will be our own dark matter candidate. So overall, we have charged pions charged under this U1 dark gauge symmetry that are absolutely stable and will be our dark matter candidate. What are the mechanisms for depleting the abundance of these charged pions? We have already discussed that we have these 3-to-2 transitions, as it was studied in the early papers for SIMP phenomenology. In addition to that, actually, we discovered in this paper here that we have also semi-annihilation. Namely, these processes here where you take two dark pions and they will annihilate to a dark pion and a dark vector. And then the dark vector will decay back to the standard model because some of these dark vectors mix with the dark photon of our theory. And then finally, we have a third mechanism that is depleting the dark matter abundance, namely the annihilation of two dark pions going back to the standard model, thanks to this mediation of the dark photon. So interestingly enough, these type of theories that were proposed initially for this 3-to-2 annihilation also predict additional mechanisms for the depletion of dark matter states. And depending on the value of epsilon of this kinetic mixing between the dark photon and the photon of the standard model, one of these mechanisms is the dominant one. So let's look at this plot. So the four curves are done for different values of this mass ratio between the dark vector and the dark pion. But what we can see is that at large values of epsilon, so if you are here, the third mechanism is the dominant one. So you have annihilation of two dark matter states going to the standard model. That is the dominant mechanism for depleting the dark matter abundance. If you are here in this regime of epsilon, the semi-annihilation is the most important process. And then finally, if epsilon is tiny, then this 3-to-2 process is the dominant one. And then, of course, it won't depend on the value of epsilon. That's why you see these vertical lines, because this is just an annihilation that happens in the dark sector. Okay. And what is interesting is that, as we show in our papers, thanks to these additional annihilation processes, now the range of masses that is allowed by cosmology is much broader than in the early studies. As we can see here, we are spanning the dark matter mass between a few tenths of MeV and a few GeV scale. Okay. So this is all I wanted to say about the cosmology of this type of theories. And then the second part of the talk will be dedicated to collider tests of this framework. In particular, I want to discuss fixed target experiments and how to test the SIMPs at fixed target. And we have several detection strategies at fixed targets. Either we look for invisible signatures, and this we can do either at fixed target experiments looking for missing momentum of energy. And here is a list of experiments, either running or proposed, that are looking for this type of invisible signature. Or we can use dark matter beam dump experiments, where here you have your high intensity beam that you scatter against some dump, and then you look for dark matter states scattering in detectors that are placed after the dump. So this is for invisible signatures, and then we have we can also look for visible signatures at fixed target. Again, using beam dump experiments, but then after the dump, we place detectors that are looking for standard model particles. And then again, I'm listing here a set of experiments either running now or proposed for the future. And then in parentheses, we see also past experiments. So let's see what we can we discover at these experiments in the context of SIMS. So at the fixed target, we'll be able to produce dark photons since they mix with the standard model photons. And we have several production mechanisms. Either at electron fixed target experiments, we can produce dark photons through Bremsstrahlung production, diagrams like this. At proton fixed targets, again, we have Bremsstrahlung production, or also we can have large rates for meson decays. So these are standard model mesons, like the pions decay into a photon and the dark photon, or the omegan decay into a pion, or the standard model and the dark photon, or also the Rayleigh production. So all these are important production mechanisms for fixed targets, and actually we can produce many of these dark photons. Here, to give you just a flavor of this, I'm showing the number of dark photons that we can produce at a... Excuse me?
Look at your time.
Sure. I have still 5 minutes, right? Or...
Okay, 5 minutes.
Okay. And we can see that at 120 GeV proton fixed target experiment, we can produce really many of these dark photons, even for a small kinetic mixing operator. And once we produce them, the dark photons will decay either to dark matter states, our dark pions of SIMP models, or dark pions and dark vectors. Here you can see the branch ratios as a function of m pi over f pi. And actually what is interesting is that dark vectors will decay back to standard model. So we can have both invisible and visible signatures of this dark photon. And dark vectors are typically long-lived. And here you can see the lifetime of this dark vector. And this is pretty good to be searched for at beam dump experiments. And the conclusion of this slide is that you can see that you can have both invisible signature and visible signature. So you can aim to test these SIMP models at many different types of fixed target experiments. And what we focus on are these two types of experiments: the LDMX proposed experiment at SLAC and DarkQuest proposed experiment at Fermilab. The first one is looking for invisible decays of the dark photon. And the second one is looking for visible signatures, so the visible decays of the dark photon. And here you can see a few details about the experiment, but I won't go through. You can look at the slide afterwards. And here you can see our summary plot. So this is a pretty busy plot, but let's go through a little bit of details and then I will conclude the talk. So first, you can see these black lines here, this line and this line, that are the relic lines for two different values of this mass ratio between the vector meson and the pion. And this will be our goal, because here, basically, if you're here, the dark matter can have the right relic abundance. Here you can see constraints from bullet cluster. So basically, you should be above these lines. So on the right of these lines. And the dark regions are regions of parameter space already probed by past experiment. In particular, you see here at large values of epsilon, you have the Babar experiment, and here you have the E137 past electron beam dump experiment. And the several colored lines are the prospects for testing parameter space at future either approved experiments like BEL2, as we have already heard during this session, LDMX, looking for invisible, the case of the dark photon, or also visible. The HPS experiment that is running in these years, that is an electron beam dump experiment. And then finally, DarkWest, okay, looking for visible decays of the dark photon. And what is interesting is that both the DarkWest and the HPS collaboration are looking are working on these type of signatures. So this leads to my conclusions. I hope I convinced you that strongly interacting massive particles are an interesting thermal dark matter model. There is a natural emergence of a new physics scale for dark matter at around the 100 MeV or GeV scale. There is a wide range of viable dark matter masses, ones that we study not only the 3-to-2 transitions, but also semi-annihilation and annihilation of dark matter. And there is the rich collider phenomenology to be searched for at several fixed target experiments. Thanks.
Thank you to the speaker. And there are questions, comments? Some comments? I just say I am glad to see again the world's strongly interacting massive particle, on which in the 90s, several of us, including us, make measurement at the ground in different approaches. So if there are no comments...
actually, I see a hand raised. I'm not sure if it is a comment or a question, but...
No, it was just a comment. No, to say that this candidate now in the strongly interactive massive particle were investigated in the 90s underground by several apparatus. Scenarios probably is not exactly identical, but I say just for me is good to hear that these kind of candidates are still considered. So I thank the speaker very, very much, all the speakers, for their effort and the results and the idea, the suggestion. And even more, I thank Alexander Studenik for offering all of us the possibility to speak and to speak together. All the best to all people.
Okay, Rita, thank you very much. First of all, I would like to thank all the speakers for a very intensive work during this session on dark matter. And special thanks to you, Rita, for your huge job you has done during the whole day, starting from your presentation at the plenary session on dark matter and then convening the whole session for many hours, you see, and you promote real, very creative and scientifically interesting discussions. And I would like to thank you for this, your very important contribution to the Lomonosov conference. Once again. I hope we shall meet all together in 2 years again here, but face to face.
I hope.
Yeah. Well, thank you very much.
Thank you to you, Alexander, and to all the speakers.
Yeah, thank you. Bye-bye.
Bye. Bye.
Bye.